Welcome to the second day of this workshop. In this we will discuss about supervised classification. So, we will go in chalk and talk mode for this session. Or supervised classification, let me write. I am sure many of you know different types of classification. So, when I say supervised, what else is there? Unsupervised one is there. So, how is it different from this? How are they different?
So, they will provide classes.
Right. In one case, you have a training data where you know what is the expected outcome of it. That is where, so that is why we call it as a supervised learning. And there could be instances where this information might not be there, but still you can do something on that. Do you remember any algorithm from yesterday's overview lecture from Dr. RKG where you have seen an algorithm for this? K means clustering, right. So, at least if you know that, let us say you are dealing with tumors there, you do not really know the output training data you do not have, but you know for sure there are benign and malignant tumors. There you could perhaps go with applying an unsupervised learning, for example algorithms like K-means clustering. There are quite a few instances and applications where you could afford the supervised learning, where along with the data you also have what is the expected outcome of that, that is supervised learning. Okay. And again this learning you could do for different applications. What is other than classification, we discussed something else yesterday. What was that? Yes, regression is another thing. So, today we focus on the classification problem. Okay. Say let us start with a very simple case. Out of this we will, what I will do now is I will start with linear classification case. What we mean by that is, again for easy of drawing and getting an interpretation here, let us consider your feature vector is 2-dimensional, you have 2 features, okay, and assume then you are drawing the features for each class. So, circles are one class and the crosses are another class. Then this is what the training data you have. Now, how could we separate one from the other here? A simple line would do that, right? A simple line would separate them. So, what is the process that you would do, discussing at a higher level? Given this, you extract the features, you have a training data. From the training data, you extract features for each of those image or sample, whatever you call it, extract x1 and x2 for that. You draw them here and figure out or find out a line that separates one class from the other. Then comes, this is what you do in the training data. Then what about the testing time now, where you are just now given, this is what your training phase is done. Now you are given a new image that has to be classified, let us say into class A or class B. So, how do you do that then? That is what, how do you do that is the question here.
You will find the normal vector and take the dot product between them. If it is positive, it belongs to other class. If it is negative,
yeah, that how do you know positive should I assign to this class or negative should I assign to this class? You do not even go to the math level, just tell me intuitively. I got one new sample I have given to you, new image I have given to you. Okay. How do you now classify that? Yeah, that is one way of classification. From there now we are coming to this linear class. See, training, what was the outcome of my whole training process? I could get this line that separates from one class to the other. If it is a nearest neighbor, my whole decision is simply based on even a single sample. So, that is prone to errors, or at least relatively more errors. So, this here the approach is different. I am assumption here is there exists a linear separation in the space of this feature vector for one class to the other. Okay. So, whole training objective is to find this line. What else? How do you do? Now I give you a new image, what will you do then? Correct, that is all. Huh? You have to see which if this is this side of this, we will figure out, means as you said, negative and positive, it will eventually come, but we will arrive there shortly. Okay. So, if it is this side, you will say this belongs to this class, let us say this is class A, this is class, then if it is on the other side, you do class B. So, in summary, linear assumption here we are starting with assumption that this feature vectors are such a way that the features of the two classes can be separated through, well, if it is just 2, you call it as a line, if it is more, it could be a plane. So, this in a higher dimensional space, a linear plane in a higher dimensional space is what you have here. Okay. So far clear? Right. I hope you have done some Bayesian classification or Bayesian approaches for classification also you would have studied, and you have seen yesterday's lecture by Dr. Naveen where you will be looking at probabilities. Suppose if let me just start there and again link it with here, when do you go for all this Bayesian classifications and all? What is the what is the prerequisite to go for those things versus this kind of approach? Have you studied some Bayesian approaches for classification? Yeah, at least some of you would have done that. So, when do you go there? Very good. So, you should have some understanding about the distributions to be expected. Here, it does not assume anything about the distributions per se. Nevertheless, there is some assumption here that these feature vectors is such that they can be separated, that is there. Okay. Say for example, you know that there are two classes, just there is one feature vector I have drawn here, the PDF of them, there is just x1 is here, this is for class A, this is for class B. Okay. Now, a new image has come, I am extracting one feature. How do you decide whether to assign it to class A or class B? This is what I acquired from the training data. So, from the training data I figured out what is the, I know for example, they are each one of them is Gaussianly distributed. I got these distributions, I parameter estimations I have done, I got these distributions. For time being, let us ignore the posterior probabilities and other prior probabilities also. Let us assume that the prior probabilities are equal and all. Finally, this is what you got. Now, I got a new sample for which I have extracted its x bar. Okay? I got a particular x bar. Based on that, how do you decide should I assign it to class A or class B? Sorry? Confidence interval? Each class is equally likely. I have given you x bar, how do you assign? Please do not toss all the probability words, I know you know all of them. This is what I have given the finally, this is what I have given you. This is probability of occurrence of each class is there. How do you assign that? Probability of? Okay, see I am basing my whole classification based on this feature, only one feature is there, that feature I have given you already. Okay, yeah, do I one sample, how should I find PDF from one sample? One feature from one sample, can I find PDF there? I wish I can. We just look at its magnitude, see till here this is called as minimum error based probabilities, that is how you assign it. If your x1 is, let us say, okay, I mean it is not exactly correct, because if I had taken features I cannot draw, but it is okay, but I am sure you can understand this. If any value of x1 here has these probabilities, okay, so again let us assume also the same variance is there, let us make some more assumption here. So in that case what would happen, any value if your x1 is here, the probability of error that you are getting, if you are assigning it to this class, okay, this is the error that you are making. On the other hand, if you were assigning it to class B, the error was more, so you would assign to class A and assign other to class B. So again, if you want you can go through my last semester videos also, where there were around 10 lectures on this Bayesian classification. There you would see what would have, there are different things. For example, what would happen if your variances are different but you have Gaussian distribution, what kind of boundaries do you get there, okay, these are all things are there. So finally all those problems boiled down to finding out a decision hyperplane, because we call it as a decision hyperplane. Here it is a decision point. Had there been two feature vectors, it would have been decision line, decision plane, any number of feature vectors, we call it as decision hyperplane. The whole problem boils down to there finding out a decision hyperplane. You do not have to exactly compute the distributions there, but if you could find out right away the decision hyperplane, that will also serve your purpose. And that is exactly when it comes to this type of linear classification problems that we are going to take a look at today, we will focus on finding out a decision hyperplane. This I could also call it as, of course it is here a line being 2, but imagine you have a number of those things, decision hyperplane. Based on that you will make a call there. Is that point clear? Okay. So now when it comes to the decision plane, typically it is if you had already have seen that there is something called as a discriminant functions that you apply there. That means this is, after all, you are doing a relative comparison. So instead of dealing with probabilities, on top of it you can apply a function, as long as this function is monotonically increasing. That means the relative magnitudes are maintained. For example, if A is more than B, you apply a function here log A for example and here log B. As long as relatively still this is high, you can take a call here. That is all you would require here. Okay. So that's then those kinds of functions, they are referred to as discriminant functions. Now the reason why I am just bringing this probability thing also is that later if you if you happen to study this probabilistic Bayesian based approach for classifications, that gives you very good intuitions about what kind of decision planes could exist. So how many parameters to estimate, in which cases that would be better versus these approaches. So I am just giving you some pointers comparing the both. Okay. So again, yeah, coming back, this discriminant function you could define it. Okay. Let us say you are simply looking at here probability of class A. I am doing some abuse of notation, but hopefully that is okay. If you are looking something like this, if it is negative, okay, if the probability of A is less than probability of B, assigned to one class, right? Positive assigned to the other class. This is where it is 0. Okay, it will not be like this. There is some logarithms you would apply, and there are other things you do for the discriminant functions, but just to give you one possibility, I am telling it here. Okay. So anyways, that is enough for the Bayesian classification part. I will come back here. Now let us define here another discriminant function, W bar transpose into X bar plus W naught. Have you seen this guy anytime? Right? Yesterday only we met him. You would have met him earlier also, but at least yesterday you have met him. This is a line W1 x1 plus W2 x2 plus W naught. Okay, had it been just 2D, what will happen? Accordingly, x1 x2 is there. So here W1 W2 will be there plus W naught will give you the line. Now there is a slight variation to the way we were doing yesterday regression and defining this here. How do we define here is g of x bar is equal to 0, okay, on the decision hyperplane. This is how we want to find out these W bars such that if you compute W bar transpose plus W naught, transpose x bar plus W naught, that should be 0 here. That is how we do this. Okay. Now again, if you look at many of the textbooks, the reasons why it should be positive on one side, negative on one side, what would happen will be a bit confusing unless you all synthesize all things and consolidate and have a holistic view there. So I will spend maybe 5 to 10 minutes to give you some clear inferences here that would potentially help you to get a clear understanding of this. Okay. For that I will write some very basic equations I will do on top of it. For example, assume that I have a point of xa bar here, xb bar here. Okay, I am writing, I have 2 points on the decision plane. Okay. So what do I know there? If I take g of xa bar minus xb bar, g of xa bar minus xb bar, what is that? Xa bar is a vector here. I could comfortably call it as a vector and write, after all, let's say x1 x2, that makes the vector, right? And this is xb bar. Now xa bar minus xb bar, that means this, correct? So then any of this, if I change this, that will be essentially the point on the line. xa bar minus xb bar will be lying here on this line. Hope you all can see that, because this plus this, so somewhere that would value is there. So g of xa bar minus xb bar is equal to W bar transpose into xa bar minus xb bar plus W naught, or no, let me write it slightly differently. I cannot write it this way. For point A, g of xa bar equal to W bar transpose into xa bar, right, plus W naught. This is equal to 0 because it is a point on the hyperplane. Now I will write g of xb bar, W bar transpose into xb bar plus W naught, again a point on the plane. Now what I will do, g of xa bar minus g of xb bar, what is that value? W bar transpose times, you just subtract and tell me, xa bar minus xb bar, and it is equal to 0. xa bar minus these are 2, 0. Very important. You might be wondering what is there to be important there. Can anybody give me any interpretation for this one? What is orthogonal to what? See, xa bar minus xb bar will be a line on this here, right? Xa bar minus xb bar, this is the vector. For example, xa bar minus xb bar is this vector, is it not? This is xa bar, xb bar minus xb bar, so this will be this vector. Xa, so that is nothing but this is a vector along the decision line. Can I say that? So the message here is decision hyperplane is perpendicular to W bar, very, very important stuff, which forms the basis for rest of this explanation. So I will draw one more diagram here, just because we will be doing few more inferences also. If this is my decision hyperplane, I would be computing, okay, which is a result where this is 0. What I would get there is my W bar will be perpendicular to this. This is very, very important. So, that is why your weights W bar would decide where this line will be. By varying your weights W1, W2, what is W bar here? If you want me to write, W bar is W1, W2, so on WD. Okay, d-dimensional feature vector if you have. So, your x bar is x1, x2, xd. So, if you are varying that vector, essentially W bar would vary. Once you know W bar, the line is perpendicular to that. Is that clear? So, in other words, I could also say orientation, this is actually something that you could say from here itself, but I want to explicitly state that orientation of your decision hyperplane is dictated by W bar. Again, make a note also here, this has nothing to do with as such with W naught. What is the role of W naught, can you tell me? So, what I am saying here is, if you, depending on your W bar, if it is this way, your line will be this way, perpendicular to that. That is what you get the decision hyperplane. Notice here it has nothing to do with this parameter W naught. Can any of you tell me what would be the role of this W naught? You just, I will give you a hint, boil down to a case of x1 and x2 and think about that equation and tell me what is the role of W naught there. Just think in y equal to mx plus c, the answer will be there. Right, very good. And what else? How, if I change this W naught, what is going to happen? Very good. It just shifts the line. Slope is dictated by W bar and W naught will tell you where to keep this line. Okay? So, anyway, I could write it also by doing a little bit of math here. I will leave that in the interest of time. So, but I will still write offset or placement is dictated by W naught. Okay? Instead of putting equations numbers, I will put to these inferences, very important inferences. Fourth one, suppose I have a point on the right hand side of this equation. Now, I am standing parallel to this line and then I am saying that is the right hand. Okay. This right hand side, I have a point here. Now, all I know for now is g of x bar equal to 0 here, for this line is all that I know. Now, I would like to figure out what would be g of x bar for this. Can anybody help me? So, again I want to come to the same thing you are saying, it will be greater than 0 or less than 0. How could I arrive that? Can somebody help me on how to deal with the math for arriving there? Between what?
Between the x point and the normal to the
Right. Okay, maybe in the interest of time I will go ahead, maybe what you are saying is same as what I am going to do. See, what I could do is, let me draw a perpendicular here to this line. Okay. Anyway xa, xb I used, let me call it as xc bar and this is xc bar. Okay. So, basically this is my xp bar initially. What I did now, I write it as this plus this. Okay, xc bar plus whatever you call it. Do you see any relation between this and this? Right, they are parallel. So, can I not write it as r times g of what should I write? R times, or I will write w bar by norm of w bar. Can I write that? R is a scalar quantity. I am taking a unit vector in this direction and that multiplied with the scalar will give me this length. Is that fine? Will R be positive, negative? Can't say. Can you say something about R? At least for that point. Will R be always positive? Can you say that? Yeah, but might not be the case, because see here this is all the first in equation is all that it is telling is perpendicular only. I could have my W bar in that direction also, still that is holds good. That is why if it is in this direction, that is positive, R is positive, could have been in the other direction also, we do not know. It depends on where you initialized and where you ended up. That is why for some class, class A is positive, class B is positive, unless you verify it you will not be able to say that. Okay. Now let me hope that point is clear. It could it depends, W bar could be in this direction, or for the initialization of W bar you have taken, it could have been in the other direction also. Okay. Yeah. Now what we will do is, we will write the G of xp bar. What am I doing? I am computing this discriminant function for xp bar. How could I compute that? This is nothing but G of xc bar plus R into W bar by norm of W bar. So substitute there in that equation, that is W bar transpose into xc bar plus R times W bar by norm of W bar plus W naught. What is its value? Do you see some terms resulting in a 0 value? I would say this plus this. See, for a point here, if you write the discriminant function,
0.
that is nothing but you take xc bar here, W bar transpose into xc bar plus W naught is 0. So all this results in is, this is a scalar, I can move it before, W bar transpose W bar by norm of W bar. What is that value? Anyone have any idea? W bar transpose W bar, what is its value? Very good. It is very easy to see. You just multiply W bar transpose with the other one, W1 square plus W2 square, and all you will be getting. So norm is square root, so you have square. So what is the resultant value then? So another important result is, for any point P, for any feature vector xp bar, you could say that G of xp bar is a measure of what? A measure of Euclidean distance from the decision hyperplane. Very another, I would put maybe 3 are done, so I will put it as 4. Why am I writing it that way? See here, the norm of W bar is a constant for a chosen value of weights. Then if you look at a point here, a different point, what is a perpendicular there is essentially giving you an Euclidean distance, correct, with the sign change of course. So if you are computing G of xp bar for 2 points, if one is more than other, the one for which it is more is far from this decision hyperplane, right, because you draw a perpendicular there, the length will be more. I take some point here, what would be by my R value? This is my R value, because anyway that into unit vector only I am multiplying, right. So it is a measure of Euclidean distance. Not only that, now it should clarify you why this value G of x bar value is positive on one side and negative on the other side. Why? It is because this R, if you want to have exactly a point here, to achieve that your vector you have to take it in the opposite direction, unlike here. So that will be minus R there. So for all the points on this side, the discriminant function will be negative, for the other it is positive. Of course, if I had my W bar in this side, then this would have been negative for this and positive for the other one. Okay. These are typically some missing links where they will write, you know, from your 12 plus math, that is how the equations in some of the textbooks I have written, but this, unless you have the, you will appreciate better if you have this clarity. To just quickly summarize, the decision on the decision hyperplane in your linear classification, the value of your discriminant function is 0. On the other side, one side it will be positive and another side it is negative. Which side it is positive and which side it is negative depends on your W bar you are having at that point of time. And not only that, if you compute for any point in this feature space, the G of x bar will tell you, give you a measure of how far it is from the distance plane, from the what is this DHP? Which hyperplane? Decision hyperplane. How far it is, it will tell you. These are the most important things that you should have a clarity. Is that clear? Or are there any doubts or missing links? Okay, hope you are making a note of these things also. Right, good. What shall we do next? Now, how do you think we will, this is all good, this is all telling you given a decision hyperplane, things are very easy now. For example, then if you are given a test, yeah please.
This W bar can be one of the data point also.
No, it cannot, it has nothing to do with these data points. See, this is something which separates them, separates these two lots. These are any of them, if you take it, those are the data points. This is a different thing. This is something that separates these two lots.
But maybe theoretically it may be possible that this W bar may be it's an n-dimensional point in the space.
Right. Means all we can say is decision hyperplane is also in the same space, feature space, but very unlikely unless we come up with some tailor-made thing where it would come, and then ideally this should separate. It should not be, if I have something like this, means again, see this point is different from a plane, that also pay attention to that. It may even assume that there is a one point might be there here, there are so much crowded that somewhere I have to take a trade off, then it might pass through that point. Okay, that is an accidental, or that is the best you could fit, but there is no way you could see anything related to this point being the decision hyperplane.
Weight vector.
Okay. Yeah, might be you might take some average and maybe that way you may initialize. If you want to do some initialization of averaging or something like that, you might do. But other than that, it's not like any of the points should become a weight vector. Yeah, means weight vector is not this, this is along this, right. Okay. Any other questions? Right. So, in that case, now if I with a magic wand I found this decision hyperplane, and then if you are given a point, it is very easy to say, you look at G of x bar and see if it is negative or positive, figure out which side it should be negative, which side it should be positive, accordingly assign to that class. This is easier. But how do you find this line now? As he was asking something related to that only, how do you find this line now? Any ideas on that? How should we find? Just forget about math for a moment. I give you those points. Why do you fit that line here, not a line here? Why were you keeping this as your line? Why is it so? What is the problem with this line being the decision hyperplane rather than this? What is the problem there? Yes. Right. So, misclassified feature vectors, there are quite a lot of misclassified feature vectors. So, what is it that should drive finding out this decision hyperplane? Yeah, support vector is even a little advanced than this, where there are multiple possibilities. We are not even going to that level now for that moment, but that is eventually what should be done. Even before that, even a simpler case, just to take very few things. See, I give you 3 lines, okay, this has one decision, this has one decision hyperplane, this has one decision plane. What is it that you would choose? The middle one. Why is it so?
It properly separates two classes.
Sorry?
It separates two classes.
Right. So, rephrase it slightly, that is indeed true. Rephrase it such that I need to now come to some mathematical terms to solve this.
Linearly separable
Minimizing the number of misclassified.
Yeah, that's right. So you need to minimize the misclassified feature vectors here. That is how you are going to now define your penalty function. That is the most important thing now. Okay, that's what we will do now for next few minutes. So, see, somewhere my function has to be iteratively driven and I should arrive at something that minimizes the number of misclassified voxels is coming from me, misclassified feature vectors there. Okay. So, what could be that? For example, we define a penalty function now, right? Let us, you take for example, forget about the testing for a moment, just consider the training one. You initialize with some weight vector. Now, have a set that gives you all misclassified feature vectors. It has all misclassified feature vectors. Now, what I should do is you go through for all I that belongs to y, that means I go through all misclassified voxels there, and suppose if I keep g of x bar, is that enough or something else I should do here? What is the problem? What will this do? See, we have already seen, by the way, is this scalar or vector g of x bar? Scalar, right? Okay, this is a single value for one feature vector. What will this will happen now? Or maybe I will write you the answer, then you tell me. I will put it this way. My last function is that for all misclassified voxels, I will compute g of xi bar and take an absolute value. Can you give me an interpretation for what I have written here? This will help you. Something I have erased from this space will help you that. Very good, very good. We have already seen, that's why I told those 4-5 points are the key building blocks to understand the whole linear classification followed by nonlinear classification. G of x bar gives you a measure of distance, Euclidean distance from the decision hyperplane. And now you consider it as an error whether it is on this side or this side, as long as it is misclassified. That is an error, correct? That is why I have taken g of x bar, otherwise 10 misclassified for class A and 10 misclassified exactly a reflectance of that on the other reflection of that on the other side will make it 0. Okay? Mean square error, you know, or square, you take square because you want to get rid of that, or you take absolute values and then sum them up. So, it is for that reason I have taken that is the reason why I have taken absolute values. There is a slightly polished way of writing that you would find out. For a reason it is written like that, is for all I that belongs to y, let us say delta xi bar into g of xi bar. Okay. This is to just say, if it is one class, if it is misclassified the other way, see which one to be, all negatives have to become positive. Assume that g of x bar is positive on that side. Okay, I have drawn so many things here. So, better, since we would spend some more time with that graph, let me redraw that rather. Okay, that is one class, this is another class. Here g of x bar, assume that this is positive. It could have been other way around, you have to figure it out based on your w bar. Okay, g of x bar is negative here, this g of x bar is 0 here. Okay. So, now well, coming back here, see if this line, for example, this is positive here, you got for some reason you got here, ideally the line should have been like this, assume that. So for this point you get positive, right, you should get negative. So essentially just this is a mathematically looking at things, you would accordingly for one type of misclassification, this is whole thing, the purpose of this is to make each value positive, just look at it that way. Okay. So this is how you have defined your loss function now. Well, loss function is fine, but how do you cope up from this loss? How can you leverage from this loss function now? For example, I initialized something here. Okay, this was my initialization. Okay, don't ask me why I could manage with my initialization parallel to it and just move there, or maybe that will only change W naught. It's okay, but assume there is some line there. Now, how do you leverage from this loss function to improvise your thing there? What you do there is, for example, your new value of W bar that you are going to make out are your old values minus some alpha times dou J of W bar by dou W bar. What is this? Gradient descent. So if look at here, maybe to give you some intuition, let us say the relationship between this W bar and this function is something like this, with your where you have your this W bar. Now what will that, or J of W bar is this function. Okay, right. This is what I have drawn is a one dimensional thing, but just as I am drawing it for some intuition there. What will happen here? Suppose you landed up here. You want to, minimization means your penalty should get minimized. This function, what is the finally what should happen? Select W bar such that J of W bar is minimized. That is the whole objective here, is it not? So how would I do that? Now W bar new will be W bar old, you do a gradient descent here, that means you find out the slope of it, multiply it with a scalar, because that is the proportion of weight that you want to do for each step. And what will happen, for example, here, this will slope will be in this direction, let us say here, that's, if you look at it, it's a negative slope. I take a negative value here, that will make a positive thing. I take, depending on its magnitude, initially I was here, now what I will do, this will make me to move in this direction and I would reach in the next iteration here. If my alpha is more, I may make a bigger jump there. It could be even I might go here, then I have a positive slope, minus is there, that will pull me here, and finally I could end up here during my iterations. I repeat here, you have defined a loss function here for which the parameter is W bar. Now find out how is this loss function is defined is, for all misclassified voxels, you are taking absolute sum of absolute Euclidean distances, or a measure of that, because there is W bar also there, not worry about that, but it would give you G of x bar would give you the measure of that, right. So that you are computing and summing them all, and that is how, when will this be 0? When you got the right W bar, that will be 0, that is the whole idea there, right from here, right, and you repeat this whole process until you arrive here. What will happen if I take gradient ascent? Maximum. What will then, how is it different? Equation is different, there is just a plus. What will it do? If it is this way, it will pull me this side, and slowly it will land me on the peak there. What is peak here is very bad there, okay, that is a trough in fact there, we do not decide that, you do the gradient descent there. And so this is how, so in summary, you initialize your W bar to some values, then this is the loss function that you would use, and this is how you approach this to compute the new W bar values. You repeat this until, in an ideal world you repeat this until, what will happen at the convolution in an ideal case? That what does, when will that happen? When will the error be 0? When will that be done? You are coming down, I am trying to take you up. When there are no misclassified feature vectors. You are doing the whole thing sum for all misclassified voxels, right? So when that happens, this is ideally, but there could be cases where there are some outliers or the feature vectors are such that they cannot be absolutely separated for few. It could be various reasons, but in an ideal, when the assumption that they can be linearly separated is true, it can end up you there. Clear? Any questions or any doubts, comments there?
Will it always reach global optimum using this?
Very good question. No, this is a very difficult one to answer. Reason being, if your jumps, for example, are bigger one, this is, see, there could be something like this. Gradient descent is never a global one.
But if the loss function is convex, you can try to be local.
Right. What is this? What we are taking is an absolute thing that itself as such is not convex.
If you try to square it up, then will be able to
G of x square.
making it positive and
Not sure, because the gradient descent itself is an incremental approach. It is dependent on the initialization. See, whatever you make there, look at it here on which you are doing the gradient descent. What would happen there? The gradient descent, you are from the initialized step you are going, yeah, if the function whole thing can be made convex, that is a different thing, but I do not think this can be converted that way. I do not think so. And again, it is also important to have a look at how much jump you allow here, because that may either slip or the one which is there optimal, or will make you struck also somewhere. You will probably, there could be something here much down than this, but you are making small moves, you will end up at this solution only. So to deal it, the more efficient way people do is you take multiple initializations to your W bar, okay, and you repeat the whole process, and finally you take that solution for which your J of W bar is minimum among all of those things. And of course, there is not only that, this step also is very important there. So that is something one has to pay attention to, how much should I go. And there are even other things also possible. Your function could become kind of plateaued somewhere, and the slope is almost 0 here, and you will struck there, right. So there will be, if you look at this one, they have approaches where they add a momentum term to it, which gives you, momentum is nothing but if there is nothing coming from dou j by dou W bar, you still have one more term that will simply push you from there. You still have a minimum step that you would take there, okay, and that will be based on what was the previous W bar. Based on that, this momentum will be given, thus that term will be also there. Not only that, do you remember from the last lecture yesterday, he was talking about online learning. You have each sample is coming one after the other. This might happen in some training also. You might be getting training samples, it is not that you have in one lot, okay. So if one after the other samples are coming, the summation won't be there as such, or there could be instances where you calculate this value for just sample wise and you keep updating W bar for each sample. There is a batch thing where you put whole thing there, and then based on that you do this, okay. This J bar calculation could be sample wise also. So that means instead of this summation, I take only one misclassified voxel, compute this, update my weights, and then again go here. I could do that. or if your training set is too high, you take somewhere the path in between where you have 10,000 samples, you just take 100 samples at a time and do the updation of these weights. That is also done. Okay. There are still other approaches. Anyway, I think that is good enough. Okay. One more, just I will leave you with one more point here, which is important, is these feature vectors could be having different scalings. So, when you compute this here, what could happen is one that is there in a higher scale, assume that there is something in the range of 0 to 1, another is in 0 to 100. So, you will be biased or dragged by that alone, such that this happens, the whole convergence happens based on that. So, in order to avoid that, you will typically normalize these feature vectors also before coming here and doing it. And there are some ways to initialize these weights also. What could be the range of weights that you could initialize, so that there are more chances that you could converge is also there. In the interest of time, we will not be able to discuss that. So, that is another thing that is there. Okay. Are those points fine? And maybe you are thinking we would discuss about neural networks and neuron. Where is the neuron here and where is the neural network here? Isn't that any of you are wondering about that? So, those who have already studied, can you tell me how is this related to neural networks and all? Where is the neuron model and everything? Neuron, huh? Where is the neuron? Do not tell me it is in the brain. This whole thing is a single neuron perceptron model you could think of. Okay. So, now one thing here, just one missing link, then I will come to the neuron. So, the neuron model which you would probably are more keen on looking at is how do I do classification here in this whole thing. This all would help me to find out in the training W bar, then how will I do the classification? I already answered that, so I am sure one of you would still remember. At least in the beginning you were probably awake and you should remember that. So, you have given a test sample now, you should tell to which class I should assign. How do you do that? Huh? That is all. G of x bar you compute. If g of x bar is negative, assume that my class A, I will call it as 0, my class B I would indicate it 1. So, if it is, let us say if they assume based on this W bar, my assumption is for class A it is positive. So, what you will do now is, if it is negative, okay, this is my, I am just plotting here, if my, this is g of x bar here, if it is negative, I give to class A, positive class B. Something is tickling, something is ringing in the mind once you see and the relationship to your single neuron model and all? Sigmoid function. What is all this we are doing here? W1, X1 and all those things? That is the integrator and the sigmoid function. Okay. Let us do that now. I will not deprive you from neuron model, we will do that now. So, you have feature vectors W1, sorry, what is W1? What I should have written if it is a feature vector? X1, yeah, X1, X2, let us say d dimensional one, XD, okay. Then what will happen then? I am going to, what am I going to do here? W bar transpose times X bar. So, W1 X1, expand this, I have given you already here W1 X1. So, W1 X1 plus W2 X2 and so on, WD XT. So, flow graphs you are all familiar with, and this tells you the multiplication one I need to sum them up, okay, and then what do I have after that? This is at the end of this, what do I have here? What is the output here? Right, g of x bar. Then what should I do? That, okay. And what do I have here? Y. I can call it y, a simple scalar, 0 or 1, 0 for class 1 and class 2. Okay. This, if you look at in not so well written textbooks, the explanation right away starts from here, where they say that this is inspired from the neuron model, dendroids are there, means that probably is how it has been started, but this mathematical framework will nicely put you that, and this is a very convenient representation, and of course it helps you a lot later when you come to multi-neuron model. This helps you a lot. But when somebody asks you why activation function is there in the interviews, the students' answers are, they will say that is how our brain works, sir. That is the answer I have been getting there. And why you are summing up, when we ask the students, they would say in our brain there are dendroids, they will take inputs and then they do weighting, that is why we are doing weighting. Okay. Then we take decision, and then something else is missing here, by the way. What was missing? Right, bias. So why do you need bias function? They say that in our brain there is some bias, that is how we take decisions. Okay. Well, and why g of x bar is negative for one, positive for the other, no answer there. But to understand that, this is very nicely coming out. Hope you have, now you will be able to appreciate the neuron model better. Okay. Probably that is what would have stimulated. I haven't read well, let me admit that, all this, whatever all models are there. Definitely that would, something would have motivated and inspired from there. But now, with all due respect to that, you could even understand that from a proper mathematical point of view on how we are doing it, and even we could relate it to or compare it to the Bayesian framework also, what we are doing there, the discriminant function there. Okay, fine. Right. So this I will write it here as W naught. Okay, this is, you call it as the activation function, right? This you call it as integrator. Then again make a note here, my assumption here was there is a line here or a hyperplane here, w1 x1 was good, but I could have even have a polynomial there, nothing stops me from doing that. So that is where you could have different, this integrator function need not be this way, you could come up with different integrator functions also there. Okay. So before I go to the nonlinear one, just let me draw your attention to here, because this is something again in the math yesterday it was not discussed. What is the dimensionality of this one, dou j of w bar by dou w bar? What is the dimensionality of that? Huh? What is the dimensionality of that? D by 1. Okay, do not think that this is one value. So how do you compute that? That is nothing but saying dou j of w bar by dou w1, dou j of w bar by dou w2, and so on. So taking partial derivatives with respect to each, this j of w bar, if you notice, have w1, w2, w3, everything. So you are taking partial derivatives of that here. Okay, keep that in mind. Okay. So anyway, since just to make sure you understood this, let us say I have w bar transpose w, for example. Okay, this is my j of w bar. Okay. Now what would be the dou j of w bar by dou w bar for this? Very good, very good. I am glad you got it correctly. Okay, because it will always, you just write it in a simple case. If you do not remember also, just take w1, w2. What is happening now? w1 square plus w2 square is the result there. Now you want to take that derivative with respect to w1, will give you 2w1 there, right? Then it will come, this will be 2w1, this will be 2w2, so 2 times w1, w2. So for all these derivatives and all, particularly once you go to this multi-neuron model, you will get so many things there. So, always keep a very simple example with you and figure them out, that will help you. Okay. Yes. Okay. Now, we wish everything can be done linearly, that is not the case, you might go with polynomially, that also will hit a limit somewhere. Then what should we do? Let us take another example here. Okay, any questions so far? Can I go ahead? I will give you one more scenario now. Okay, I should have not drawn it. Again, even if I without drawing also you could easily make it out. Now, from the training data, my x1, x2 samples have come like this. Okay, there is not always guarantee that it will be linear. Then, can you find out a linear line that separates them? Maybe yeah. But on the other hand, I could say that if I put two lines here, I could say this will be these, I could separate them. For example, this is, let me call this line as g of x1 bar, this as g of x2 bar. Okay, assume that I draw two lines here instead of one line. Can then, if I process the result of this, will I be able to separate? That is the question here. So, well, let me also just come back here now. What I will do with each line, I have g of x bar and I will apply even activation function also. Assume that this side it is positive, this side it is negative, and again this side this is positive and this side it is negative. Okay. And class labels, for example, positive one, let me call this with class 1, this is class 0. Okay. Now, assume that let the output of this be y1, this be y2, output of this. Okay, I am doing two different lines. Okay, outputs y1 and y2 I am calling. Finally, I need some output y, whatever I want, I will put it as y. Now, this line if I take, okay, what will happen here? So, with respect to this line, right, how can I separate them? If I get y1 and y2, what would be the y1 and y2 values here? So, y1 is corresponding to this and y2 is corresponding to the other one. Okay. Negative, let me put it as 0 here. So, as I have drawn here, negative till this negative value, this is 0 and 1, correct. For this region, this is negative, and what is the value with respect to this line? Will I get negative or positive here for these points? No, for these points. See, this side it is negative. For this line also this is negative. So, this is 0. Okay. I call this as, let us say, class 1. Now, look at these points here. With respect to these points and y1, is it negative or positive there? Positive. Okay. That is 1. This is with respect to this is negative. So, I will get here 0 and what is that class? 0. Now, look at these points now. This is positive, this is positive. So, both are 1 and I should assign it to which class? Class 1. Right. Now, what I will do now? So, I have y1 and y2 now. Say my class 1 0 0, if y1 is 0 and y2 is 0, that belongs to class 1. Okay. Let me put it here, both are 0 is class 1. Now, it is y1 is 1 and this is 0, that is also class 1. Both are 1, this is class 0. That is how I should do. Now can I separate them?
So,
1
0 0
0 is 1, 1 1 is 1. Yes, yes, I would have landed up in a mess now. Thanks for saving me. Okay. So 0 0 is 1, 1 1 is 1, 1 0 is 0, the other class. Can I separate them now with a line, linear line? Yes, I can draw a line like this and separate them. This is exactly what nonlinear classifier does. Instead of having a single neuron which gives me one decision hyperplane, I will use multiple neurons, get the outputs of that, and then again do a classification one more time. Is that making sense? So let me draw that out now. This I have drawn apt to this blackboard size, but since I have to draw more neurons, I will redraw that. These are my feature vectors x1, x2, x2d. Now what I will do now? There is one neuron here to which all these inputs are coming with its own set of weights and W naught. There is an output here, and there is another neuron there to which also these inputs are coming with their own weights and bias. Then what I did, notice that this is again I am drawing one more line. What are the inputs to it? The outputs after applying my activation function, right? So I have here just an f dot I will write, output is there. Here also I will take an f dot here, I have this output here. What am I doing then? One more neuron I am feeding. So I have one more neuron here, I will feed that, two inputs are there now, right? And then they will have their own weights and a bias here, and that again I will give again 0 1 I should come. So I will have one more activation function here, and that will give me the value of y. So this you call it as hidden layer. In between it is there from your input to that, and this is your output layer. And of course, just for this example, you are able to see the very objective here. If you look at it, how many neurons should we take essentially depends on, if you look at the segments that it is getting, essentially finally a linear that should essentially segregate into different groups. They might be there, one here, one there, one another place. Assume that there is one more class here. There should be, okay, that's 0 is not a problem. So it could be something like that. So how many neurons do I need depends on the complexity of the distribution of your data. In other words, because that is what is segmenting it into different, partitioning it into different regions, that would dictate this. And this just need not stop at one level. You could have multiple hidden layers also. Sometimes depending on the complexity of the data, that is also you would require. And for certain instances, you might prefer to have to keep it general also. You can have multiple neurons in the output layer also. Okay. So there could be this goes on and on here in this direction here, and number of hidden layers also could go there, and finally your output layer can have multiple things. That is what your multi-neuron model is. Any questions? Any doubts so far? Okay. Yeah.
0 1 is also this, but somehow it will the line there in y1 y2 like it will divide.
No, if it is negative, you just assign it to 0 and 1. You can take whatever you want. 1, 2 also it can take. It's just some illustration. That is not the fixed numbers we need to consider.
These tables are y1 y2 y. The fourth case 0 1.
Very good, very good. Anyone has any answer for that? What he is asking is, what happened to 0 1 missing? Okay, he has put a missing poster there, missing 0 1. Can you give me an interpretation for 0 1? What is this case here? So y1 is 0, that means what? See, that means this side or that side? It is this side, and on the other side this line is, the other one is this, so there is no overlap here. So there will be, it only helped you to get a linear classification, otherwise this could not have happened. For a different way of drawing that could be possible also, having lines in different orientations. So if you consider the width, this also, this happened to be a square like here, just because I consider 2, 3 neurons will be cube, 4 you will have hypercube, and there will be always some missing vertices of the hypercube which are not feasible because the way the lines are there. Is that answering the question? Very good. That is a very important point. It is not like you get all combinations here and this will never be solved then. Okay, is that clear? Good. Of course, it could be also solved for some configurations, but there are some hypothetical nodes which does not exist for those lines or hyperplanes.
In that case, maybe increasing the number of layers.
Correct, correct. Increasing the number of layers as well as increasing the number of nodes in each layer also, right? And then there are, then you will study a lot of material where theoretically telling you what should be the limit of number of nodes in each one, number of layers, so on and so forth, but could not really, yeah, you may go through that. I will leave you there at that point. Okay, coming back here, what is the problem here that we have not yet addressed here? Right, finding weights, you will not directly get those lines looking the data, you are using some 1000 features, you can't even get a visualization there. Earlier things were nice, your calculation is, you have an error, just there is one thing here, you have an error, you are manipulating or modifying or updating the weights. Now, where do you know error in this whole stuff? So, to know the error, there should, at that point you should know also what is the expected outcome. Where do you know in the whole thing? Only at the output you know this, nowhere else. So, this information now from here you need to back propagate, okay, till the first hidden layer you have to do, that is where the back propagation comes into picture. Suppose if you have, you can, as I said, even in the output layer you could have multiple things, y1, y2 might be there for some reason, or for now just consider one, that also is good enough. So, here you define some j of w bar, again earlier there is only w bar, there were around, I think we took around 7 lectures, if you just go through my thing, we were talking about 2 classes on this, whatever covered so far is in first 4 classes, and then we, of course, we skipped now few things, and then this has a couple of classes, and the other one where some guidelines about the practical algorithms, choosing the weights and other things, you may go through that, but here I will still tell you few things here how you do that. You look at the misclassified voxels there and you compute the derivatives from here. Again, earlier this step also we did not bother much about. You look at this whole thing here, while you propagate weights, you want to update weights, output is not exactly, there is one more step here for which also you need to find out the derivative there to back propagate the stuff there. So, that is why you can't consider that del x into your g of x bar also will not be done, because you need to find out derivatives there. That is why you take a smoothed versions of your activation function. So, which would be like, for example, if you call it as f of x bar if you do not want me use f of g of x bar or whatever, is f of, let me write f of x bar only for right now. It will be like 1 by 1 plus exponent. What is the input to it? Is it a scalar or vector to this function? Activation function input is a scalar or vector? For the activation function, it's a scalar. See, output here at the end of your summation itself is a scalar. Okay, so this was a mistake from my end. So this should be, let me write simply f of x 1 by 1 plus exponential of minus ax if you take it, so that you can later take derivatives and propagate that error, distribute that error to every other node there based on this error. For example, this f dash x will be a into f of x into 1 minus f of x, you can work it out. So that also you will use. Now so you have to take it in 2 levels here. So I will not go, in the interest of time, will not go into the details of back propagation, but please do go through it since you have been already listening now for 1 hour 15 minutes almost. So I will not, I don't want to put that, but that is how you do the back propagation, and you will keep updating the weights there. That is the multi-layer neuron model. Or any questions or comments here? Is that fine? Hope you got some intuition, but again, if you want to implement it practically, you still need to understand the back propagation thoroughly. So please do go through that later. It will be now too much of a thing. I will just maybe add a slightly different point and then I will conclude. As one of you were mentioning, suppose when I have data like this, let us say I have some data here, I mean same thing will be applicable to multi neuron case also. I have data here. The way we have defined our loss function will converge for any of these lines, any of these except this. Okay, too recklessly I had run it. This is okay. I will just erase that. Okay, it will converge to any of these things. Will make your loss function 0 during your training. Which one should you select now? What should be the criteria for that now? Like, see, do you still remember how we have defined our loss function? How did we define? When will the loss function become 0? Right, the moment the misclassified voxels are 0 here, you will stop there, it will not converge. But practically if I ask you, okay, I will draw one more one so that you all will tell the same thing. Okay, if I draw you this, out of this which one do you select? Obviously the last one would you select. Why don't you select this one? So what? Right, from the training, you are right. From the training, this might be the case, but later when the real samples would come, it is better you keep equal distance from both. Okay, it is like you are sitting in a bus, so you better sit it if the all seats are vacant, you better sit there so that you may have free seats next to you. You don't sit assuming that the only where one seat next to you is vacant. In similar lines, because of the training data that you have or bias in that or the completeness of your training data, you would figure out something, okay, which you take the Euclidean distance from each of those points, for example, and do it such a way that the maximum of these Euclidean or minimum of these Euclidean distances is maximum. Okay, it looks like a twisting word, minimum and maximum, but you pay attention, you think about that. The minimum of Euclidean distances, if you can, you take this case, this line. Okay, what is the minimum of Euclidean distance? Maybe this. I have taken this line. This is the minimum Euclidean distance. You take a line which is middle. Why I am saying minimum of Euclidean distance? Because minimum, when I say it, you take all samples into account and compute the Euclidean distances and you take what is minimum there. Now for a line which is at the center, if you take minimum of Euclidean distances among all these lines, that will have the maximum of that. That is why you go for it. And what does the method that does this for you, which is the class of methods that does it for you? Right, SVM does that. Support vector machines will help you in doing that. So, that also you may again in lectures also support vector machines are there, you can go through that. Okay. So, just to summarize what we have discussed for roughly last 1.5 hours is we have looked at the problem of supervised learning, that is where we restricted ourselves to, and then we tried to get some intuition. Suppose there is a linear plane separating it, how different things are related. If the condition that we are keeping is the discriminant function g of x bar you are computing for this will be 0, then we have seen that this on one side if it will be negative for samples, on another side it will be positive. The measure of this g of x bar for any sample, if you give, it will give you a measure of Euclidean distance to that decision plane. The weights will be perpendicular to that. These are all the insights that we have got in the beginning. We have got its relation, some we compared to an extent with Bayesian classification also. Then we figured out how to solve this problem itself. So, we have come up with the loss function to do that. We have done this W bar transpose x bar W naught, and then we have seen how to use that to update the weights, right. And then we have seen the diagram for it, the linear classifier, a single neuron model that represents that. And after that, what if it is still you need not just one linear line to get clusters of different classes, but multiple things, right. And then how this is, by the way, the first one, this problem in computer science is, what is this problem that I have drawn there? XR problem. Okay. So, I just gave some better shape, I hope, to the XR problem 0 0 instead of keeping that. So, this is exactly XR problem that textbooks will be talking about. Okay. So, that is what we have done, and then we have drawn the equivalent multi-neuron model there, and we have seen, at least although we have not gone through it, how should we find out the weights now. You need to find out weights for all the neurons here, where you know only the output, you know the expected output only at the output neuron, you need to back propagate things. You have seen about also the activation function and integrator, that is how you separated them. Okay. If there are no questions, I will stop here without depriving you for your tea and biscuits, and today I think high tea is also there, so you will you will scold me more if that is missed, so I will stop here. Okay. Yeah. Thank you.
Thank you for providing deep insights into supervised learning. Let's have a break and get refreshed for our next session. Next session starts at 11:15 exactly.
Thank you. Thank you, Sumant. Yeah, good morning to all. So, to take you to deep learning or to go to deep learning, let me quickly spend a little time on backpropagation in neural networks. I tentatively plan for 10 to 15 minutes to spend on the neural networks. I will not go into the details, full details of backpropagation. I assume that you might have seen or studied sometime somewhere and you know partial details or you know full details. I will only try to bring in the notation and want to have a connectivity for the next discussion on convolutional neural networks. I would like to bring in some insights while I discuss on convolutional neural networks from the neural networks. So, that is the reason why I am discussing the neural networks backpropagation a little bit. So, I will put 15 minutes for it. After that 15 minutes I would like to spend on what is the need of what is this convolutional neural networks. Okay, what is the need of when you have already neural networks, why do you need some other learning method like convolutional neural network. Okay, another half an hour tentatively I will put on discussing what convolutional neural networks are and how they can be trained or how they can be applied in basic classification task. So, this is the tentative timeline of my discussion. So, let us anyway get into the feed forward neural network. So, as in the previous talk you have seen, the notation of neural network may be slightly different, but I hope you will be able to understand. So, what is that I am drawing here? So, I am putting some zeros. What are these things? Neurons. Okay, you can consider them as neurons or nodes. Okay, and we have the interconnections in a neural network. How will be the interconnection in a feed forward neural network? Input to hidden layer neurons, all input neurons to all hidden layer neurons. Okay, so this is that's why the name has come as feed forward neural network. Okay, so this is feed forward neural network. Fine, we are feeding all neurons to the next layer. So, all will have connections. So, if I do like that, if I have, say for example, I will bring in some notation, xi is the input here, okay, and say x1, x2 and so on up to xd are inputs. So, essentially the vector x is the input. What is this vector x? In a practical scenario, when we want to when we want to put a sample as input to a neural network, what is the x? Input feature vector of what? Of the given data. Given data is not very clear. Of given data sample. Okay, can you give an example? Say if I want to do digit classification, let us take the simpler example or known example, digit classification, okay, 3, 5, 1, 2 and so on. We give a 2D matrix of the image of the digit as input to the neural network. That is what we want to do. And the output what we expect is, see if I give as 3 as input here, what I expect at the output? Output how many neurons will be there? For a digit classification from 0 to 9 digits, how many output classes will be there? 10 classes will be there. So, 10 output neurons will be there. So, how do I decide the number of output neurons is based on the number of classes, right? And how many input neurons should I put for this classification problem? So, assume that this is 20 cross 20 image. Okay, I have an image of handwritten, you know, we have the handwritten digits, right? I take a small image of it. That image is 20 cross 20 pixels. Okay, I want to put directly that image in one dimension. I will just put the raster scan of that image and put in one dimension as a vector to the input. So, how many neurons has to be there at the input? 400 cross 1. So, essentially 400 cross 1 or whatever, this depends upon what? The input number of neurons depends upon the number of features. Okay, this depends upon the number of features I have for the sample, for each sample. Okay, and then this the output depends upon the number of classes. And how many, say assume that, say I just for generality, I assume that there are D neurons, input neurons, okay, and then there are H hidden neurons, and then there are C output neurons. Okay, this is the the generality. I am giving some symbols for it. So now how many interconnections will be there? So in a feed forward neural network, how many interconnections from this input layer to the hidden layer? D by H, of course, we can call D by H, it is D cross H or D into H, okay, DH essentially. So if I have 400 and 100 here, I will be having 4 into 10 power 4 interconnections. What do I mean by interconnections? These interconnections are what does these interconnection carry? Weights. Okay, so Wji will connect, for example, any of these, if I consider this as Wji in general, it connects Xi to Yj. Okay, let it be, I have given a general notation, but we can, Yj can be 1, 2 and so on. Okay. Similarly, Xi can be I, X1, X2, anything. So the weight Wji connects the ith input neuron to the jth output or hidden neuron, jth hidden neuron. Is this fine? And then this, how many you said D cross H? This is the, if I want to represent as a matrix W1, okay, one matrix, W1 matrix, whose elements are Wji, okay, then how many elements this matrix has? How many elements, what is the dimension of this matrix W1? D cross H matrix. Is this D cross H? So Wji I have put. So essentially what I am doing, this is H cross D matrix. Okay, because see, if I can put in either way, but I have given this side and J I have given to this side. So if essentially Y I have put in this way is, see, if I want to write in vector form, how do I want to write? What is this vector Y? Y1, Y2, Y3 all together. Okay, all hidden on neuron outputs is Y. Okay, and then this W matrix I will try to use, and then what I have input as X. W into X essentially, okay, is supposed to give me Y with, if I consider an activation function F, this is what is the relation between Y and X. Is this clear? Okay, so only thing here is I have not considered explicitly bias. Okay, of course you can absorb the bias in the X vector as you have seen in the previous lectures. Okay, so we are not explicitly putting it. Of course it is needed in general. Okay, bias is also there in general, but we are not explicitly highlighting or putting that. Okay, so that's the reason we usually consider its dimension to be H cross D. Okay, is this fine? Right? So now each of the input neurons are connected to the hidden neurons, fine. Okay, and then each of the hidden neurons are connected to output neurons. Now how many interconnections do you will you have here? Will we have here? Wkj I denote, okay, the matrix W2 here, okay, with elements Wkj, and how many interconnections do we have? C cross H, very good. And the matrix W2 will be C cross H. Okay, like we have made the J again this side, okay, not on that side, fine. J comes to the, in some sense it's on the rows, not on the columns, okay, fine. So now this is same, if I want to create output O, if I consider here as the output, okay, O is equal to what? In this similar fashion I can write O as what? O as W2 into G, of course I can consider G, or F itself I can consider, assuming that the activation functions are same. So W2 into Y, very good, okay, into Y, fine. So what is now there are a few questions quickly we will ask, and then we will move on to the idea on back propagation. Okay, so why do we need nonlinearity? Say if I am writing an activation function and so on. Okay, previously you have seen in a binary classification problem, okay, where you want to classify the samples of one class and other class. Okay, finally you ended up with a linear line, W transpose X plus B equal to 0. Okay, and this side, one side is positive, other side is negative, and so on. Okay, so there is no nonlinearity here, and the model essentially is trying to find out W and B, and hence okay, a neuron typically does not need a nonlinearity. But why do we need nonlinearity in a neural network? Why do we need nonlinearity? Quick answer? We do not need nonlinearity? Yeah, we need. Why do we need? Huh? Okay, very good. One answer is decision boundaries are complex. So, I assume in some way, okay, your answer I assume that, okay, the samples are like this. Okay, I can draw any crazy location of samples. Once I make this, this decision boundary can also be like this. So, for this to bring in, you have to have nonlinearity somewhere, okay, and you need to have it. Very good. Any other answers? XR problem, for example, does not have nonlinear decision boundaries, two linear decision boundaries it has. Okay. The one thing is, if I put all of them linear, finally what will boil down to? After a couple of linear operations, okay, I will keep writing one linear operation, on the top of it another linear operation, and the top of it other linear operation. Okay, what will finally boil down to the relation between input and output? Will be a linear operation, nothing else. So, I can't have the complete, if I knock off all nonlinearities, I can only get linear decision boundaries. Okay, and that too a single linear decision boundary, which will not enable us to essentially bring in the nonlinear decision boundaries or nonlinearly separable samples to separate. Okay, what do we mean by nonlinearly separable samples? Are not linearly separable samples are like XR problem, okay, which are not separated by a linear line. Okay, so fine. So, given all this, now we have some relation between output and the, see, if I want to relate now output and the input, I can use these two together, fine. Now the question is, as we discussed, what is learning happening here, what are to be learnt here, what do we want to learn here? It is fine, you have actually input features, okay, presented, output class values you are getting, okay, and then W somehow I initialize, assume that I initialize randomly, and then what do we want to learn here? Why do we want to learn weights? Why do we want to learn weights? Okay, if I do not learn it, okay, then if I give 3 here, do you expect that the for third neuron, okay, which is supposed to be high, say that class 3 should be 1 for third neuron, okay, ideally, and other neurons should be giving 0, 0, okay, the 0, 1, 2, 3, 4, 5 and so on, okay, this has to give high value compared to other values in the output, okay, that is how it should be if it is well trained, okay, if I give 3 as input, it has to give high value to the third neuron, if I give 2 as input, it has to give high value to the second, okay, the third neuron here, okay, if I give 0 as input, first neuron it has to give high value, if I randomly initialize and start using it, will that happen? Will that give a high value for a 0, if I give 0 as input here, do you expect that the 0th neuron always get a high value? It will not happen. So, I have to learn these weights and biases such that for each of the correct some class sample, I will get the corresponding label as high value here, or corresponding probability or corresponding output as high value compared to other outputs. Okay? So, for that reason learning is necessary. So, the predicted values of the outputs has to match with the target values of the outputs, right. So, these are assumed that the target values of the outputs, that is given by T, okay, I am just denoting this vector, okay, output vector as T. Now, given all this, so what, how, see, if they may not match, as we said, if we do not train it, but to train it we need some, what do we need? If we want to train it, what do we need? We need loss function. So, what is the loss function? Say if I randomly initialize and give a some input, okay, keep giving inputs, I will not get the expected output. What is the discrepancy between the actual output, okay, target output I want to get, and the obtained output by the network? This discrepancy over all samples, in fact, I am not considering all samples, currently we are just considering one sample, okay, all samples, this discrepancy is the cost function, okay. fine. Now the question is what this cost function is function of, what is that I want to do from this cost function? From this cost function what do we want to do? What do we want to do from this cost function? We want to minimize loss, okay, with respect to what? With respect to all the weight parameters. So W1 and W2. When I write W1, W2, these are matrices. Okay, explicitly writing dou of Wij, sorry, Ji and Wjk. Okay, Kj. Okay, with respect to all elements of weights, okay, I want to minimize this. Where are this Wji, Wkj and so on in this loss function? They have to be this side also somewhere, right? Where are they? In O. Okay, O if I want to expand, it is in fact W2 times Y. Okay, I can write like this. Of course, I can also write this as W2 Y, oh sorry, another f of W1 x. Okay, of course, I can also write in this way. I have left the biases and so on separately. We assume that everything is absorbed in this. Okay. So, now if I W1 and W2. Okay. So, now what we want to do is we want to learn the weights such that, how should we want to learn the weights? Such that the error discrepancy between the target values and the predicted values output of the network. Where is the network here? This itself is the network. Okay, network means it doesn't appear as network there, it is just a function. Okay. So, the output of this minus the target values has to be as minimum as possible, or they have to be as close as possible. Fine. So, now to do that what should we do? With respect, we should learn these weights such that this is less. So, what should we do now? What is the next step? We have to do back propagation, or what is that back propagation means? Adjusting the weights. So, essentially what I want to do is dou j by dou W2 for example. First I want to adjust these weights, okay, because these weights are near to the loss function. Okay, loss, see this whole network, it may have, as we have seen here, 400 input neurons and 100 output neurons. If we say 40,000 weight elements are here, okay, and then if I put 100 neurons here, 100 neurons and 10 neurons here, 1000 elements are here, weight elements are here. I need to set or adjust these many weight elements I need to adjust these many weight elements just by what? I need to adjust these many weight elements using what clue? Using the error between the expected output and the actual output. Okay, but see, is that do you think is it realistic? It is not realistic. So, what should I do now? I should look for, say I have presented 3 now and I have got some error, and with that error I want to adjust. Okay, what should I, to adjust these many parameters, what should I look for now? More 3s, okay, more 5s, more 0s and more 1s, is it not? We should have more number of samples such that they generally describe how all 0s are, how all 1s are, how all 2s are and so on, and also how all 1s are different from all 0s, how all 1s are different from all 5s and so on. Okay, so we need to have large data set usually for training the neural network. Okay, so usually the number of parameters of a neural network, if we consider as whatever the total number of parameters, they are referred to as expressive power of the network. At least 10 times of the number of the parameters of this are the number of samples that are required to train a neural network. Okay. So, now I will not get into the back propagation or deep derivative here. Of course, you can directly do derivative with respect to matrix and do that. Okay. I will give the answer. Okay. For this, those who have seen before, try to relate it with something that you have seen. So, assume I will tell some hints. See, assume that the I want to write error here, j is okay t minus o or o minus t whole square. See, as we said, we want to find out here dou j by dou w2 okay kj. Okay, this is what we want to find, is it not? Each element, how much does it vary? Okay, if I change small value in weight, how much does it affect the loss function? That is what I want to see. Okay, after seeing that, what do I do with this value? Dou j by dou w2 kj, I assume that I have got. After getting this, what do you think I will do with this? Update what? W2 kj itself, using this value, how much does it affect the loss function I will take and use this to update the W2 kj itself, okay, from the previous value to the next value, okay, and then eta times or whatever dou j by dou w kj. If it influences more, then I have to update it appropriately or more, okay. If it does not influence more, I need not update it, it is fine, okay. So, like that we do that, fine. Now, the question is dou j by dou w kj I have to get here. So, if I want to see how much the change happens because of this, first I have to see here itself dou j by dou o, okay, because there is an error. See, error is related to output and output is related to what? Okay, W2 anyway, W2 y. So, output is related to W2 and so on. Okay, so if I want to see the variation of this, I have to see first the variation with respect to this and then I have to see that, fine. So, now dou j by dou o, what is this? Anybody who knows can quickly tell? If I have j equal to t minus o norm, what is dou j by dou o? J I can also write as t minus o transpose into t minus o, okay, and then if I differentiate this x transpose x with respect to x, okay, what is that I get? 2 into t minus o, very good, okay, I take it, okay, 2 into t minus 4, this I write it as delta o, that, of course, this I write it as delta o, that is fine, okay. So, this I assume that you can probably understand, and from here then what I should do? See, but I have only used the first expression now, I have to use the now second expression and write what? Using the second expression I have to write what now? Okay, dou, I have to write what? Dou o by dou w. While writing here I will play a trick, okay. I will not write for all elements, o itself is a vector because o is o1, o2, o3 up to 10 values are there, 10 outputs, but I will just take only kth one, okay, and then r some one, ith one I will take, okay, or pth one I take, okay, and then jk, wkj I will take, okay. So, only one of the output I am taking, fine, and then one connection I am taking, okay, dou op by dou w kj I am taking. This if I want to write, how much will this value will be? Can anyone tell? Say dou o by dou w kj I want to do. How much will this value will be? This is the relation. How does it depend? See, I will tell intuitively. I am trying to find out, see, O2. Okay, with respect to O2, I am trying to find out the differentiation of W. This is 2, 1. Okay, that is actually 1, 1, 1, 2. Okay, so there is a connection that connects the second neuron here to the first neuron here. Okay, but there is a second output here. I want to see if I make a differentiation of dou o by dou w 1, 2. That means if I make a change here, how much does it affect this? I want to see how much does it affect. If I make a change in this weight, how much does it affect this output? It won't affect, okay, because 0 it affects, because this is not connected at all. How does it affect? So, this is equal to, ideally say this I will write, this is equal to 0 if what? If where P is not equal to what? P is not equal to, P is the here not equal to, P is not equal to K, okay, because K is this one. Okay, if these two are not equal, okay, it is connecting to some other output and I am trying to differentiate with respect to another output. It will be 0, okay, 0 if P is not equal to K, fine. If P equal to K now, what is the answer? If P equal to K, it's second condition. If P is equal to K, what is the answer? Now assume that I take another connection, okay, which is something like this connection itself, W3, 2, 3. Okay, this is the connection I take, okay, and what is the output here? Y2 is output, Y3 is output here, and O2 is output, Y3 is the hidden neuron output, okay, and O2 is the output neuron output. So now I want to how much does it influence this? Simply I want to use the direct relation O2 if I want to see only with respect to all Y's here. It is, okay, how do I write? So if those who have seen in matrix in element wise writing, O2 is only if I want to write, O2 only if I want to write, how do I write? Kj, Yj, j equal to 1 to whatever h. All of these will get added here, right? All these will get added here. So y1 into w21 plus y2 into w22 plus y3 into w23 plus and so on will come. Okay, this is what I will get. Okay, so now of course f is there, activation function is there. Okay, activation function is there. Now leave the activation function for time being. If I O2 by W, so dou O2 by dou Y3 if I want to do, what is the answer I get? Or dou O2 by dou Yj if I do, what is the answer I get? Dou O2 by dou Yj. If I differentiate, see there is a function, if you are not able to see there, okay, the function is OK, okay, in general is summation Wkj Yj. I am leaving the bias and all, okay, assuming that you can absorb them. J equal to 1 to h. Okay, dou OK by dou Yj I want to do. Okay, what do you think is the answer? I have written very clearly here, okay, the only relation, and what is dou OK by dou Yj? Wkj. And in case if there is an activation function, what will happen? That also has to be taken into account. So f activation function, if f is the activation function, somewhere f dash also will come into the picture. Okay, f dash of whatever. So if I call this as net k, okay, this value as net k, f dash of net k also comes into the picture. Okay, because if I differentiate any say function f of x, if I differentiate, what is the differential of f of x? F dash also will be there. Okay, f of x square, if I want to differentiate with respect to x, what do I write? F dash of x square into 2x. Okay, so whatever differential I have into f dash. Okay, so is this clear? So now just to give you an intuition finally, if p equal to k, what should I get now? It is essentially f dash of net k, okay, that I have written there, into net p here, okay, into what? Not y, I am differentiating with respect to w, right? Oh, here I have differentiated with respect to y. If I differentiate with respect to wkj, what do I get? Y, okay, okay, by dou wkj, if I differentiate, what do I get? In this, without f and so on, to make our job simple, yj I get. Okay, if I differentiate summation wkj, okay, with respect to the wkj, what I get is yj, right? So now simply this is equal to what? Into yj. That's all. So what finally I will write here, I will just so dou OP by dou wkj, okay, if you want to write, it is 0 if, when it is 0, p not equal to k, and what is the value? It is f dash of net p, okay, net p or net k is same, into yj, okay, otherwise. W I am differentiating, so yj will come here, okay, is this clear or not? So this I call it as, okay, so this I call it as delta net k, okay, net k or net p same, okay, net k or net p. So I essentially, where k equal to p, right, so it is same, net k or net p, okay. So now what I want to bring in it here is, if I want to write dou j by dou net k here, so essentially what do I have? The Okay. See, one thing to note here is, what I have written is, I have written the dou z by dou O, I have separated dou z by dou W into two components. One thing is dou j by dou O, okay, and other component is what? Dou z by dou O, which is already computed here, into dou O by dou W2 Kz. Okay. So, whatever I have computed here is what? Second one. Okay. We also have the other component dou z by dou O computed here. So, essentially if I write this, what will happen is, this is delta net K, okay, into, so what you have actually, delta net K, or what, we will write the whole thing. I will write here, I am erasing and writing, because the last expression I want to use for giving some hint. So, dou z by dou W2 Kz, now if I write together, what will happen? F dash of net K, okay, because K is here, net K will come here, okay, into what? Yj into OK minus Tk. Why I have written OK minus Tk? Because only I am taking the kjth element, I am not taking all elements of O, I am only taking OK, okay, essentially I am taking K only, okay. So, this is the final answer I get, right. This answer you can verify yourself with your previous workings or with the detailed lectures, okay. This I can rewrite as, see how do I rewrite it as, delta net K into Yj. Okay, you may ask me what is the advantage of writing, because there are K terms, these two are K terms, this is J term, okay. If I write like that, what do I interpret this as? See, if I want to adjust Wkj, that is delta Wkj if I want to find, essentially what I am looking at is, Yj is what? The corresponding input here, okay, Yj is the corresponding input here, right, and what is this delta net K? Here, see this value here, if I differentiate this further, O minus T you have got up to here. If I just cross the differentiation of F, see forward operation of this neuron, what it does do? After doing summation and all, it will apply F of, okay, it will apply an activation function. In forward pass, it will apply an activation function. If I want to go back, reverse pass, what I am doing here, F dash is coming into picture. So, if I see here for this delta, OK, essentially what it is happening this side, okay, not this side, okay, O minus OK minus Tk into F dash net K or net K. If I write net value is, what is the value before activation, okay. So, what I am trying to say is, the error that it back propagates up to up to this side of the neuron is delta net K, okay. So, that see if I want to update a error of any element, what I should look for is, I have to take the input here and take the error here, multiply them to update the element, weight element. This is delta net K into Yj, okay. So, this happens not only at this layer, this happens at all the layers. So, hope you understand the main point I am trying to tell. If you just keep back propagating, you back propagate the error. If you want to update any weight element, then you need to look for what is the input for it and what is the error at this end. Just multiply both of them, you will get the weight update. That is all you need to do. Is this clear? So, because why I have written delta net K here, delta net K is nothing but, okay, O minus T into F dash net K. O minus T is here, F dash net K comes because I am crossing the F in this direction, okay. If I am going in this direction, F of I will apply. If I come in this direction, that means back propagating, F dash will come. So, delta net K is nothing but, okay, F dash net K, okay, net value means up to here what the value is, into O minus T, that is all, okay. This is delta net K. So, if I want to update error, if I want to update any weight element, just look what is the error here, okay, from the end, okay, what is the contribution of delta dose A by dou this value, okay, dou net value, and multiply that with respect to the input, that is all, okay. So, if I want to update now any of this element, this I call it as Wji, assume that, okay. I will not derive anything, I want to write dou delta Wji, that means I want to see dose A by, okay, dou Wji is how much, I just want to see, okay. How do I see that? Can anyone tell me what is the simple way of doing it? Given this discussion, I just want to see now how do I update delta, how do I update the this Wji using this delta Wji, or how do I find delta Wji? What are the terms involved in delta Wji? There are two terms involved as I mentioned, okay. One term will be what? One term will be input. What is input here? X, xj or xi? Xi. So, input will be there surely xi, okay. And then what is the next term? Delta, yeah, delta net j. Where is net j? Before going here net j you have, and after going here yj you have, okay. If you cross this you have yj, okay. If you do not cross it, it is net j, okay. Yj equal to f of net j. So, simply you take the gradient here, okay, and then multiply with the input here, you get this weight update, fine. See, this kind of rule is applicable to any number of layers, not just 2 layers. If you have 100 layer network, there also if you want to update weights, what you need to see? In a 100 layer network, you need to take an error here and you have to pass 100 layers and then update. We can't keep on seeing what the chain rule and so on. What we will see? We try to see what is the error at the rear end and what is the input value, multiply them appropriately and get weight update. That is all. Okay, is this clear? How exactly we get delta net j or dose A by dou net j, that you bother about, okay, looking at the gradients, chain rule, all those things, okay, which you might have seen in other places or video lectures, okay, fine. Okay, so we will stop the discussion here and we will move on to the discussion on the convolutional neural networks. Yeah. Any questions so far on this? You can bring down. If you have any questions on this, you can ask. I have enough cluttered the board, but you can ask any question. I will probably put that separately. Yeah. So, what I would suggest is, if you want to understand and apply the neural networks, you take a 2-layer network, okay, put all the forward pass relations and write the output, how is it related to y, x and so on, okay, and then write the error, write the derivatives, okay, from j to o to net value here, net value to y value here, y value to net value here, net value to x value here, okay. So, derive yourself those derivatives and then put together to see these things or put together to understand or exactly get the details, okay, fine, okay. Okay. So, let us see what is the need of neural networks. So, convolutional neural networks. See, what do you think is any limitation of neural networks? That is the question now. Anyway, we, as we discussed, if you want to perform any automated task, we need to first start with some pre-processing, feature extraction and classification. So we have seen also that features are different for different kind of data, okay, and often it is not very easy to take the direct raw samples, either pixels or the signal values or any data values, okay, let it be binary or whatever, any values directly raw data itself as features. We need to usually, if you want to give it to any neural network, any classifier, we need to first extract some handcrafted features, then give them for classification, okay. So these we have seen, and computer vision field has evolved a lot in terms of what features are good to represent an image or objects in images, okay, and then the one of the very successful feature extractor is histogram of orientation gradients, which will take the gradients of an image and take the gradient angles and make a bins of them or histogram of them to represent the object shape, okay. So for humans all angles will be on 90 degrees, for example, if we consider as 0 degrees. So then you will have actually the human separately represented by dominated 90 degrees angles of the shape, and say if it is a horse, for example, it is dominated by 0 degrees, something like that. So that's widely used in computer vision, and this kind of handcrafted features are very much important if you want to perform classification by conventional machine learning methods. Let it be neural network, let it be support vector machine or any other method, okay. But the difficulty is for each data type you need, or each application also demands different kinds of features. Same features that I extract for a face detection may not work for a fish and non-fish classification, other fish classification. So what kind of features are more important is has been a important question. One observation in that lines is the features are extracted through convolution operation. As we mentioned in the previous discussion, say if I want to highlight the edges, what kind of filter do I use? I use an edge filter which looks like 1 1 1 minus 1 minus 1 kind of thing and convolve, and then I highlight edges. If I want to highlight corner points, then I design a filter like a corner which looks say 8 in the middle, okay, and minus 1 minus 1 minus 1 minus 1 in the all surrounding 3 cross 3, then that looks like a corner, right. So if I visualize it 8 in the peak and then minus 1s in the surrounding, that if I convolve with any object, any image, I see that the corners gets highlighted, okay. So for face, as we discussed, face filters, okay, can be there. So like that, if I design appropriate filter, I get better features enhanced. But the question now is, there is one parallel thought or parallel line of methods that are on investigating on feature extraction, and with filtering also you can do feature extraction with different filters, you can extract different features. On the other side, learning methods has evolved to learn directly for classification. If I give you features, we will be able to put into the separate classes or find out the regression value and so on. So on one side, learning methods have evolved to map the input output relationship, okay, if I give features to the output. On the other side, what kind of features are we looking for is an important question, and filtering also is known to be a good answer for it. The question, the subsequent developments has looked at, can we have a combination of them? Can we have these filters itself, can they be learned in a process, and then can we extract features also without handcrafting the features or without picking up some features, and also train the feature extraction stage as well as classification stage? The answer to this is convolution neural networks, okay. So this is one importance of convolution neural networks. The other thing is, see, when I give any image to the network, what do? I will make one dimensional vector and give it to the network. When I make it one dimensional, there will be some problems, okay, we will see that. So these details I am skipping now. This is what actually we have derived just now, okay, this is the whole expressions, okay, and then when you see finally what will happen, the weight update here is equal to the delta net here and the input value here, okay. So in vector form also it nicely fits in. Similarly even in next layer, okay, if you go also the output input vector here, okay, multiplied by the error here, we will put into the delta here. Okay, so you can see that later. And what essentially neural networks learns in this process is, if you have an input sample here and if you have output variables here, if you see mapping from input to the output directly, then if you bring in this any W that it learns to give a high response for a particular class, that W itself looks like a object of that class. Say for example, if I give a car image here and if I am getting a with very well trained neural network, I am getting high value for a car here. If I see the weights connecting all inputs to the class of car here, okay, that weights, if I put those weights, okay, in 2 dimensions, that itself also looks like a car. Okay. So what essentially it is extracting is that W filter. Okay, if I consider even W as a filter, that W filter that matches very well with the all input samples. Okay. So if I have all cars, assume that if I have a some average or unique representation of all cars, okay, that itself is what is being learnt as W here. Okay, if I want to see as mapping between input and output. So now the question is, how do we learn that such filter directly? Okay, without this is of course learnt in even in feed forward neural network or even in conventional neural network, but the problem is the ability of it is limited because of few things, and how do we do better is the question. So one more problem for developing deep neural networks is, as we have seen, when we back propagate, what will happen? At each stage you will have one f dash, because each layer, if when you cross, there will be one f dash added here. Another layer if you cross, one more f dash added here. Okay, added multiplied here. Okay, so weight update, if you want to see after 10 layers, okay, it is function of all these many f dashes. Okay, weight update after 4 layers, if you want to see, these many f dash terms will be there along with other terms. Okay, each f dash value, if you consider sigmoid activation function, okay, f dash value is in sigmoid is in the range 0 to 1 and f dash of sigmoid is in the range 0 to 0.5 only. Okay, if that is the case, what will happen? These many, each of them multiplied by 0.5, 0.5, 0.5 because of f dash in 10 layers, then what will happen? The weight update dou A by dou W itself will be very small. So for that, usual answer that people have brought in is use an activation function called ReLU. What is ReLU activation function? Rectified linear unit activation function. What it does is, so instead of the sigmoid activation function, for f of net value sigmoid activation function, what it does is, it tries to map the input net values, okay, to something like this. Okay, so essentially it will try to map 0 to 1 here, then this is half here. Okay, this is what it is trying to map, net value to f of net value. Whereas sigmoid activation function, what it does is, this will have a small gradients. Sigmoid activation function, what it has is something like this. Okay, sorry, this is ReLU activation function. How it has is, net value it will map to, okay, net value itself on the positive side, okay, on the negative side it puts to 0. Because of this, what will happen? The gradient in negative side is 0, positive side is 1. So this, because of this, this f dash does not die down. So this is addressed, but the problem is, if we want to consider feed forward neural network and give a 2-dimensional input to the feed forward neural network, if you shift the image or the object by a small amount, then what will happen? Previously where you have learnt for A, okay, in other neurons is not there as A now. Okay, so previously whatever the neuron supposed to predict A now will not predict A. Okay, so if with small shifts, the input you give to instead of one neuron to some other neuron at all, completely different neuron. Okay, so this will bring in a difficulty in terms of learning. And even if rotate and so on, okay, what will happen? Okay, whichever you have learnt all A's with having high value for first 10 neurons. Okay, now after rotating, what will happen? They may be in next 10 neurons. So the if you bring 2 dimension to 1 dimension, the whatever you have learnt for some neurons will appear in some other neuron in testing, so they will fail. So the what we need to do is, we need to have a method that directly takes 2-dimensional input. So all these are being addressed by convolution neural networks. So what convolution neural networks does is to represent the if you have image, first let us extract some features. in 2 dimension itself. For extracting features in 2 dimensions, what do we know? What is the good operation to extract features in 2 dimensions? Filtering, convolution. So apply some convolution and get features, and these features can I assimilate together and make better features, high level features. Then let us put one more layer of convolution and see can we assimilate better, okay, and then put one more layer of convolution, can we assimilate even better. So what it tries to does is, it tries to extract the features layer by layer, low level features to high level features directly in 2 dimension or whatever the dimension of the data itself. If I have a RGB image, it is 3 dimensional, so X, Y and RGB, okay. So it can be directly given to a convolution neural network. No, there is no need to bring it to 1 dimension or 2 dimensions. So any data, let us try to bring in its own dimension and try to find out the features in that dimension itself through convolution operation, and can we assimilate them in a layered manner and get better features and classification as well. That is what is being addressed by convolution, done by convolution neural networks. I will skip the very basic details. The layer of the structure of convolution neural network looks like this. As I mentioned, the greatness or the famous reason for convolution neural networks being famous is it is very simple. Okay, it only has 2 building blocks, ideally speaking. Okay, one is convolution layer, as we mentioned, perform convolution, that is all. Only the question is which mask or which filter to use for convolution. If I want to find edges, I have to pick edge filter. But if I want to perform say cat, dog, person and so on, 1000 class classification, which filters to use is a big question. So it is answered by the learning method. I will learn the filters itself. Okay, what 3x3 filter should I use is also being learnt. Okay, so that is the convolution layer is first layer, and I can bring what how many features should I extract. Say edges are only features I want to describe an object. Corners also I need. Corners are and edges, only these 2 features I need. I also need texture features. I also need few other features. So bring several feature maps, not just one feature map. Okay, so each filter here will give one feature map. I can get actually 6 feature filters. If I use 6 feature maps, I will get. But these are only low level features. That means one step from the pixels. I have to get the high level features. I perform another filters, another set of 6 filters or 10 filters, okay, to get the next level of features. But if I keep applying filters like that, the dimension of the feature maps become more and more, okay, and then the number of filters I want to apply at different locations also, the computational complexity in applying filters is also high, because each convolution operation here, if you want to do convolution with a filter, where I have to place this filter? At all pixels I have to place, is it not? So if it is 100 cross 100, 100 cross 100 into those many operations I have to do for a single filter. If it is 5 cross 5 filter, 5 cross 5 into 100 cross 100, those many operations I have to do for just getting one convolution output. So I have to reduce somehow the computational complexity without compromising the requirement I have. So one layer, another layer that convolution neural network has is compactly representing this information in terms of pooling layer. Okay, pool the information. How should I pool? Put the maximum value in this block to the next layer. Let us leave the other things. Okay, that is referred to as max pooling. Or put the average value for each block and then go like that. Okay, that is average pooling. So essentially it has a convolution layer followed by a pooling layer. Okay, and again convolution layer because we want to extract high level features. Again pooling layer. Okay, this is essentially is done in convolution neural network. And finally, after doing all feature extraction, I have done enough learning for filters and feature extraction. After doing whole thing, what I need one dimensional representation because the number of classes are in one dimension. Okay, so I will take the one dimensional representation. I will do back propagation exactly in the way we have done here. Okay, slightly in different manner. So you can see here, this is the convolution neural network. It takes finally the features may be like this. Okay, each filter may extract features like this. Okay, one may extract horizontal, vertical, and then all lines and so on, circles, all those things. Okay, but this is the convolution operation. Hope you know convolution operation. I am not discussing or describing it. What we do is this is the kernel and this is the image. Wherever there is an overlap, in the overlapping region we will count how many are overlap. The overlapping region only we will multiply and add. So the value is 1 here. It is 0 here because there is no overlap at all. These are non-zero values. So here overlap is there, so it is value is 3. Okay, so it's like that. So convolution operation, hope you are aware. And then some of the important things, if you want to understand, mainly those who work in this convolutional networks want to understand the literature, you need to understand the dimensions from layer to layer, how much they will be, because in papers, if you want to design your own convolutional neural network, or in papers if you want to understand, there will be a table giving the convolution, how many filters they use, what is the dimension of filters and so on. Okay, so from that you need to understand what is the dimension of next map. So if you have 5 cross 5 or 6 cross 5 map here, 6 cross 6 map here, okay, if I apply a 3 cross 3 convolution, okay, I am considering such that whole convolution is within. That means I don't want to have the border effects, boundary effects. Okay, so I put the kernel completely inside. So then what will happen? It will only start here, it will end here. So what is the output value? Output is, okay, it is 5 cross 6, so it is 3 cross 4. Okay, so essentially it is H cross W means H minus F plus 1. Okay, F is the filter size. Okay, H minus F plus 1 or W minus F plus 1. That is the dimensions of this. Okay, that is how output dimensions are. So you should know how to calculate output dimensions. This you can see by convolution operation. Okay, calculating that. And sometimes what we do, we may not do convolution at all locations. We may take here and skip one value here and put kernel here, and again skip and put kernel here. If that is called stride. Okay, if I don't do convolution at all location, that means feature extraction I don't want to do at all locations. Okay, I want to do here. It's anyway done for this pixel now. I want to shift one pixel here and then take the feature extraction. It's not coarse feature extraction. It's okay, I sample here, features here and so on. Okay, with stride 2 and so on. In that case, stride gets divided while calculating the size. Such things you should probably understand. So this is the other thing is, see, whatever we have seen before is a 2-dimensional convolution. But usually what happens, from input image, I want to extract 6 feature maps. That means 6 kernels I used, 6 feature maps I have got. Now I don't have 2-dimensional image now. I have 3-dimensional feature maps now. Okay, H cross W cross C. Now 3-dimensional feature maps too, I want to get the another 3-dimensional feature map. How do I go about? There are already H cross W cross C, and I want to get another H cross. So I have, it's like H cross, okay, W cross C here, okay, and from here I want to get anyway I will write H dash cross W dash cross C dash. I want to get, okay, another feature maps. How do I get that? Then what I do is, the operation that I do is, I perform the convolution operation with a 3-dimensional kernel now. See, I will write this, okay, if I want to get the convolution output, say assume that we have image I, which is 3 dimensions. So I is 3 dimensions, assume that. So I will write K here, okay, I is A here, okay, because I is a convolution operation, you know well, I am not representing this, IK convolved with, okay, C kernel, right, K this Pi, right. See what this operation I am writing it is, see I assume that I is 2-dimension H cross W cross C, where C is represented by P variable. Okay, I have not represented H cross W because it is anyway 2-dimension. I am assuming that either 1-dimensional signal you write, right, usually, okay, H convolution, if y equal to X convolution with H, you people may be aware of this in signals and systems. Okay, we drop N for simplicity here. Okay, similar way I am dropping here spatial variables I and J. Okay, so IP is the pth map, okay, of the feature map. You can see that pth map is one of the map here. Okay, I am taking IP and convolving with what? Kp comma L. Okay, again K is also 2-dimension. Okay, so if I say that this is already I is 28 cross 28, okay, cross say whatever, so 6. Okay, then what I have here? P is what? 3 cross 3 filters if I am using. P is 3 cross 3 cross, okay, P is same here 6, okay, 6 I have, cross how many L I need? L equal to, say if I need 12 maps output, this is 12. Okay, this is the dimension. So what essentially I am doing is I am taking an input image, p channel of the input image, okay, and convolving with the p channel of kernel, and such L kernels I have, okay, and then this I sum over p because output is only Lth map I need, okay. So this is what I do usually in this process. See, this is the mathematical notation and this is the visualization. What is happening here? This filter is 4 cross 4 cross 3, okay, 4 cross 4 cross 3 is here, okay, this is what is this, okay, this is essentially is that, okay, 4 cross 4 cross 3. How many such filters I have, how many maps I need? If I need actually output 12 maps, okay, these kind of filters, how many filters should I have? 12 filters. See, if I, instead of 3 here, if I have 5, assume that 5 channels I have before, already I have 5 channels, then what will be the dimension of this, can you tell? 4 cross 4 cross 5, because I have to start with that 4 cross 4 cross 5, and if I need 8 here, then how many times I have to do this, how many W's will be there here, W1, W2 up to W8, okay, so like that. So that is how it happens. Essentially if you want to look it as number of input, so this is I1 and then IP, okay, and then these are the input channels if you consider, and the output C1, okay, and then CL if you consider like this, then what is essentially happening? It is roughly like a fully connected neural network, okay. So each is a channel now in 2 dimensions, okay. You can see the analogy between this operation and as well as the neural network, where each is a channel now, 2-dimensional channel, okay, fine. So you should know essentially if I have 6 maps to get to 12 maps, how many kernels, what is the size of the kernel? This is one more important element if you, when you design a neural network, convolutional neural network. So this is the other layer, as I mentioned. This layer what it does, it tries to do a compact representation of the image. See what as I mentioned, there are 2 layers. One layer is convolution layer, which will do feature extraction. The second layer is what? Second layer, other layer is in convolutional neural network is what? Pooling layer. What does pooling layer does? It tries to represent the same information in a compact way. That is only its job. So if A is like this, okay, and another A is like this. So for humans we can say that both are A's. For a machine it is very difficult to say these 2 are A's, same A's. But for machine it is easy to say that these 2 are same A's. Okay. So what do we do? It is unnecessary information to have at this resolution. Okay. What we do? We can do a downsampling or pooling, okay, or averaging, and represent in a compact way. That is done in another layer. So these 2 layers one after the other, go one after the other. So in a convolutional neural network, I will just skip the small details. Here see, this is a typical example of a convolutional neural network where we can apply the convolutional neural network for digit classification. This is referred to as LeNet model, okay, those who might have known before. So this is a very simple LeNet5 model where this is the digit is represented in 28 cross 28 image. Digit means 5, 6, whatever, or 28 cross 28 image. That image we will pass on 6 filters we use, 5 cross 5 or 3 cross 3 filters. Here 5 cross 5 filters. If I use 5 cross 5 filter with 28 cross 28 image, what is the output dimension size? 28 minus 5 plus 1. Okay, that will be equal to 24 cross 24. That is what we have. And again we have 6 channels because 6 filters I have used. And after that, okay, we have actually downsampling, because each channel if I downsample, how many will the number of channels change? If I have 6 channels, I downsample them again corresponding to the corresponding channels. Will the number of channels change? They does not change. So I have 6 channels compactly represented in 12 cross 12 now. I apply again 5 cross 5 filter here. If I apply 5 cross 5 filter, what is the next dimension? 12 minus 5 plus 1, that is 8 cross 8. Okay, again I apply compact representation representing in 8 cross 8 to 4 cross 4, and 4 cross 4 12 channels I have, I vectorize. So 192 cross 1, that I will connect to output 10 neurons. Okay, this is a simple architecture how a convolutional neural network looks. Okay, So, you can see that we will skip the details, some of the details. One of the important thing to know is how do I initialize these filters. See, as what did we mention, these filters, how do I see how many filters are there? Here 6 filters are there giving 6 maps. From here to here there are 6 maps here and then 12 maps here. How many filters are required? How many 5 cross 5 filters are required? 5 cross 5, 6 maps here and then 12 here. 5 cross 5 into 6 into 12. Okay. So, essentially 5 cross 5 if I look at 72 are required. Okay. But if I require 5 cross 6 only 12 are required. Okay. So, those many filters are required. How do I get those filters all length? I have to initialize something, right, with these filters. How do I know these filters? By learning. That means I have an error here, I try to back propagate and learn these filter values itself now. Okay, two dimensional W's I try to learn now, not just one dimensional W's we have done in a feed forward neural network. Okay. So, how do I do that? With some initialization and back propagation later for learning. How do I initialize? Usually we initialize by random initialization. So, usually there are some guidelines because the initialization also plays an important role. See, you are looking at the j function or cost function not in 1 or 2 variables. Okay, as we have seen in this example itself 10 power 6 variables, million variables. So, that obviously will become non-convex, okay, and it is very difficult to track where the local minima, global minima, anything of it. Okay, we can't visualize at all. So, that much higher dimensional space, we want to find some good W, okay, with all elements of W which is best suits for classification. So, we have to initialize also properly. So, initialization is done through random initialization, but however there are some guidelines for it. What is the range we should consider, negative to positive and so on. Okay, what is the range and so on. So, usually there are some Xavier initialization and so on which will tell that minus 1 by something to plus 1 by something, minus small positive to small negative to small positive. In that range we initialize. After that we need to back propagate. So, we have already discussed this, you have seen, right, how 6 maps to 12 maps, if you want to get how many filters are required. Okay. So, these many filters are required, each of 5 cross 5. Okay, 5 cross 5 required for 6 maps, 6 of them for getting 1 map here, like that. Okay. Again, no, for the next one, like that. So, this is the expression that exactly I have written there. Okay. So, except that the variable z is here and then some other variable there. Okay. So, now the question is the error, after this you have the error here, how do we back propagate? That is the next question. How do we back propagate the error? We will see a little bit, I will not get into the details again, but I will give you an idea. And this is exactly in the same way as we have done before. If you understand in a neural network how does the back propagation happens, understanding in convolutional neural network is not difficult. See, error you have here. So, error if you have, first find the gradient here, okay, O minus t or whatever, after find the gradient here and so on. If you have a convolutional neural network, if I want to update this weight element, okay, then what should I do? If I use my previous principle, what should I get? If I want to update this weight matrix here, what should I have? The forward process is convolution, okay. So, some other process may be there for convolution, but the weight update here depends upon error here, whatever I get up to here, and the input values here, that is all. Okay. So, if I want to update this input value x into something will come, error here. Okay. Same operation also happens here, but the major changes are because you are going forward with convolution operation, you back propagation, it turns out to be correlation operation. Okay. So, if you are moving through a activation function f, same f dash will come in the back propagation. Wherever you are doing downsampling, in the back propagation what will happen? If you are going in the forward direction by downsampling, if you want to bring the errors to the back, I have to do upsampling, that is all. Okay. So, with these small inputs, you can see that the error gets back propagated. Wherever forward downsampling is there, I do upsampling. Okay. Wherever the convolution is there, I do correlation, that is all, nothing else. Okay. So, there are some, if you want to get real inputs or key inputs on how convolution here becomes correlation there, okay, you have to wet yourself with a little bit of small examples. Okay, you can take in 2 dimension, okay, do convolution operation, get output, get the errors, and see how does the errors get back propagated. Try to see forward relationship and then try to see the reverse relationships, and then try to see, okay, how do you write this compactly. This finally compactly is written as I mentioned like this, okay, in the forward direction convolution means inverse reverse direction back correlation, that is all. Okay. So, it is not too difficult to see, but you have to see with small examples if you want to see. Okay. Similarly, it happens even for the weight update. Okay. So, finally, as I mentioned, if you want to update the weight, you have to see the errors in the output and the input, that is all. Okay. At any layer, if you want to update the weights, what you have to see, errors up to corresponding output and inputs. But you can't multiply here because forward operation is convolution, you have to do some other two dimensional operation which is correlation here. Okay. Flip of convolution is correlation. Okay. So, something like that. So, this is regarding the convolution neural networks. I will show small examples and then conclude in 5 minutes. So, here you can see how what kind of filters does it learn. You can see that actually, so this learns at different layers, different versions of 7, okay, and try to put it, and then based on it, it does classification. So, the kernels always we can't make much note of it, okay, but sometimes with some different way of visualization, the feature maps gives a better understanding of what is happening. It is not very easy to get the intuition on what exactly filters, are they edge filters, are they corner filters and all, but in some cases we can get. And the other thing that you can see is, even with if you train with a 3500 neurons, a feed forward neural network, you may get a maximum of 93% accuracy for digit classification on 60,000 samples and 10,000 samples for testing. But if you train a convolutional neural network of 5 layers, as I mentioned now, okay, we can easily get a accuracy above 96% with the same data. So, because as you have seen, we are not bringing 2-dimensional samples to 1 dimension, we are effect of shift, writing, all these things are taken care well, and learning is happening not just for the from the features, but also for the features to some extent. Okay. So, there are some examples that students have done. So, this is one example, they have applied for white blood cell and red blood cell segmentation and classification. So, initially segmentation is done, segmentation can be done through image processing applications. These are the white blood cells with stain, okay, and these are the red blood cells. Now, if you see actually we want to learn a convolutional network, give all the white blood cells and we want to put a malignant and benign class, okay, cancerous cells and non-cancerous cells. So, what do? We want to give some input. See, should we give directly the blood cell as the input, or do we want to give some little bit of better enhanced handcrafted features as the input? It is up to us. So, they have one of the students has extracted some handcrafted features and gave them as inputs. So, the kind of inputs are now we consider this as shallow features because we extract with without not much layers, right. There is a deep neural network we call because there are hundreds of layers. Okay. The number of layers where we learn these filters is referred to as the number of layers for a network. Okay. So, and this is more means it is deep network. Okay. So, it is not initially we give shallow features with some pixel differencing R minus G, G minus B and so on, also with some other kind of like with stain, without stain images and so on. Some different versions of the input handcrafted features are given as input. Okay. And then there are different networks that are parallelly trained to get actually extract different information. And this is a conventional practice in convolutional neural networks to extract better features. So, one network extracts some kind of features, other network other kind of features, we augment or stack all of them and finally give for computing the error at the output, and then from there the error and back propagate, learn all these things, all the three networks together. Okay. So, this has given a good improvement over the current methods of cancerous cells classification in terms of this blood cell classification. Of course, there are different ways in which the people explore in terms of in classification. See, should we use all samples? The answer may not be yes. You need not use all samples. Use very distinct samples, or you somehow have a mechanism to pick the diverse samples and give it to the network and train better. Okay, that there is a field called active learning. What they do is initially start with very small samples and try to see which are the samples which are difficult for this network to classify now. other samples and only label them, do not label all of them. Okay, try to find out the samples which are tough for current network and label them, use those samples to train this better, okay, like that. Then with that he is able to see that even with very small 50% of the samples, we are able to get the accuracies better than all 100% samples using, and so on. So the even computational complexity is reasonably less compared to ResNet 150 which he compared with, so on and so on. So there are some references I have put here. So if you want to follow deep learning for computer vision or visual representations, so I would recommend Professor Fifi Lee team video lectures, Stanford. So they are very good. So they have given very detailed lectures starting from how to the theory and then training and many other aspects. And they also have given different other resources there in terms of the papers and which papers to look for, and which even for projects there are some good hints there. I thank the students who have made these slides long back. Thank you. If you have any questions, you can ask now. No questions? Okay, thank you. You can ask me anytime. Anyway, you can be there here for a day. Thank you. We will try to give you slides, and probably you can also see the video lectures later, but you can also take. Sure, thank you.
Thank you, sir, for this wonderful lecture. So now it's a lunch break, so you can collect the coupons. The volunteers are waiting outside, so you can take the coupons and go for the lunch.
Just to add to that, after the lunch, there are two, like I'm sure you have seen the schedule, two by invited speakers things are there, so be there in time. Hope you will find them very useful. Yeah, see you.
So you can collect the coupons just from the volunteers.
to our next interesting session on deep learning for computer vision. I request Dr. Ramakrishna Gurti to take this forward.
Yeah, thank you. Yeah, thank you, Vamsi. Good afternoon to all. Let's continue our discussion of convolution neural networks. This is the application of convolution neural networks or development of convolution neural networks to computer vision methods. Usually, classification is one of the primary task in computer vision. Say if you want to be, as we discussed in the previous lectures, computer vision try to deal with the making inference from images or from videos. Yes. That PTZ camera alone is taking. Okay, so it will blend both of them. Okay, okay. Okay, thank you. Yeah, good afternoon to you all. Let's continue our discussion with the applications of convolution neural networks to computer vision. As we discussed before, computer vision deals with inferring from images or videos. So processing is not just enough. We would like to infer, means we would like to know how many persons are there, where the persons are, or what's happening in that scene. Let it be with persons or without persons. So what's the whatever is the inference we would like to do from images or from videos, how do we do it? So in some the primary task of inference is classification, one of the primary tasks of inference. Say where we want to, based on the images, we would like to classify, is it a cat image, dog image, person image, or so and so person image, is he the same person that we would like to detect or find. What is the probably classification also can deal with different kind of say digit recognition, iris recognition, biometrics and many other things. Of course, it has applications in many other domains, medical image classification, blood cells classification as we discussed, also cancerous, non-cancerous kind of classification of cells and in many other domains. But there are other important tasks in computer vision. This is referred to as semantic segmentation. Semantic segmentation means instead of labeling the whole image at once, can we label each pixel to one of the class? Say, can we say that this is belongs to background class? Can it belongs to a mountain class? Can we label each pixel of the cat to cat class and so on, grass class and so on. So this is referred to as pixel segmentation, pixel based classification or semantic segmentation. Okay, so we want to give the semantics to the image or the scene that we have. So this in this task, for example, how many number of labels are we would like to generate is equal to the number of pixels in that image. So unlike where you want to give one label for a whole image, it is like we would like to give the dimension of image is 100 cross 100, we would like to give the labels or the output also of 100 cross 100 dimension. Okay. So this is referred to as object detection, where on localization. Object detection essentially is to localize an object. So we are not interested or not enough to say that there is some object here. Where is that object is of interest. So at what xy locations it starts and what is the height and width of the object. This is one typical way of localizing an object. height, width and xy. So, 4 values we have to get from the image that we show. If you want to localize a single object, if you want to localize multiple objects, then we need to get more x, y, h and w's for each object one kind of. There is other task called instance segmentation, where we are not interested in background as we do in semantic segmentation. We are interested in the foreground objects. Say if I am particular only about humans, I just find the instances of humans where they are and try to give the instance segmentation on humans. So, like that, and each instance is different from other instance. So, as each human is different from other human, I would like to perform a task differently for different instances of that scene. So, that is done through instance segmentation. Of course, there is one more task called combining these two, background semantic segmentation and instance segmentation, referred to as panoptic segmentation. Sometimes I would like to give the single label for all background, but each instance I want to give different labels. Now, what we see is we try to see, we will see some of the architectures or development of the deep learning methods for performing these tasks. Of course, these tasks have been there since long, and computer vision has dealt long way in terms of developing methods for each of these tasks. But the deep learning from its introduction has shown tremendous improvement in terms of the performance to handle each of these tasks. So, assume that we now want to have a network based deep learning based solution or a convolution network based solution to classify, to make the instance segmentation of this image. What is the typical way of doing it? A very crude method if you want to do. Say each pixel I have to give one label, let it be a grass, cow, sky and so on. What should I do? I have a small network, assume that network I will put at every location and take a small patch and then give that patch to this network and try to label it, right. So, how many times then I have to apply this network? If I want to label each pixel here, if it is 100 cross 100, if this is 100 cross 100, how many times I have to send apply this network to make the labeling? 10,000 side, 100 cross 100, 10,000 times I have to apply. And in training also is like that. So, it is not very effective way, because the whole image has the, say I am putting a network here exactly at the next pixel. So, there is a commonness of information between these two pixels and I am not using effectively. And also the whole image can be given at one stretch if possible and get the labels at one stretch. Why to run it this for 10,000 times? Okay, so the developments headed towards that, and this is one development where we give the image and try to get the labels for all of them. The remarkable ability of this deep learning is that as we do not essentially fix the filters or extract the features handcrafted, we can learn the filters or the feature extraction stage also and perform the classification also, driven by the objective function or the cost function we have. So, if we develop the final cost function in such a way that we get the labels for each of the locations, then it is good enough to train this network. So, how this is referred to as a semantic segmentation network, a kind of one example of this is Signet. What they does is, we have 100 cross 100 image, we have at each location we provide the ground truth label. So, we have 100 cross 100 labels, 100 cross 100 predictions of the network. We see the error in this 100 cross 100 image label image, 200 label values to predict the actual values. These 100 cross, at each location we have an error value, right. We group together and then back propagate. So, the back propagation is done as we discussed in the morning, wherever which are dependent to this pixel output, they will be updated they will get the update from that error. So, it is the this is one possible provision to get the learning of a network to give directly pixels for all labels for all pixels. But the problem, there is one problem with this network. What do you think is that? The problem with this network is, see this is 100 cross 100, this is the filters are also 100 cross 100, okay, and then if I want 10 filters, okay, each of the filter has to be applied at each pixel, is it not? The computational complexity all through is 100 cross 100 into those many filters or dimension of the filters. So, it is very high. So, then the just after this the immediate developments are to see if can we reduce the dimensionality, the complexity and still get the labels at the image dimensions. So, what the idea is to use the structure like we have in CNNs to extract the features up to some level with the convolutions and downsamplings or subsamplings or poolings. Then what we have in this process, we have the compact representation of the information and extracted or encoded the information very well up to here, and we have actually a lightweight network to do that, or relatively lighter weight network to do that. After encoding, what we need to do, the encoded information is directly useful for classification, but not for pixel level segmentation. So, we have to bring back to the original image dimension to get the labels at each pixels. So, that is done through a decoder network. Just exact replica of this is usually used here in terms of the architecture. In terms of training, there are also some commonness that will leverage from here to here. But these two can also be independently, in sense that it can be trained in the way that upsampling to downsampling is done here. So, in training, downsampling to upsampling will happen for the gradients, whereas here it is upsampling to downsampling to upsampling is happening here. So, while training with the errors, we downsample the errors. So, same thing happens. So, there are different ways in which they upsample, because upsampling is not very, it is a ill-posed problem. So, upsample by just replicating, upsample by putting zeros, or upsampling by max pooling. If I do max pooling, for example, I take this 5 from here, okay, while I use the other, this is while downsampling. While upsampling, what I do, I will put this error whatever I have at this location, okay, I will put the remaining locations 0, because there is no propagation in the forward direction. So, some tricks like that are used while bringing the encoded information to the decoder, and then it is trained accordingly. So, the model that uses this is referred to as Signet, that has demonstrated good accuracies in terms of pixel level classification or segmentation, instance segmentation. There are other ways in which we can upsample. By there are methods to train the filters itself to upsample. So, like we are doing convolution from one convolution layer to other convolution. If we do with a stride of 2, for example, what is happening? Stride means we shift by 1 pixel and do convolution there. So, the dimension will be half, because we are shifting 1 pixel and doing convolution. Similarly, while doing upsampling also can done through a filters, the learnable filters. What do? Is they put the filter here, or bigger size filter here, exactly put at the next location, they tile them. So, in this way they can upsample as well through learnable filters. So, this is referred to as transpose convolution. The name transpose convolution comes because those who know convolution writing in matrix form can write it like this. Okay, those especially some kind of books specifically write or deal the convolution through matrix operation. That can be written in a with a transpose operation here. So, that is that's why it is referred to as transpose convolution. Here we learn the filter, say if we are learning this filter, in convolution we will be learning the other filter in the transpose convolution. So, there are a follow-up works on instance segmentation. The kind of works that are try to leverage from the computer vision community. See, if you want to extract good features for it, what we usually do is we see the signal or the image at multiple resolutions. At different resolutions, some of the different objects which gets highlighted or can be we can effectively extract their features. So, there are some methods that use the multi-resolution kind of framework in the deep learning. What they try to do is they extract the features, say they sample the either image and extract features at different resolutions of the image, or they sample the features extracted and try to infer from one resolution of the features to another resolution. So, this is conventionally used in computer vision, and these similar ideas are borrowed even in, are used even in the deep learning frameworks. The idea is at this resolution the bigger objects, bigger objects may look compact and fine. At this resolution even smaller objects may have their features retained. So, and while combining we effectively will have a effective procedure to blend them. And these usually give better accuracies in terms of the either segmentation or any other tasks as well, and these are recently also seen to be robust to some kind of attacks. That means if slightly perturb the neural network, will its results change drastically. So to such attacks as well, these are more robust. So this semantic segmentation is very well applied or demonstrated for cityscape scenarios. The one of the very important problem that many of the industries and researchers want to deal is on the segmentation of the cityscape or the street scenarios, where we would like to identify the cars, persons and so on very accurately. And this is useful for self-driving cars development and so on. This can also be applied in different fields. This is one application where it's shown to segment the roads and buildings. This is on some other natural scenes. This is brief about the segmentation methods. Now let us move on to discuss on the object detection methods. Conventional way of detecting object, say if I want to detect a cat or a dog or a person. Okay, what is usual way? If we do not know anything about say deep learning or even image processing, if somebody asks us to detect an object, a person here, what do we do? As we discussed in the previous discussion, if we want to detect face for example, we try to see the template for face roughly and try to see if we can match it, and then wherever the correlation gets higher, that is the region where we say that the face is there. Or we try to get effective filters that imitate the face and then try to run across and see the correlation where it is higher. So the usual procedure or crude procedure is to, if I want an object, let us get a template of it and then try to match, and wherever the object detects is detected. But that approach is very costly. So we will see now what are the developments that we had in this direction. One thing to note is in terms of object detection, there are, for each of these tasks, there are good data sets, especially driven by the requirement of deep learning. As we discussed in the morning discussion, to train the networks, each of these networks, we need large data samples, large samples. So there are data sets for object classification. There is in fact 1.5 million images with 1000 classes is usually referred to as ImageNet data, that is widely used for assessing the object classification frameworks. For object detection, we have we again have plenty of data sets now, and if we see in our large scale, the accuracies till 2012 are only up to 40% mean average precision, with which we see precisely locate the object and across several classes, and that is boosted up very well by the deep learning methods. The ability that deep learning methods has in terms of object detection compared to the conventional methods is much higher, as we can see now in the attributed to the better ability of learning the localizing the objects and localizing the features of the object. There are several developments in this direction. So COCO and Pascal VOC are the well known data sets, and mean average precision is the metric, and there are several benchmark methods. One advantage or the disadvantage with the deep learning is most of the methods that are developed, architectures that are developed are available for direct use and implement application on different domains, and these are all the well known models that have celebrated models which have shown good improvement in terms of object detection, and some of them both for object detection and segmentation. I will discuss a couple of intuitive ideas that has emerged in developing these models. So one way of doing, say if I want to detect multiple a single object for time being, if you want to localize this object, what is important is we need to know what object it is and where the object is. So usually if I want to know which is the object, we perform classification. If you want to know where the object is, we will perform we need to find out x, y, h, w of it, so we perform regression. So what we need to do is once we extract the features through the deep neural network, we use these features to identify the location of the object through regression on XYHW values and classification of the label of the object. So, this is performed together with the same features, and the cost function is a combination of both of them. But the problem is when we have multiple objects, we cannot simply go with a classification and regression framework. We may have several objects, and one way of dealing with it is let us try to get each of the object annotated by different XYHWs and try to run a deep learning model to get the localization and the class label for each of them. But running them for several for each object independently is, as we discussed in segmentation, is not a good approach. What usually is done is, so we would like to first identify the probable regions of the object, and then from the probable regions of the object we would like to say what object it is. So, it goes usually in a two-stage manner. Most of the initial developments are with these two-stage object detectors. What they do is initially, so they scan each region. Usually in computer vision there is a method called selective search. What they want to do is they take all possible regions, and in which of the regions there is a possibility of object. Say usually what the procedure is to knock out the regions where there is no object. Can you tell actually any region, if I want to knock out, if there is no saying that there is no object, what may be the criteria? If I just want to knock out that this region there is no object, what do you think is the criteria? In that region, no edges, okay. What still better a quantitative measure? No variance at all. If I see the pixel variance, it will be close to 0. So, there are some methods like that to identify the region of object, whether in that region, given region, object is there or not there. Once we identify them, then we would like to say whether what object it is. While identifying the region of object, since we take several bounding boxes, we also initially get the XYHW roughly where the object is there, and in that region whether object is there or not. So, that is done through selective search, and then subsequently we try to see what object it is. So, the algorithmic developments a combination of were initially combination of computer vision and deep learning. What the initial developments are to see each of the regions and see the object regions and then get the features for them, and then try to use in the based on these features what is the exact bounding box and what class does it belongs to. But the problem is for identifying the region of object through computer vision, we need to do an exhaustive search, and here for each region different networks are used. So, there is a high computational complexity in getting the features independently for each region. Then the next development is why anyway we need the features for all the whole image space. So, why don't we get the feature extraction, or why don't we get the deep features for the whole image at once, and then scan each of the region to see whether there is what object it is. So, that is the first extract the features, and then from the features apply a selective search kind of thing to identify the object is there or not, and then further we try to identify which object it is. The next level of development has happened in terms of, see initially even here the object regions are done through computer vision, and then for the regions are identified we take the features and apply through deep learning what the class label is. The subsequent developments are why to have a computer vision method at all, even to give the object region. Why don't we directly use feature space itself to localize the object locations roughly XYHW and whether there is an object or not through a training like this. Here there is one you can consider an object detection network. What this does is it does not tell what object it is, it just tries to I switched off. No, fine. It just tries to tell whether there is an object or not an object. The primary task here is to know object or not object through deep learning, and then roughly localize the object as well. That is the first task. Given that task, again use another deep network. Of course, it is a follow-up network. Both are trained in an end-to-end manner. That means we take the loss function here, and that is used also to train this. Of course, there is another loss function separately for this. So, what we want to do here is what class it is, and we also would like to get the label of it. So, that is the next level. Both are done in a training together to identify the localization of object or whether there is an object or not as a primary task, and then what object it is and better localize the object location. So, this is a very celebrated method in fact for object detection referred to as faster RCNN. This has shown good improvement with respect to the time of execution in terms of training and testing compared to the earlier developments. The loss functions are roughly based on the matching the pixels, maxing the XYHWs with respect to the ground truth through regression, and then classification scores through cross entropy. There is one more trick that one more thing that people usually are interested or make use of is as we discussed, analyzing the information at different resolutions. As I discussed in the previous discussion, one way of identifying is looking the object, we sample the image at different resolutions. So, if we have 100 cross and 100 image, we see at say 50 cross 50, 25 cross 25 and then try to see the objects. That is one, we are sampling at the image space and try to look for different size objects or scale objects at different resolutions. The other way of doing it is, say instead of sampling the image or instead of looking the image at multiple resolutions, can I look the filters, can I design filters that look at multiple resolutions. So, we bring it, if we see with a 5 cross 5 filter versus a 15 cross 15 filter, the region I see is different or the way we see the information is different. That is taken care as other way of addressing the multi-resolution or different scale, identifying the objects at different scale. But the idea that is used in fast RCNN is even better. The key contribution for them is to use the anchors. The processing is done at once for all the whole image and get the features in a given region of interest. Sometimes this region may be smaller based on the object, sometimes it may be bigger. What we do is we analyze these features itself through different anchor boxes. That is, after we finally get the features, we try to see at different lengths with small scale or different aspect ratios. So, that is what is done. This is identifying the objects through the anchor boxes. When we do that, what will happen is at every previously as we discussed, if we want to identify whether there is an object, what object it is and then find the XYHW of the object, essentially XYHW and the class label are to be identified. Now, in addition to that, at different scales given by the guided by the anchor boxes are also to be identified. So, the computational complexity finally here increases by k times as number of different aspect ratios or lengths we see. However, it helps us to identify the objects at different scales. So, it is well applied on different data sets and we can see very good accuracies in terms of detecting the objects at different scenarios. Of course, there are associated difficulties or challenges still for these methods. This is another framework which is very celebrated and widely used again. This is referred to as mask RCNN. The ability of this mask RCNN is in addition to detecting or localizing the object or different objects, it also can give the segmentation of the object. So, it is not just detecting the objects, after detecting the objects till the final stage roughly same as the fast RCNN. Here we try to give for the region of the object, region of interest of the object, we try to give a 2D mask where the based on the location of the object and use this for identifying or giving the pixel wise classification as well for the object region. So, this in a sense integrates the previous segmentation method or instance segmentation methods into the object detection frameworks, and once we detect, it does automatically the segmentation as well of the object region. So, this is in fact even more celebrated or widely used than fast RCNN and it is used not only for segmentation, this is also used for several other tasks. For example, this is pose identification. So, whether a person is moving his hands or running, jogging or what is he doing, or the expression analysis, all those things can be done effectively. The reason is actually this has the ability to segment and we exactly can locate each of the part of the person or an object and then we can say what where is it now. So, XYHW will be there, one for leg, this leg, one for this leg, one for. So, we usually have landmark points or some key points of the person to track and all those points we try to regress and then identify in a frame to frame manner. and that can be done conveniently by this Markov-Sierra. There are some other developments for object detection. Essentially, they try to do without doing a two-level detection. Can we do in a single level of detecting the object without initially saying that whether there is an object or not and then going for what object it is? Can we directly say what object it is and whether there is an object or not together? So this is usually done through a methods called YOLO, and there is class of methods of YOLO. These are usually lightweight than fast RCNN and so on, okay, and faster, much faster than fast RCNN and other two-stage methods, but slightly less accurate than the two-stage methods. Now there are several other versions of these methods as well, which are almost all accurate, as accurate as the other two-stage methods. I will introduce or give some little bit intuition on the other computer vision application, that is visual tracking. So the problem in visual tracking is, if we have a object, if we have a series of frames or a video of an object, moving object, if you would like to, if we locate an object at the first frame, can we locate it in all subsequent frames? If a car is moving, for example, I just locate it in the first somehow, either with manual annotation or automatically. Now I would like to know where the car is in all the next set of frames. Not just a single object, but there can be multiple objects. All persons may be moving, okay, in a in general scenario, and we would like to track each person and give unique ID to that person. So if he crosses over the other person, or if he crosses over any other vehicles and so on, he should get uniquely his ID, so that we can identify where he is, and we also can easily assess on the actions and other things. So this is also a very important application of computer vision. So what people usually do is to perform a correlation. Correlation is a building block for all the most of the methods of computer vision, because we want to see the similarity of the first the target object with where is it in the frame. So what they do is they extract the features of the target object, they do extract the features of the search region, and then try to, instead of correlating the image space where to locate where the object is, they correlate or convolve or correlate in the feature space. Wherever the correlation is higher, there we have the better identification of the object, and that we do in each frame. And as I mentioned, there are good number of data sets even developed for tracking, visual object tracking, to evaluate them or to train them as well. So as I mentioned, the correlation is considered, and we would like to see the correlation value being higher, being matched with the actual value of the location of the target, and that based on that we try to see that we the response map shows the peak or the high value exactly at the location of the object where it is. The response map is obtained by correlation. Once we have the peak of the response map, that is supposed to give the actual location of the object, we match with the ground truth location of the object and try to back propagate. So usually many of these things are also associated with challenges. Those who especially want to work in this area are usually submit their methods for challenges and evaluations, and the visual object tracking challenge is one of them. So many of our previous works were through in visual object tracking challenge. Many of the students have worked in this area before. So the problem is to track the objects in very challenging scenarios, in background clutter or say fast moving objects when they are occluded and so on. So there are some contributions from our students to track in occlusion recently. I will very briefly touch upon or discuss the intuitive idea of generative adversarial networks. This we can consider as one of the breakthrough after convolution neural networks, and this has elegance of generating the samples as well. We will see the ability of this through small details. So what the problem usually so far we are discussing is how to classify or how to detect or how to track and so on. So this is more of an analysis task. That means we already have the image with us and we want to locate where it is, and we want to identify what's class or what is the action happening there. But this method, what the problem that is posed now is, see, I have several faces with me. can I say if I consider each say I have several random numbers that is thrown out, say 5, 6 and so on, I will give some 1,000 random numbers or many 10,000 and 1 lakh random numbers. If I give all these random numbers, the question is not to generate one more, the question is to generate one more random number as well, but more than that, can we get the underlying distribution? What is the distribution with which all these random numbers have come? Not just analyzing what the distribution these have come, can I generate with that knowing that distribution or without knowing that distribution, can I without explicitly knowing that distribution or with explicitly knowing that distribution, can I generate samples of this sort? Okay, if a person says for 5 times, okay, or 1,000 times or 10,000 times, can a machine continue? This is the question. So the answer so far before GANs is almost no, but with the generative adversarial networks, at least there is a good ability to synthesize the images, synthesize the different scenarios like we see in real nature. So for example, if we have actually faces, several large data set of faces, of course for training you need the large data sets again, but using that these GANs can capture the distribution of the samples and generate more and more faces. Similarly, any of the different objects. This is usually there is a good literature behind to perform this kind of task. The one way, very crude way of doing it is modeling the distribution itself with some kind of a known distribution and then try to get the parameters of the distribution if I have some samples. I assume that if I throw 10,000 numbers, I say that they are Gaussian distributed. I will just try to find out what is the mean and variance of that Gaussian distribution. Of course, once I get that, I can generate more little. But the other kind of problems are, this is usually done through maximum likelihood approach and so on. And there are other kinds of approaches where they do not want to make a parameterized distribution. They want to develop without parameterizing the distribution, they want to find out the distribution. So that is usually, there are some methods like Pargen windows and so on, try to do that. But the scenario here is much more complex because the images themselves are of like 10 power 4 dimensions and 10 power 6 dimensions. So the feature vectors are the samples, it is not just single numbers. So this much dimensional feature vector is what is describing the image, and we would like to generate such in such higher dimension. So the initial developments are with respect to the autoencoders. What they do is, say for example, if I give an image here, I will try to say that there is an encoding and decoding happens. Finally, I would like to get the image back. So the advantage of this is, even if we get an image with noise here, I may fill that gap somehow and get the noise free image here. Even if I have an image with small missing region 7, if it is written with some missing like details in 7, still I will be able to get 7 here. So there are the kind of application of this, these are referred to as autoencoders, and then subsequently denoising autoencoders which will denoise and give the noise free images, and filling the gaps in the images through association and so on. But these methods have a limited ability because they need to train with the same class and then get the same class with a little bit of for the same sample, and they can't generate new sample all across. And the advantage that usually taken from these methods is to take the decoded features and then use for classification and so on. But as I mentioned, you need to have the sample. From that sample, only that sample can be made better, or you can't generate a new sample. What this GANs frameworks, the idea has come is, say the question is, if we give a random noise, can I generate the, can I see if I have a Gaussian distributed samples, I give some Gaussian distributed samples of 1,000 or 10,000 samples, can I generate uniform distributed samples? We take the Gaussian distributed samples and then generate the uniform distributed samples. The answer is yes in conventional terms to some extent. Even the statistical methods guide us to transformation of the distributions. But however, through the learning they would like to, they targeted to do, and for learning this we need some clue. So assume that this generates some value here, or some other sample from other distribution. In that case, there should be some guiding one that is referred to as discriminator. What this discriminator does is, Say if I want to, my aim is to generate from Gaussian to uniform. So I keep generating several samples, but this discriminator also generates several samples and try to see is that matching with the sample that is there in discriminator or close sample that is there in discriminator. So what the idea is, if we bring in purely on from generating any noise to image, then we would like to see if I want to generate cars, for example, I have several cars and then try to see the generator that can it generate a car. The first initial answer will be no, because it will anyway give a false generation, or it will not generate the image that we wish. So the discriminator initially makes in a critic way, saying that this is false, the generated value of generator has generated false sample. Then it tries to say that it tries to give an error, quantification of error, and that when we train together in some nice fashion, we can see that the discriminator critic will help the generator to improve. So how does they do? So they does usually in a game theoretic manner. What is essentially done is, the objective of the generator is to maximize the probability to generate correct sample, whereas the discriminator objective is to say that it is fake. That is where we start, and then when when they get trained appropriately, the equilibrium happens, and then generator is able to generate the samples that the discriminator has as real samples, and discriminator says keeps quiet. So the it does not have, then we assume that it is trained or it can generate samples. So how is it usually done is, say if we have a say here please note that assume that we have we have the some random sample x, and we would like to generate some the sample of other distribution, and we have a discriminator here which is trying to see whether this generated sample is it correct or not. So G is the whole representation of the network. That means if we have whatever the layers and so on, I assume that after passing through the sample that I have, input random noise I have through this G, what I get is G of x. Okay, this G of x may or may not match with respect to the real sample Z I have. Okay, so if we give here if we want to be in line with that notation, Z is here and Z is the sample, G of Z is the output and x is the real sample. Okay, so this discriminator has real sample and also has this input. Both of them are taken as input to this discriminator. Since discriminator can compare both of them, what it compares is d of G of Z. When I pass this input, what the discriminator gives output is d of G of Z. D, what D is here is nothing but the as you have seen in neural network, it's function of something W1 into X, function of W2 and so on, right. So the whole thing I represent as D here. This function of whole network is D, this function of whole network is Z here. So it tries to see d of G of Z, is it matching with the X, okay, d of X. So the objective of the discriminator, if we want to see first, the objective of discriminator is to say that, okay, the I just assume that cross entropy loss computation is known or can be seen. So it tries to maximize the probability that this is real sample. Okay, so d of x, if we maximize d of x, it means that if I maximize the probability of getting d of x, so we assume that actually this function d is also such a function that will bring the output in probabilities. Okay, so this d itself gives the probability of x being correct. Okay, so now what we are trying to do is the discriminator function is to maximize d of x, probability of x being real sample, plus what, the minimizing the probability that d of G of Z. That means it want to say that the generated sample is not correct. So what it does, 1 minus of d of G of Z is maximized. So what is happening here, the first term is maximizing the probability of real sample being correct, that probability of real sample. The second term is what is it doing, the prediction of the g of z is not correct. Okay, 1 minus I have used, so it is not correct. So the objective of this being maximized with respect to the all parameters of d, okay, for the discriminator training. Okay. So while the generator function is what? Generator does not care about discriminator. Of course, it uses the feedback from the discriminator. What it tries to does? It tries to maximize the probability of g of z, d of g of z. Okay, if I pass through, if my sample gets passed through discriminator, I would like to get the maximum value. That is the objective of the generator. Okay, putting together what we have here, here is directly we are using d of g of z, here 1 minus of this. So we minimize here with respect to generated parameters. So this is what the objective function that GANs does with. What they are trying to do, generator purpose is to maximize its sample passing through d of discriminator, okay, probability, but the when we put in framework 1 minus of d of g of z is minimized by in generator, whereas the discriminator tries to maximize the real sample probability, but they minimize the sample that is obtained by the generator. So this is done in a iterative manner, and then this one there are several difficulties or several aspects that are to be taken care while training the GANs, because this is a min-max function. There are two networks which are not directly interacting. So after taking care of reasonable aspects of training, one can see that GANs can produce reasonably very good accurate image synthesis or sample synthesis. So the initial experiments are to generate the digits, and then subsequent experiments are to generate images, and then initially the results were not that great, but later with several advancements while to train them better, to take the loss functions in an effective way and so on, we can see that we can generate very good images. Of course, the ability of GANs not just ends with generating images, they also enhance the ability of computer vision methods that we will see with an example. Also they can help to see that at the feature level like the attribute level integration, so picking the some aspects of one image and put on the other. So automatic colorization, all those are the advancements are the offsprings of the GANs. So for each of these methods there are model juice where you have several models to experiment or to develop further with. So I will conclude with this small example where in computer vision we can see that this can be considered how GANs play a role. So this can be considered as generator, generating a higher resolution image from the lower resolution image. This can be used as a discriminator where it sees the generated image with respect to the actual super resolution image and try to improve the generating framework. This framework, this is like a conventional CNN or convolutional neural network for super resolution. This to putting together with the discriminator is the GAN framework. So I will conclude with this. You can see plenty of references for deep learning and deep learning in computer vision. As I mentioned in the morning, Professor Fifi Lee team Stanford has video lectures on convolutional neural networks for visual recognition. There are plenty of other references there. Thank you. Are there any questions? Okay, thank you then. We will.
Thank you, sir.
Thank
you for an intuitive discussion on computer vision applications using deep learning. Now I hand over.
afternoon, everyone. So after a long discussion on ML and DL techniques, where we talked about different types of algorithms and computation methods, now we invite Dr. Santosh Kumar Vishwakarma, who will talk about in-memory computation for edge AI applications, opportunity and challenges. Professor Vishwakarma did his BSc degree in electronics from University of Gorakhpur and MSc in electronics from Devi Ahilya Vishwavidyalaya, Indore in 2001, followed by an MTech degree in microelectronics from Punjab University and a PhD degree in microelectronics and VLSI from Department of Electronics and Communication Engineering, IIT Roorkee in 2010. Then he was a postdoctoral fellow at University Graduate Center, Norway. From 2010, Professor Vishwakarma is with Department of Electrical Engineering, IIT Indore, where he is a professor now. He is leading nanoscale devices and VLSI circuit and system design laboratory there. He is engaged with teaching and research in the area of energy efficient and reliable SRAM memory design, enhancing performance and configurable architecture for DNN accelerators, SRAM based in-memory computation architecture for edge AI, reliable secure design for IoT applications and many more. So I welcome Professor Vishwakarma and over to you.
Thank you. Is it audible? Hello. Yes, thank you, Professor. So first of all, thanks to IIT Tirupati to invite me in this holy city. I came yesterday and then onwards I am taking roaming of the city and that to the temple. And it's a big challenge for me to you guys to make live, and that is the tea time is close to 3 o'clock or so, right? So you all from which background? I mean, computer science or electronics, electrical? Mix. Okay. Okay. Yeah, so it will be more challenge for me to explain this hardware concept, but I believe that you will enjoy. I mean, at least because as of now I was just listening to Professor Rama that people are talking about more about software side, but in system design we need hardware, right? So what are the things we have to take care of if you are really thinking of to design and develop and something workable model? Without hardware things are not working, right? So little bit knowledge about hardware will always make your interest live. So probably I will try to bring the hardware aspect of these machine learning or AI aspect, what are the hardware availables, and even if hardwares are available, that why we are doing edge computing and so on and so forth, right. So many things you may have covered, but I will try to touch up not in detail in technical insight, but what are, since this is a new area, so I thought I should talk about opportunities and challenges, right. Little bit about contribution what we have made, not that much. This is a group where I belongs to in IIT Indore. So where we primarily work on memory design, right, especially on the static SRAM memory, and there also we try to make the edge AI computing using SRAM only. The last 5 years we are focused on the accelerators, right, and then in the past couple of years we have made lots of project and we have designed couple of chips for IoT applications, and there also we talked oftenly about reliability aspect of the chip design, because if you are designing any circuit or system, so that should be reliable. So we are also touching 2-3 PhD scholars on reliability aspect of circuits. So this is the group where I belongs to. Coming to the research activities from 2010 onwards, so what we have started, that we have started with the devices. Those who are from electronics background, they may understand very easily that what are these MOSFETs. So since this is so if you if you just see this diagram, this is FinFET structure, but it comes from FinFET. So, FET stands for field effect transistors. So, but early days, right, many years before, when the chip things started, the concept came MOSFET, right, metal oxide semiconductor field effect transistor. So, this was the fundamental block in semiconductor devices and later in circuit and systems, by which you can realize any complex circuit. Okay. So, but over the period of years, right, when you try to have more functions into the chip, more operation into the chip, right. So, we need a huge number of devices on a tiny chip. So, for example, if you are considering a chip size of 5 millimeter cross 5 millimeter, okay. So, in this tiny chip area, right, we have to have lakhs and lakhs component. So, how to do? So, initial days, for example, if this is the MOSFET, okay, and this is the channel, and this is the silicon dioxide, and this is the N plus, this is the N plus, all right, and then of course silicon dioxide, and this is the gate, this is the source and drain, whatever you can change, the source and drain can be interchangeable, right, and of course this is the body, and this is the channel through which the electrons can take the movements. If you are talking about N type enhancement type MOSFET, okay. So, there are various categories of the MOSFET. The first category was the enhancement type, where we try to enhance the channel or create the channel by applying the proper potential on its gate. So, I am just brushing up the semiconductor devices and physics, okay, just to generate the interest. So, the electrons used to go from source to drain, and hence the current used to flow from drain to source, right. This is the fundamental physics behind this. So, since you are trying to create the channel, right, so that the there should be a path, okay, just between silicon and silicon dioxide, okay, and that the number of electrons which are flowing from source to drain depends upon the applied electric field, and hence this name is called the field effect transistor, because the current conduction mechanism used to be controlled by the applied vertical electric field or horizontal electric field, okay. So, you try to shrink the device dimension, maybe the channel length, this is called the channel length, this one, the width and the depth, and many things are there, so that you can accommodate large number of MOS devices in a tiny chips, okay. So, as a result, people evolved various MOS transistors, where the FinFET is the one which is commercially available in many processors which we used to have in our mobile phones. Qualcomm Snapdragon 22 nanometer technology node, you must have heard of it. So, over the period of years, people have thought of that if you shrink this device dimensions, right. So, what are the alternate options called the advanced MOS devices, okay, advanced MOS devices, right, where if you scale down the device dimensions, right, and if you are supposed to operate at lower voltages. Early days when the channel length was for example 180 nanometer, okay, then applied voltage was 1.8 volt, okay. Now, since we shrink the device dimensions, so you cannot operate the same device with shorter length at 1.8. So, you have to scale down even this from 1.8 to, for example, 0.2 volt or 0.5 volt, right. So, everything we are syncing, right. So, electric field is supposed to be maintained within the device, okay. But forget about all those things, but you try to understand that people in the research community try to evolve various non-conventional devices. Conventional device is this one, the MOSFET, which was started 40 years before, 60 years before, right. In fact, the concept of the MOSFET was in 1930, right. But at that time, the fabrication technology was not available by the research community or even fab labs. So, then the FET evolved, JFET evolved, junction field effect transistor. Couple of years JFET comes, then over period of years 1948 or so, BJT evolves, right, and then in 1960 or so, the MOSFET, even though it was invented in 1930 or so, close to that area, right, that era, But in 1958 or something, the first monolithic IC fabricated. So, it took years to evolve the chips. And now over the period of years, if you scale advances, try to see more functionality and so on and so forth, people investigated various non-conventional devices where FinFET is the one, tunnel FET is the one, and gallium nitride and so on and so forth devices evolves. Okay. Now we have talked about foldable devices also. So foldable devices, now silicon is not there. So as of now people are talking about all materials silicon. Now we may have seen all Samsung foldable lavender phones, right? Smile, is 3 o'clock time means let us charge. Lavender phones, so it's costing around 80,000 rupees, more than that, right? So how foldable comes? Lots of OLED are there, OLEDs are there, light emitting diodes, right? So with the semiconductor materials era also devices developed, and hence the product developed. Earlier we used to have a flat screen, now foldable screens are there, or you can say curved LEDs are there, right? So many things evolve, and hence people started research from devices to materials and try to investigate some circuits and later bigger circuits and try to make some kind of these boards having various part and then of course chip. So this is the one board which we used in our lab called the Zinc board, which is this board is called the system on chip board. So what I am trying to explain is that that last 12-13 years we have started working on the devices, device circuit co-design, couple of chips we have fabricated. Then for IoT hardware based experiments we have used couple of boards and so on and so forth, where we have interfaced couple of sensors, and then we have realized couple of system on chip. For example, this is the IC, right, which was tested for one of the biomedical application chip called IoT wireless sensor node, right. So where for example this is the ADC block sitting, this is the memory block, and there are many other blocks are sitting on this 5 mm cross 5 mm chip area. Okay. But what we have done and what we have learned last couple of years that as of now we were trying to interface only signals of only not really image or even video or audio. But with the evolution of these computer vision, just now Professor Rama was talking about, where we oftenly interact with the images as a data sets, right. So when you are interacting with such a huge data sets with your hardware, right, so it is not so simple even for the chip designer that the normal chips will be sufficient enough to process such a huge data or to store that large number of data, okay, in the same chip. So people thought of, can we have a sophisticated chips or a very appropriate chip which has a capability to deal with the images or the audio or video, right. So how to design those kind of chips, even a small thing, for example power dissipation or power dissipation of the chip. There also we have to evolve the machine learning techniques, right. So the entire history of the VLSI chip design is changed now last 2-3 years. Okay. So now people are thinking what should be the hardware, how to design various hardwares or various sub blocks of a complete block. For example, a processor. So in processor there are multiple blocks, right. So for example, addition is the one operation, adding 2 bits, right. So how to do addition or multiplication of those 2 bits. Even multi bits, right, multiplication, how to do. So all those mathematical processes or the operations is also performed in a very systematic manner, and ultimately as a researcher or as a product engineer we have to store all those huge data in some hardware. So what are the different techniques by which you can store or retrieve the data rather than the von Neumann computer architecture. So in von Neumann computer architecture, so there is a processor, okay, and there is a memory sitting on the chip, right. So processor used to process the data, right, and this is the memory element where the information are supposed to be stored or retrieve the information, right. So both the things are little bit away, right. But since there are various applications where these techniques may not be applicable, so how to do? So rather than von Neumann architecture, right, if the data used to go from here to here, it will take some time, called the latency. So to minimize this latency, people are trying to come up, can we have both the things on the same chip? So in memory computing, so computing used to be happen in the processor and storing here. So can we have the everything in memory itself, where no need to travel the data? So that is what the topic of the relevance of today is, right. But at the same time, since we are dealing this complex inputs can be image or something. So what should be the complete hardware? And as a researcher, sometimes it is very difficult that we always look forward for the GPUs, right, or sometime even bigger than that, right, to train the data. That required the money as well, right. So how with the small FPGA boards, right, you can train the bigger data? That is also a topic of the interest. So we have developed couple of algorithms where neural networks, bigger neural networks can be trained, and you with a small money budget, from not more than 20,000 rupees board, right, you can easily train the model, and accordingly you can improve the performance of that network, right, on a particular data set. So we will discuss all those things, but what I am trying to explain is that our journey was with the devices, materials till system. Okay, coming to the exact topics, right, people are talking about AI, and why? But because we need to have some motivation things, right. So motivation is like that there was era of internet, okay, where deep neural networks was not really that much, but it is forecast that in the coming years, right, the DNN market is going to be really changed like anything. So DNN market will start from 2020, before that I should say. So in next under 20 years or so, we will have a huge jump in this area, in deep neural network, okay, called the deep learning, okay. And this also you can understand in the worldwide picture, if you see, right, in next couple of years. And so this is the North America, right, and then Western Europe, and then of course Eastern Europe, Asia Pacific market is this. So in Asia Pacific market, this AI accelerators, or you can say the AI chips, are going to a big leap. So that also sometimes motivates us to do the research, okay, in AI accelerators, because if money is there, then definitely research will be there, product will be there, right. So this is how the trend of the artificial intelligence and the AI chips, okay. So this is just to motivate you guys. And there was one word called the edge. So what is happening in the edge? In early days, even now also, for example, the servers are there, or you can say the cloud is here, right. So cloud is what exactly cloud? A huge number of servers sitting remotely, right. So for example, if you do some computation, right, and your all the information used to go and compute on the cloud, and according to your request or the user needs, so data comes from the cloud to your machine. So it used to go from your end user to the cloud, and it comes. So that takes some time called the latency. But there are various applications where even this millisecond time may make a difference. So for example, autonomous car, okay, the sensors are placed in the car, okay, and the car, if the car is passing through various ways, okay, so it used to encounter various images. Accordingly, the car should work, right. So for example, the turning image are there, or ahead image, or lidar sensors are there, whatever sensor you are using, right. So what I am trying to say, you have to take the decision right away, quick decision, right. So for that a particular hardware is needed, right, no processor computing, should be on the same chip and everything. So and Google Glass is the one example, right. So if you are wearing this Google Glass, okay, so a small chip is there, and chip used to interact with all the images which are encountering, and accordingly it used to act, right. So that is what, like of course mobile, wearable, IoT devices, almost all the connected devices are going to have the AI chips, and that to the edge. For example, this light is there, or bulb is there, right. So bulb, you have IoT devices, and there also, and few years before, the sensing elements sense the data, and it used to send to the cloud, and then based on your requirement it used to come the decision to the user, but it takes some time. But nowadays, for example, safer city concept, right. So in safer cities, cameras installed in the city, right, and images are going to be captured by what the movements, something or whatever, right, and then you can take the decision very quickly. For example, the police officers or the crime police or something has to take immediately action, right. Otherwise, there are various applications, strategic application, for example, where the sensing element computing element and everything are sitting on the edge. So, for all those edge devices, what should be the required hardware? I mean the chip, what should be the philosophy that we are talking about. But just to motivate you that these things are is very very important, okay, on edge intelligence, and I just now talk about the issues. So, where do we have inefficiency comes from? So, I said of course, the algorithm, circuit and systems which are sitting in the chip over here, and the hardware architecture. So, if you can think of these circuit and system part and the algorithm side part, right, which by which you are designing the hardware, right, then probably you will meet the requirement of the edge computing. Okay. I was just talking about the edge. So, in the cloud what we does, right. So, for example, here, right. So, this is the cloud computing, but this is the edge one, right. So, no need to go on the cloud, things are over here, and accordingly immediately you have to take the decision, right. So, latency time is very very less in edge. It is not a much difference, only maybe milliseconds or fraction of second, but there are various applications where you can think of. Okay. So, but of course, what are the benefits of the edge computing? Of course, enhance the data security, okay. Low pressure on the bandwidth, even internet speed or the bandwidth is very low, you can operate, because sending the data from your sensing elements to the cloud, it needs huge data or the bandwidth. But there are various applications, for example, border security areas, right, where sensing element would be there, even with low bandwidth you can sense the information and train the information, right. So, of course, reduce latency is the one, low cost data transmission, increased availability. So, these are the couple of benefits, and accordingly you can design the hardware, okay. And this is the one example of the edge AI, right, and these are the latency what we are seeing in the market, okay. Now, so these things we have just spoken about the relevance of the subject and what kind of hardware do we need, right, on the edge computing. But almost all the places many speakers may have spoken about the neural networks. So, I will not spend much time, but just to brush up that the DNN lots of inputs are there, and these are the hidden layers, okay, and these are the outputs, okay. This is the fully connected neural networks, okay. And for example, if this is the one neuron, right, model, right, of for example MNSC data sets. So, this is the 10,000 samples of 0 to 1, it is easily available, right. So, for example, 9 can be written in multiple ways, right. So, how 9 can be recognized in its output, that is what is being shown over here, right. So, for example, this is the input and they are the hidden layers, there are neurons, large number of neurons are there, and then ultimately you can get 9 or whatever it is there. So, but in this process you have to pass on this complex theory into some hardware. So, what should be your hardware? That is the main interest of your story, okay. But if you start designing a simple neuron, one neuron, okay, where images are supposed to interact, so we need to have the first block called the MAC unit. MAC means multiplication and accumulation unit. So, what is that? So, for example, this is the one input x1 and this is the weight of the neurons, because here you may have learned maybe understand the fully connected network or any kind of CNN or RNN, whatever it is there, every neuron have its weight and bias, okay. So, that comes from the training, okay. So, if neurons will have some input, any number for example, and some weights, so they need to be multiplied, for example, x1 into w1, so that is multiplication happen over here, plus x2 into w2 and so on and so forth. All the weights are going to be multiplied by the input, and accordingly you can get. So, what is this? This is a multiplication, this is a multiplication. So, that is called the multiplication and accumulate addition. So, addition is also coming over here, addition, right. So, it seems we understood very nicely as of now that to realize a one neuron in the hardware, right, we have to have a little bit knowledge about the multiplication what we have learned into the digital electronics. So, in digital electronics we may have learned how to multiply 2 bits or even multiple bits or multi bits, right, and then addition of course we know, okay. And then to fire each neuron we have to have some activation function. So, activation function can be of different varieties, sigmoid, tan hyperbolic, Swiss, ReLU, many things are there, right, available in the market. So, depending upon your application we have to have some activation function and Mach unit, and you can start thinking of designing one neuron, then multi neurons, and then how to use this activation function, in which way, how to use these hidden layers, right. So, we have to introduce some concept. For example, we have used this is all about once again Mach unit implementation, activation function, like for example high performance neuron architecture. So, couple of my PhD scholars, they have worked upon how to enhance the performance of neurons. Okay. So, we have used various philosophy, for example reused feature. So, the same activation function can be used for multiple neurons, so that we can reduce the complexity of the network, and with lower hardware we can deal huge data sets. So, those exercise we have done, like here we can see there is sigmoid function, tan hyperbolic function, and then in the neuron architecture we have improved, right, and this is how the codec algorithms, and then we have put couple of multiplexer, and then you can find, for example, this is the tan hyperbolic block, okay, and this is the sigmoid block. Okay. So, I mean no need to worry from being as a computer science fellow, but you try to understand that we have adopted, and you can find various ways in literature by which you can enhance the performance of the neuron architectures. Okay. Layer reuse philosophy we have used maybe, and then yes, here yes. I mean I have not shown many things, but we have used how many times you have to use, right, that is also one factor comes, and then we have improved the performance of the neuron architectures. So, as of now what we have learned? We have learned how to do the computing of neurons. I mean the fundamental computing is the multiplication and addition and activation function. So, these three blocks you can make using Verilog or VSDL digital design language. You can also design these neurons into analog approach also. Okay. So, as a hardware person we have to understand various data sets, for example MNIST data sets, right, or Cipher10 data. So, Cipher10 data is the 10 classes of images started from the bird, car, human, and so on and so forth. And then we have to also train various architecture of the neurons, which I am not showing here, like linear architecture, right. There are multiple neuron architectures are there. We have to train the model, we have to find and calculate the weight of the neurons, feedback somewhere else. Okay. So, ultimately what we are doing? We are trying to find out some trained weight of neurons which is supposed to be stored somewhere else. Storing means we have to have some memory element, right, which I started with here, some memory element. So, how to store such a huge data sets, that is the interest of the discussion. Okay. So, this is the recon architectures which we have developed in our lab, right, complete flow of the recon architecture, reconfigurable architectures of the neuron, where multiple layers are being used, so that the same layer can be used for various architectures. So, this is how we have learned that how we can improve the neuron architecture, or how we can enhance the performance of the hardwares. Now, a very interesting topic that is that was one of the outcome was the AI accelerators. So, accelerator is nothing, is like once again the chip only, but since you are interacting at kind of data sets of images or video or whatever it is there, right. So, your hardware should be competent enough, that is called the accelerators, which accelerate the performance of the chip. So, all the components which are sitting, for example addition, multiplication of even all available blocks or sub blocks, that should be designed accordingly, so that can interface the images data sets. Okay. So, this is nothing special, okay, but your chip should be competent enough to deal with the specific networks. Okay. Okay. So, for example, here if you are taking the input size of 5 cross 5 kernel size tried and output, you are getting one input. So, these things once this is a vector multiplication. So, these things you will learn and do the things, and then you will find out, and accordingly you can design because here it will come multiplication, addition, everything is coming, right. So those things we have to perform in the background, and then you can calculate. But you try to understand that ultimately we need a sophisticated hardwares. Okay. So now question is, which kind of hardware you should think of for edge computing. So for training the data sets, multiple variety of hardwares are available in the nature in the market, right. So GPU is the one, right, graphical processing unit is the one, FPGA and ASICs. So ASIC stands for application specific IC, which is small in size, very tiny chips. FPGA is little bit this much size, and GPUs are of course bigger in size. So if you try, and there are a large number of accelerators available by even Google, Intel, Xilinx, all these companies, they have their own accelerators, NVIDIA. Now the issue is that for edge AI computing, do we need such a big servers? Because they will consume power, right. So what kind of hardwares or what kind of accelerator we should, right, so that edge computing can be done with a small form factor, low power consumption, and without losing the data and maintaining the latency. Okay. That we have learned in the few slides before. So GPU can also be act as an accelerator, right, but the advantages are with the GPUs are like, which of course the increased speed of the computation. So if you have a huge data sets, for example image, so usually very easily you can compute on the GPUs, okay, and this is because of the efficient parallel processing, multiple cores are sitting, okay, and then the high bandwidth computation feasibility and ideal for existing ML algorithms. But limitations are of this kind of accelerator if you are using GPUs are high power consumption, because the big servers are there, right, and of course extreme heat generation is there. So maintaining a servers in the data centers is a very expensive, with the cooling effect basically, right. So the keeping servers is much easier rather than maintaining those servers into the cooling environment. So that is what now these liquid coolants are coming, where the entire GPUs are going to be put inside those liquids, so that it can dissipate the heat of those complete servers. So right, so you can see in the market. So GPU has also a couple of advantages and disadvantages, but bigger in size, more consume the power. So is it suitable for the edge? Not at all. How about ASIC? ASIC is a tiny chip, very small chip. Okay, so ASIC is of course the optimal speed of transferring the data is optimum, not a big deal. Lower power consumption, which is the need of ours of edge computing, right. More application at embedded devices. So this may be suitable, but couple of limitations are there. So limitations are no flexibility, means once you design the chip, even it's very tiny, right, you cannot reuse, right. So that is the one issue with the no flexibility in nature. Long time to market means designing a chip, right, it requires huge, like 1 year, 6 months or even 2 years time, a big team also. Focus on various components, for example ADC, many blocks are sitting right here. So time to market is also very long in this, and of course the cost of implementation is very high. So because of these limitations, people are less preferred to ASICs, right. But FPGA is another class. So what is FPGA? FPGA is a field programmable gate array. So the plus point with the FPGA is flexibility of computation. You can do multiple times. You can write the code of the desired AI accelerators multiple times. If you are not satisfying your goal, you can reprogram, and that is called the flexibility of the system. It means it's readily available chip which are placed on the board, okay, which I have shown in one of the beginning slide, which is reprogrammable. So flexibility is the one important, reconfigurable is there, logic computation, high performance per watt is very good, right. But of course low throughput. So this is the only reason that the complex programming required, of course we need to know, right. So reliability and the efficiency and the flexibility, right. So ASIC is of course very efficient as compared to an FPGA. So FPGA is, for example, you try to understand if this is the server size, FPGA is like this much, and tiny chip is like this much. It is a very form factor varies like this. Okay. So, because of this, but of course, the FPGA is also not so small, but nowadays the Xilinx, now Xilinx is being taken care by AMD. So, AMD Xilinx they have come up with a very small form factor of a kind of stick, memory stick, or you can say the kind of pen drive kind of stuff, where you can deal with huge data sets. That much sophisticated FPGA they have come up into the market. Even Intel also they have come up with, right. So, that is what people are trying to evolve. So, the FPGA and GPUs and ASIC things are being shown over here, adaptability, availability in prices, user friendly and power efficiency, right. So, this is how ASIC is, right. Of course, availability and cheaper, of course, the price of the ASIC is very cheap, very cheap, right. GPU, CPUs of course low, and FPGA is the medium one. So, that is what most of the people prefer the FPGA as a potential candidate of training the algorithms in the hardware, and hence the design and development of those FPGAs are also very important. So, can we think of rather the processor and many things on in memory computing and so on and so forth, right. And once you are happy with your target which you are sensing and everything, you can convert that FPGA board, that is tiny chip, into the ASIC using some softwares. So, that is what majority of the people works on the hardware for FPGA, and if they are happy and okay, they can convert into tiny chips very easily, right. So, as of now I have explained what are the available hardware to deal with these neurons or neuron architectures, which is primarily used in AI or machine learning things, right. Now, coming to the edge computing, or you can say the in-memory computing, right. Processor is there, and then of course memory blocks are there. So, in early days one human architecture, right, both the entities are going to be at different blocks. So, if you are keeping both the blocks and doing computation and storing together in memory, called in-memory computation, right. So, the data movement was one of the bottleneck in conventional computing architectures. This is called the von Neumann architecture, which was evolved many years before in computer architecture, right. So, and these operations of course you can do, not a big deal, so no need to explain, but you try to understand what are the latest memory technologies. I am directly jumping now. So, SRAM is the most preferred destination, or the static random access memory, then DRAM, flash, RRAM, PC RAM, SSD RAM, and many RAMs, many memory technologies has been evolved last 30-40 years, but still SRAM is the most preferred choice even for in-memory computing. Okay. So, now here also if you see the fundamental blocks is this MOSFET, this is called the MOSFET, which I was explaining here, right, MOSFET. So, this is a MOSFET, even this is an inverter. Inverter will also have some circuits. So, inverter means if you are passing 1 here you will get 0, or 0 then 1. So, this is a cross coupled inverter, and these two are access transistors, and these are the word line and bit lines. So, one cell can be stored in this SRAM, right. So, there are lots of advantages in technology and so on and so forth of these available memory technologies. Okay. But even RRAM is also going to be one of the potential candidate in the coming days for AI application, right, resistive RAM basically, right. So, they do not have I mean this multiple mass transistors, only 1-2 plates are there, and in 2 plates you can that can be acted as a switch, right. So, that is what the RRAM is also going to be a very potential candidate nowadays. Last couple of 1 year or so, a huge research is going on that how RRAM can be used to store or retrieve or compute even, right, in for AI applications. So, in many places research is going on very heavily. In fact, many industries they have already come up with couple of hardwares on that. So, coming to the in-memory computing, just now I talked about that ultimately when you are dealing any kind of neuron or something, we have to store, we have to process, right. So, to process and store the information we need the memory, right, and we need to compute into the memory, means storing there and processing also. Processing means some operation you are performing, for example addition. So, to add the operation we have 2 bits, right, are multiplied 2 bits, you need 2 bits, right, and store there as well. So this is for example bit line 1 line, so bit line 1, bit line 2, bit line so on so forth, bit 128 for example. Here word line 1, word line 2 and so on so forth, word line 128. Just now I was talking about here. Here this is the bit lines, bit line bar, and this is the word line. Okay. So one memory, this is the SRAM cell of which can store only 1 bit. So likewise there will be multiple cells in an array. So the same has been shown over in the next slide. Said for example this is the bit line 1, word line 1, here you can store 1 bit, and to store 1 bit we have to have a combination of 6 transistor SRAM cell which is shown over here. So likewise all the points, right, we have to have 6 transistor SRAM cell here, 6 transistor SRAM cell here and so on and so forth. So this is called the array, and then of course we have some peripherals, because bit line 1 and bit line 1 bar would be there, which is supposed to be sensed by sense amplifier, which will be placed here, and then how to go and hit this cell, there we have to have driver lines, row driver, column driver. So all together we call as peripheral circuits, which is not shown over here, but ultimately you have the sense amplifier, pre-charge circuits, decoder circuits and so on, multiple blocks would be there, and all together what I am saying, that is the peripherals, okay, which will enables to store the information or retrieve the information from the cell or into the cell. Okay. This is called the array. This is called the array. The column would be there, sense amplifier, write drivers, right, various circuit block, row decoder. This is called the M cross N SRAM array. There are M rows and columns, and on each cells, right, which is shown over here, 1 dot, 1 dot, and so you have the like this. This is just simply has been shown 128 bits row and 128 columns. So you try to understand that with the concept of SRAM, how operation will be performed, operation of performing the addition, subtraction, multiplication, division, what we traditionally do in processor, right. In processing what we used to do, 8085 processor or recall or AT&T processor, we have to pass some commands like addition process, right. So similarly how to add, perform the addition operation here, okay. So all those things will be here. For example, this is the 6 transistor SRAM cell, okay. Now this is the foundry 8 transistor, means foundry means as of now last 50-60 years in the history of chip design, right, SRAM is, this is the one which is the preferred choice by all foundries, by either by Intel or any industries, right, in memory, especially SRAM. There are various custom 8, then 8 transistor 1 capacitor, so there are even 10 transistor and so on and so forth. So over the period of years various configuration of memory cells has been evolved of these categories, for example, right. So you can think of to use this memory cell and you can perform some operation. How come? This one? No input, detecting. How is the HDMI port? Okay, good, thank you. Can we make it larger or the same size? Will be there? Yeah, it was the same size. Okay, okay, thank you. Then anyway, so what I was explaining, yes, done. Maybe a little bit down. And that's good. So what I was trying to explain that over a period of last 40 years, there are various memory cells which has been evolved even in SRAM category. there are various categories, right. So, SRAM 6 transistor is standard one, but what happens with SRAM, you cannot perform many operations in case of in memory computing. Okay. So, people have thought of, even our group also evolved various architecture of the SRAM cell, by which we have performed various operations in the memory itself. So, processing part and computing part both we have done together, and not only we, but many other researchers. Okay. So, these are the various memory cells, especially 6 transistor SRAM and its successors, and depending upon the advantages and disadvantages of each one, people preferred. Sometime 8 transistor, sometime the other one, sometime 10 transistor, and so on and so forth. Okay. Okay, so this is how we can compute in digital side and analog side and so on and so forth, but here is the point of interest, that how SRAM can be used in computing mode. So, if you see here, so this is the XNOR mode based read word line driver column, and if you see here, right, every rows and column you will have a cell, which just now I have shown, right. And then of course, we have the decoder, and then with the sense amplifier you can take the output, right. So, these are the techniques and the methods, okay, which applies to do the computing as well as the storing in SRAM, right. And here also you can see in one of the other work where convolutional SRAM, right, where they have used 10 transistor SRAM cell here for 1 bit, okay, and IMC based architecture for the CNN accelerator. As a software guys, you must have learned what is CNN, deep neural network, low power and high throughput. Here there was some problem of the 614 giga operation per second, row wise and charge sharing of the SRAM bit cell was placed, all row wise. Okay. For example, row number 1, row number 2, weight number 1, weight number 2, and so on and so forth. And then they used to place ADC, and then from here you can take the conventional output, and here you can take this convolutional input, and the convolutional output you can get. So, people have come up various ways to use the memory architecture in CNN accelerators, or you can say CNN computing memories. Okay. Like this is the another accelerator, right, where in memory computing based hardware accelerators are being used. So, various layers are there, okay, and these are the memory interfaces, like I said, sense amplifier and so on and so forth. So, multiple XNOR SRAMs are being used by multiple times. I just said that reused feature. So, layer will be used multiple times. So, if you do this, then you can improve its performance. Okay. So, many people have come up with various ideas, layer by layer basis computation comes, okay, and double buffering schemes and time multiplex and reused over timing also. So, this is complex architecture, but if you try to understand that how people have used this philosophy to do computing, right. For example, these are the neurons, right, which we have to follow, the train weight, activation function, multiple layers, and each layer are supposed to be stored in some transistor, SRAM cell, right. This is the one, like then you have to do filtering process, pooling process, all those processes you have to do in the hardware itself. So, as a software guys, you may understand how to do how to reach out to the complex output of the CNN networks. So, we have to do the filtration process and so on and so forth, but ultimately as a hardware person, we have to evolve all those things into the hardware. So, like here, right, all the neurons are here, 32-bit for example, driver lines are here, word lines are there, and each cells are sitting. Okay. So, how, for example, over here. So, this is the 10 transistor SRAM cell, where this complete MAC unit we have performed, multiplication and addition. As I said that in this AI part, right, machine learning part, we have to multiply the neurons and add it, which we are doing here. Okay. And then if you have a 1 MAC here, 1 MAC and so on, so multiple MAC units are there, right, and in 1 MAC how you are designing the efficient MAC, that matters, and hence the overall performance of the circuit will matter. For example, over here, seen over here, that the 3 input of 28 cross 28 image, okay, and then multiple times if you are doing all those CNN networks, then you will find. But every stages has to be passed on and store over here and do all those computational things, operations think over here. Okay. Right. So, this is the one thing which you can, is timing analysis and so on and so forth, which we have to do. It is not like that you can just pass on and you can get the output. We have to follow various timing diagrams and timing requirement, so that you can get the exactly output what we desire. Okay. So, many things we have done, and we have used the INMAC block, which was near memory computing, right, and various row drivers are there, column drivers are there. So, initially what we did, like other researcher, we have also investigated using 6 transistor SRAM cell, okay. And later we realized that no, 6 transistor is not sufficient enough. You cannot perform a large number of operation like this, right. These are the operation, addition, subtraction and so on, so incremental, decremental we have performed. So, what we have learned that couple of operation we are able to perform all basics, but not advanced operation. So, we thought of, can we use 10 transistor? So, first what we did, we tried to investigate the analysis and performance estimation of the 10 transistor SRAM cell, which meets in memory computing. So, we started doing all those analyses and many things we have done at various blocks and at the hardware level, and we have designed this 10 transistor SRAM cell with Taiwan Semiconductor Manufacturing Unit node 65 nanometer, and we realized that even advanced operation, CAM operation and binary neural network operation can be also performed using 10 transistor SRAM cell very efficiently. So, we have done all those stuff, right, and multiple MAC implementation for the neurons, right, the dot product is there and the many products are coming, right. So, how to perform all those products and so on and so forth, so that ultimately your image, ultimately what you want to process through the various pooling and filtering process and so on and so forth, you can get its output. So, what should be the relevant process of using SRAM architecture into the computing process that we have investigated, okay. And we have found that the CNN network with the MST data sets and ANN network with MST data set with the accuracy of 98 and the corresponding binary neural network accuracy was 96-97 point. So, all those processes we have done into the hardware. This is probably the last slide. So, overall framework of the SRAM based IMC, okay. So, circuit level what we can do, bit cell architecture. So, those who are from the hardware background or the electronics background, they can understand the bit cell architecture. What kind of bit cell you have to choose, okay, like 6 transistor SRAM cell or 10 transistor or what exactly, ReRAM or what exactly. So, that we have to consider. Then the function level, what kind of functions you are performing, right. I mean the digital SRAM based KIM or mixed signal SRAM king, because there are purely digital side, then analog and mixed side, single bit, multi bits, CAM, Boolean logics. What are the functions you are performing, NAND, OR, NOR, binary CM, and many things are there. So, these are at the next level called the function level operation of this in memory computing, and then if you are performing everything perfectly fine, you can go with the application level. What kind of network you are training, right, CNN or the AES algorithms, what you are doing, right, everything you can perform. So, this is the complete framework which will be used in the hardware accelerator design of this kind, okay. Of course, these are the challenges and possible solutions, right. If challenges are there, of course solutions are also there, right. So, we have to have various optimized materials and the device structure, as I said in the very beginning, like MOSFET was the one, then the FinFET was one, there are multiple architectures, right, which can be potential application, right. Endurance and retention in the flash memory technology, these are very important, right. Multiple states, speed and power. So, stability of the devices is the another challenge, right, which one has to think, because we are dealing huge data sets. So, your hardware should be reliable, secure, safe, many things, right, and that should have a larger data sets which can be compiled. So, these are the level where we can think of large scale integrations, new materials like silicon, maybe we can think of some other materials, right, and the crossbar array fabrication, the silicon technology, right, and then the system level application where algorithms for the physical application and peripheral circuits. they can also done by the system level, no need to design even circuits, right. So, these are the few challenges and the possible solution. Okay. So, if you think about these stuff, right, the memories, right, which we have talked about just now, it is a complex actually understanding, but ultimately we have to design the energy efficiency, right, of the Mach operation. So, your Mach should be designed in such a way that they should consume less power and very efficient, very high speed and so on and so forth, because in the entire neural network or the image kind of stuff, we have to have the dot product, I mean the multiplication, addition, and the pooling, filtering process will come anyhow, right. So, how do you do all those things, right, in memory today I have covered. So, this is the group where we belongs to. So, she is Neha, right, the leftmost, then Gopal, my PhD scholar, she was MS, she has also contributed very good. Sonu, PhD scholar, last 1 year he is contributing. Narendra is the PhD scholar, last 3 years he is contributing, and of course me, backside. Yeah, Vashundhara, she is also PhD scholar, last 1 year she is contributing this area. Sumiran is MS research, last 2 years he is contributing, and Varun, MTech student, last 2 years they are contributing. So, we have this is the this AI accelerator group, and apart from this group we have various other groups where we are working on different dimensions of the research. So, thanks to these people that they have contributed last 6 years or so in this important area of the research. So, from my side done, this is my web page and this is the email address, and if you have any interaction, anything, so please let me know. We will be happy to help you anytime, and we will be happy to even take from you people if you are working this dimension. So, from my side done, and we can interact if any concern or any suggestion or even any other things. I am sorry, probably I have taken much time. Yes, yes please. Okay, resistive RAM, great.
Yes sir. I'm working on arithmetic circuit implementation actually.
Okay.
So we are saying it takes, if we take von Neumann architecture, it is taking only 0.1 picojoule for 32-bit addition.
Yes.
Whereas accessing 32-bit data from DRAM is 640 picojoule. May I know the reason for that? Is it because of the capacitive charging and discharging?
Charge, yes. And in your architecture only capacitor is there.
Yes.
RAM, only one capacitor. That is the top plate and bottom plate.
Yes.
Right? Resistive RAM.
Yes, sir.
So that is what your device is much faster than the DRAM.
Yes, sir. But if we take one general transistor based circuit, it is easy to understand because we say energy is always consumed because of capacitive charging and discharging. How to understand the same at system level?
But fabrication of the MOSFET is also very tedious and complex process. But
yes.
Fabricating two plates is very easy. Like so that is what, even when MOSFET was not there, only this was there. Only this what we call is these things were not there. I am just forget, they were not there.
Yes.
So only silicon dioxide layer was there, and then metal layer was there, and then silicon layer was there.
Yes.
So even early days this concept was given. You got the point?
Yes.
And the same concept is being used by RAM people. So in early days, what used to have, this is the silicon dioxide, okay, and this is the metal line, and this is the silicon line. So this is still the same, right? This and this RAM, two plates concept. But fabricating this part was very difficult. It took 60 years by the researcher, by the even foundries.
Yes.
So now probably what is my understanding that the same philosophy which was like parallel plate structure is came, that is the RAM. So even we are doing research on SRAM, and recently last 2 years one of my master's students started with some German partners the same RAM based circuits and systems. So what we are doing there also, we have designed the in-memory computing and the cadence environment, and you can download RAM based technology file from IHP or even IMEC Belgium. Okay. You can easily download, where you can just connect and make any any operation over there.
Currently, I'm using a Stanford PKU model, sir,
Acha,
for my
PK.
simulations.
That also fine.
Sir, when we say 640 picojoule, where exactly it is going? People are asking me, you say 640 picojoule is consumed when we access 32-bit data from DRAM. Where exactly it is going? Like that energy, where it is exactly consumed during the transfer from memory to the processor?
I can't comment because I don't work on those area, but we'll discuss sometime because we are dealing only the SRAM side.
Okay.
But DRAM side, yeah, I mean DRAM is also one of the potential candidate because it with the only one transistor, one capacitor, you can store such a large number of data, right?
Yes, sir.
So like high bandwidth memory, HBM is there already there.
Yes.
But what I feel that what you are touching the area RAM is very good. Yeah, because the RAM is only one capacitor, right? Even no transistor is needed. So you can accommodate large number of data sets, right?
Yes.
And so since we have not performed much, but last 2 years I have given one task to one of my master students and he did a good job. But the one point which you are addressing we have not focused upon, so we will discuss sometime and we will try to understand where is this power consumption is going on.
Sir, one more thing I would like to ask. When we use different models for the memory store devices, the operating frequency is varying. For example, if you take some SPICE model in LT SPICE or something, the operating frequency is different. For the Stanford PKU, the operating frequency is different.
And my suggestion is even it's come from the standard, you use the now this IMEC Belgium people and this IHP Frankfurt order, yes. They have come up with standard industry standard RAM models.
Okay, sir.
And you better use cadence rather than the LT SPICE.
Oh, yes, sir. Sir, this IMEC one you are suggesting, is that open source?
Yes, you can easily download even from any foundries. Just we need to sign the NDA with them.
Okay, sir.
Okay, and maybe your professor, even you can sign that you are going to use that technology for your research and development purposes only. Okay, so they will give you access to download those technology file and you can use in the cadence environment like normal PDK we are using, right?
Yes.
So we have the process design kits of, for example, MOSFET 130 nanometer or any other models. So like those models they have already developed actually.
Okay, sir.
So unnecessary as a circuit designer we should not develop our own model.
Yes, sir.
If possible in your research.
That is
we can use our model because that is also well tested model, fabricated, measured data and everything. They have the technology file. And very easily you can, in fact, our general partner are very happy to fabricate those chip in the IHP only.
Okay, sir.
So even if you go with that model, you will have the tested workable results with you.
Yes, sir.
Right? That is my suggestion. Rest we can discuss because we are entering into the technical discussion and maybe. All right.
Yes, sir.
Okay, good. So you are in PhD here?
Yes, sir. I'm a PhD scholar.
Okay, good. Yeah.
Thank you so much.
All right. Thank you.
Okay, thank you, Professor Vishwakarma, for a wonderful talk. I hope that students got an idea about, not only algorithms when we talk about machine learning and deep learning, but we also have to look at, ultimately we have to implement it in the hardware and use the hardware. So it was a very informative talk. Thank you very much.
Thank you.
Now I would request Dr. Ramakrishna Gorti to give a memento to. Okay, so I think we are little running out of time now. So we will have about 10 minutes break and come back. I think tea is served on the first floor, and then we will have the keynotes.
page in a random sequence, you try to put some information knowledge into that, constraint onto that. That is VAF. Okay.
Shall I wait till they come, or maybe we will start 4:50?
No, it should be green. Hello.
Okay, now can you
Hello. Hello. Thank you.
Yeah, good evening all of you once again. So it's a pleasure for me and it's very nice that it's very good we have with us Professor B. Enginarayan sir giving the keynote lecture. And we are very fortunate at IIT Tirupati that he is here, an adjunct professor here at our IIT Tirupati from the last few years. And before that, he was there at BITS Pilani, Hyderabad, and also at IIIT Hyderabad for over 10 years, and at IIT Madras as professor for over 26 years, and IISc Bangalore. He is a faculty member for over 12 years, and he was a visiting associate professor at Carnegie Mellon University for over 3 years. And before any of us would have perhaps heard the name artificial intelligence, he has authored a book on artificial intelligence and neural networks, Prentice Hall of India Publications in 1999. Okay, so there might be some of us who are not born as well, some of you. Okay, so and it's he has guided over 30 PhD students, 42 MS thesis, and many hundreds of papers. And we are very fortunate to have you here, sir. Thank you.
Thank you. Muted it. Okay. So I suppose you can all hear now, and maybe you can switch off that projection if you don't. I have no material to project, so I am the actor, so you have to watch me. Okay. So, beg your pardon?
Can you present from here?
Oh yeah, I think you are recording mechanism. Okay. All right. So let us start. You see, when Professor Ramakrishna invited me to give a talk, and I just asked who are the audience, what is the topics, and so on. But he gave me some idea, but he asked me to give a general talk. That is all I can do, because I am not. I retired from service formally almost 20 years ago from 18 years ago from IIT Madras, and 10 years ago from IIT IIIT. But all the same, fortunately, I still do some work on my own, and I do keep track to the extent possible whatever. So what I propose to do is, in the next 1 hour time that they have given me, to talk about what we are not doing, what we are doing, all these people are explaining, you see, and what are the challenges in these last 2 talks. I heard excellent talks. So what we are doing, what we need to do that. So what I propose to do in this, in my presentation is to highlight what we are not doing. You see, you may say, why? Why do you need that? Because I retired and I am only not very active anymore, but you people can't say that. You are not that lucky to say. You have to have another 30, 40 years in front of you. So you have to worry about what we are not doing, you see. And so most of the things, of course, it's not that I am randomly saying. I do analyze things. Maybe my views are not in tune with what most of you have, which is good. That's why it turns no. And second thing is, as it so happens, of course, in my case, although I have not done anything very great in all these subjects, because AI has been there for a long time, and I was lucky to almost rub shoulders with all giants in AI for the past 60 years. That is the only qualification I have. Not that I have done anything great in this. Of course, once in a way I have a couple of times, maybe at IIT Madras they asked me to give a course on AI 40 years ago, and I gave some talk. That's okay. But but that AI has nothing to do with AI now. And this AI will not have anything to do with AI 10 years from now, you see. So you can almost be rest assured. I mean, there is no question, because all of you have seen only 2 decades or 1 decade. I have seen 6 decades. So that's why change is constant. You see, that is what you have to understand. Keep ready, because it is not that what great things are happening, what great things are not happening. That's what we have to. And for that, it so happens that, of course, one thing that doesn't change is a human being. That means we are still some 5, 6 feet and so on, and they have not changed over centuries. So suddenly 10 feet are micro miniaturization, 2 feet or 1 foot and so on. So they are same. And also, I don't think the number of neurons here have not changed either. You see, nobody has counted. We are estimated is 10 to the power of 100 billion neurons and so on. Knock off 1 0, it doesn't matter. Nothing happens. For me, some neurons have already gone. So that is the whole point here is, this whole workshop from the program I saw, and also my discussion with Professor Ramakrishna, I was told, is around learning. So I would like to take that as the theme of my talk, still learning. And notice that learning, as far as this program is concerned, I may be wrong. You can correct me after my talk. But I thought learning related to machine. That's why we call machine learning. At least majority of this discussions here are on machine learning. And then, of course, the so-called words, supervised learning, unsupervised, self-supervised learning, and all kinds of things, reinforcement learning, what more are there? Many more learning terms that have come, and that is and transfer learning. Some more learning now words will come along the way. You see, all applied to the machine. And all this that we are doing, we are simply calling it an AI. Please note that. Please, very important to understand. We are not defined what AI is. What we are doing, we call it AI. That's the point. Very important point to understand. Again, my talk is just to provoke you to think beyond this. At the same time, I have this 80-20 rule. What is that 80-20 rule for everyone, especially researchers like you, youngsters like you, who are active up to 50 years, at least I am assuming that all of you will be active. Afterwards, not that you will taper off, but you will make others active. So the 80-20 rule is the following. 80, you do whatever we have to do for the technology, follow the crowd kind of a thing. The 20% mental activity, you sit separately and see, what am I doing? Why am I doing this foolish thing? See, like that, you should be self-critical on this. That will generate beautiful. Just keep writing, don't have to give a lecture on that, you see. And so unless you have that, if you put all your 100% on there is a danger, you see. All your training that you are taking now, after 10 years you are not wanted anymore, because the training is useless. That 20% will help you to adapt to the new one and so on, you see. That's the philosophy. So learning, and now it is whatever we talk about learning is related to machine, and all the learning, whatever you do with that machine learning, we call it as AI. That's why it's called AI ML, if I am right. AI ML, you know, right from 8th standard onwards it goes now, you know, right up to PhD level. Everybody is AI ML, you see, and degrees are also with AI ML and so on. That's fine, you know. I want to provoke you to think what is not done here. That's the point. First, let us start with the whole focus of my 1 hour talk is about learning. Focus is on that. And learning, unfortunately, has nothing to do with machine. Learning is a human attribute. First thing we have to understand is learning is a human attribute. And another very important thing is learning. Please note my English. Learning is not learn or learnt or learn. It is simply learning. What is that? It's a continuous thing. It's a continuous thing. That's what human being is doing. So just to, you know, all these words got mixed up over 40, 45 years. Thank God, you know, I have to teach. I don't have to teach on this, but otherwise I will be shaking in a class, you know. I don't know what meaning or things that I have to give for these words. Learning, knowledge and intelligence. These 3 words. Learning, knowledge and intelligence. All these things were there some centuries ago. It's not that you have invented now. And they are all human attributes. So the whole summary of my talk is how those human attributes are looked at in the context of machine. That's the point, you see. So this is what and before and of course I don't have slides, because since morning I was thinking how to organize my thought, but I couldn't come up with a great structure. So you have to put up with answer. And another thing is, the message I want to convey, the moment I put a slide, that message is lost. You see, fundamental thing. You think that we are doing great things by a slide. Every slide destroys the intelligent part of your presentation. You see, because it is not letting you to think. That's the point, you see. That is the reason why I have not used slide. Of course, I also don't know how to use the PPT and so on, but I can take help of some of you to prepare them, but that's not the point. So in the I want to organize this into 5 sections. I don't want to write it on the board. Let us start with talking about pattern recognition that all of us know. This is the supervised and supervised cave. Pattern recognition, when you say it is statistical pattern recognition, that's what all of us talk. Syntactic pattern recognition has come and gone with case foo. So it is not there Purdue professor and so on. So it is all statistical pattern recognition. But, and then the second point I want to discuss here is the evolution of this AI, whatever you want to call it as AI, over past 70 years. That is, from for want of a better name, I can put it in different ways. Evolution of AI from intelligence to AI, or from learning to deep learning, or from science, engineering and technology. I can talk in any of these domains. You see, that's so evolution of AI. That's the second topic I want to touch upon. The third topic I want to touch upon, which is very important for all of us, because we refuse to think most of the time, it looks like. And it was, I don't know how many of you know R.W. Hamming quotes and so on, you heard about it, you know. Hamming said, machine should work, human should think. That's what Hamming said. But now we are letting machines to think, and we don't know what we should do. We are not supposed not to work or something like that, I don't know. Anyway, so the whole point is the third topic I want to take it up. In fact, so evolution of AI, Not, please, whenever I say this, Blaze, don't attribute any expertise to me, I am not. But it so happened that I went through all of this. I was a student in 1950s, and from then on, moved to this and met some of the giants in this field. Not that I interacted with them very much, kind of a thing. But so I want to highlight that. And so the evolution of AI that led to what we are today, you see. And so that is this second point. Third point is the distinction between human learning, not machine learning alone, human learning, learning in ANN and machine learning. They are very different. Please note that. Very, very different. You have to understand it, so that's why you can see what we don't do, what we don't know. So I am distinguishing human learning, that is inherent, that has been there for centuries, there is no question about it. In fact, people learned much better earlier than what we are doing today. So human learning, learning in ANN, my perception is, I may be wrong, please don't mistake me for some words. I am senior enough to say that, and senior enough for you to pardon me on this. So I use certain terms which are, you see, human learning, learning in ANN, which in my opinion, many people whom I talk to, nobody knows what it is. And then machine learning, very different, all these things. So that is the third topic I want to briefly discuss, you see. And the fourth topic I want to discuss is what is called the, it should be fifth topic, because first I said pattern recognition, evolution, okay. Third one is human and machine contrast, human, ANN learning, and then machine learning. And the fourth one is, these days I have been looking at this topic much more seriously, but for myself, that somebody provokes me to talk about it in some forum, so I do keep saying that, the missing science in AI. The missing science in AI. You see? So these are the 5 topics I intend to cover in the next 40 minutes or so. That's what I propose to do, and all of you are welcome to ask maybe at the end of my talk, because we'll discuss openly some of these things. So let us start with pattern recognition. I asked a lot of the guys in, all of you heard Indian Statistical Institute, Calcutta, and also you might have heard the name C.R. Rao inequality and so on. I talked to these people, and there are giants in, I said, what is a pattern? No answer. You have that is correct also. Please note that. What is a pattern? No answer at all. Now quickly go and refer to all your dozens of books on pattern recognition, you will never find a definition for a pattern. You see? And so the pattern recognition that you talk about in books and treatment, statistical pattern recognition, all these things is a pattern. There are one view of this, but there could be slightly different views and so on. The pattern recognition is a statistical pattern recognition. A statistical, there are exceptions, please note. So statistical pattern recognition, and most of the cases, although they refer to what is called the common feature space. A common feature space is what you talk about. That is why when you talk about a classifier, you are talking about how this class features are different from this class feature. That's what you talk about. You see? And of course the regression and so on. And somewhere like Bishop's book and so on, they keep on saying, oh, one leads to the other, be classification, regression, they explain them in the same framework. That's all fine, but there is some, this is not the forum to argue, but if you deeply think, there is something amiss there. There is something wrong there, you see. So classification, let us just, I am not going to spend too much. So the fundamental question here is, it is a common feature space. Already you have diluted the problem completely. You see, if I have to distinguish you from you, I may use some features. Distinguish you from you or you from somebody else, I may use some other features. So the features that you use are different, and by throwing it in, because why did you throw it in a common feature set? Because I want to use statistics and distribution. So this is the tool that forced the tool means that concept that forced us to look at it, but in the process you have already destroyed the problem. That's the most important thing, you see. So, and it is also interesting, although we have, these are the thoughts I am collecting, in fact especially last one year, last 1 month, last 1 week itself I have made some notes on this, but so my thoughts are not well crystallized. But having said that, I thought Ramakrishna has given me a forum to talk, let me talk. You see, that is the way I looked at it. So, if you take let us say that feature space itself, let us say one class some class and other classes, you see. Typically, as I told you, this class, many other classes that you have, you want to compare with, the one class, maybe there is a commonality that is called the descriptive features. There is a descriptive or generative features that is likely to be common, reasonable to expect a common feature space. But discriminating between classes has to be different features. Why? It's like a ruling party and opposition, you see. Even these days ruling party also oppose each other, that's a different matter. Assume that ruling party, they are supposed to have some underlying philosophy, you know, try to, these days they jump the ship very quickly, but let us not worry about those fellows, but you know, just what is opposition? Just because opposition name is there, they don't belong to one class. Same point works in pattern recognition, and we never do that. Very important. And another very important thing in pattern recognition is, you see, that the so-called feature, we force the feature on the data. That means some kind of a representation, and that you use it as a feature. Good, that's not a problem at all. But human being, the beauty of that is the feature that you see from the, let us say from pixels of a face or something like that, is very different from different people or different persons, you see. So, the feature that you extract is very different, but let us assume that the feature is constant here. So, that is the pattern recognition, the way, that is why I was asked to give a talk at by Professor C.R. Rao, you know, he is a great giant, he is now running 102 years in Kramer-Rao inequality and so on. He asked me to give a talk in the statistics department of Penn State in college in US, and I was just hesitating. Giants of statisticians are sitting there, and I am asked to give a talk. I was scratching my head what to do. I say, I am not a great statistics man, and the topic I chose was why pattern recognition is not a statistical problem. And you know, I gave a talk. C.R. Rao was my host, and at the end of the talk, C.R. Rao said, if you listen to Professor Egnana, nobody will get any funds. See? So that was the, so it is true. If you take a human pattern recognition, it is not a statistical problem. I don't have time to explain that, but it is not a statistical problem. And just to digress a little bit to see, not exactly matching, but you know, since all of you are talking about machine learning and dimensionality reduction and so on and so forth, all of you have done PCA. You know what is PCA? Principal component analysis. You have done that. So, you collect large number of face images, of course, crop them up to 32 by 32 or 164, whatever it is, and then you collect eigenvectors, eigenfaces, you call it, two-dimensional vector, eigenfaces. You see, and what somebody said is, okay, you take 20, 30, 40, 50 projections onto the eigenfaces, you get the person's face representation. Am I right? I think I am right there, but we are all wrong there. The real face is after removing that 50, first 50 you have, I don't know if you ever have looked at it. If you ask a person to recognize a person, I have done this experiment myself. If you ask a person to recognize from the projection on the first 50 or 25 or whatever it is, because all the variance is taken out into the, and the resultant remaining part, you see, that is where you can recognize a face, recognize an individual person. Beautiful. You see, the same thing works in speech as well. I am not quoting speech because which is what my field is, but you know, it is exactly the same there. That's why the residual type of a thing. But you know, it's like a sour grapes kind of a thing, you know. Since you don't know how to handle that residual, both in speech and image and so on, we say it doesn't have any information. Don't even look at it. So that is the pattern recognition part of it. There are many stories about this. Now I have indicated a few of them. Let us move to the next one. You see, that why I am saying pattern recognition? Now we are saying that AI does something like, that's why I mentioned initially supervised, unsupervised. For a human being, if you are not heard this, if you are not an electrical engineer, if you are not joined IIT or something like that, or engineering college, or if you ask somebody in the road who does some other discipline like music or English or whatever, or some other field, let us say architecture or something, you see, and you ask him this question, what was the question? I forgot this string. So he will not understand what you mean by this. I forgot that word. What was I talking about a minute ago? Huh? Supervised, sorry. Thank you. Just sequences. So if you talk to them, supervised learning, unsupervised learning in their daily life, do you get any answer from them? It has no meaning for them. In fact, for a human being, there is no meaning at all. In our whole life, we never do supervised learning explicitly. We never do unsupervised. Whatever, we had to break them into this category of problems and supervised learning, this category of problems and unsupervised. Otherwise, Same thing with reinforcement learning as well. We use it all the time to learn, but we never called it as reinforcement learning. If you start categorizing your daily activity into this, as a human being, you are in big trouble, because it doesn't capture all that you are doing in a daily activity. You see, we do learning a human way, but none of these are applicable there. But for our pattern recognition, this one, we need to call this as supervised learning, unsupervised learning. That is how, you see, the reason I am saying, somebody says, very simple, okay, what is that? And labeling. You give the label of each category and so on. Why do you need label? Because I want to train my neural network. See, I am stuck with this. So I have to train that. So I need to labeling. And now a lot of papers are coming in mislabeling or wrong labeling or confused labeling and so on. Hundreds of papers are coming on. So this is all nice to generate lots of papers, you see. But who asked you to label that in the first place? Because you want to apply the machine learning. I am just saying, so that is the evolution of the second topic, that is about the pattern recognition, the evolution of AI over the parts to this one. You will be surprised to know, see, poor fellows who thought about AI 60, 70 years ago, they never, fortunately all of them have died. You see, that's why none of them are available to discuss. See, otherwise they will get a heart attack and they will die. You see, that is our current AI. You see, I am not. Please note that I am not disputing the effort at all. I am only talking about, because unfortunately they were born 70 years, proposed it so many years ago, and we are using the same term. That is what they would complain. You see, the AI, we almost forgot I part of it. You see, what almost? I don't think, if you ask even among us, let us take a equivalent of a Turing test, let somebody sit as a judge and you call one by one and say, what is mean by AI? You ask all these 30, 40 people, no two answers will be correct even up to 20%. You follow what I am saying? So this is so I will tell you briefly, because this topic alone I can spend about 10 hours. So I will spend in 10 minutes or less than that. You see, evolution of AI, it started, there is an inquisitiveness to understand when you say you are more intelligent than him or something like that. How do you measure this? Of course, intelligent is not a relative thing, kind of a thing. In absolute terms also, when your activity displays some kind of an intelligent notion perceptually for the person, what is that intelligence you are talking about? That was the question in Dartmouth conference those people addressed 1955, 56, around that time. That was the one where AI, if you carefully read their course, what they said is, all aspects of human way of doing things, if you understand, we should be able to demonstrate it by a simulation. There were not great computers at that time. You see, that means your understanding is more important. That is science. And intelligence, so you attribute the word intelligence, doesn't matter. That intelligence is a natural process. Intelligence is always associated with a natural process. Please note that. And so the natural process that you display, they call it as intelligent, and they are scratching their head. So the whole idea was not to build a machine to demonstrate all this, no. They were not interested at all. They were interested only, can you understand as much as possible what you display, your human ability called intelligence. That's the Dartmouth conference goal, AI. And then slowly in those days computer, some only in the most advanced countries also they have only a few batch machines and so on. So they were not thinking of building machine and which can do all these things and so on. So that is so then what happened was, computers were getting slightly better, at least in other countries, you see. And so then some big shots like, for example, Alan Newell and Herbert Simon, I happened to just spend some time in their lab, although I just shook hands with them, but I don't know much about what. They wrote a book on human problem solving. They are called Fathers of Artificial Intelligence at Carnegie Mellon University. And so that means instead of, then they switched slowly the attention from what is at Dartmouth conference AI was proposed to the machine. Then they said, okay, machine was doing a numerical manipulation. Machine computer means compute numbers and so on. That is what it was meant. So, a computer doesn't compute numbers. You are interpreting the manipulation of one's bits as an addition, subtraction and so on. Otherwise, it doesn't do addition, subtraction. You are interpreting the manipulation that is done in a machine in terms of on-off states represented by 1 and 2 as numerical computing. Please note, I think all of you are seniors, so I don't have to say that 1 and 2, 1 and 0 have no numerical value. It is only a representation of two states. Please understand. And also, sorry for sidetracking on in a way like this, the so-called word bit. So everybody uses. I ask so many students, what do you mean by bit? All of them give promptly the wrong answer. That is a binary unit or binary. It is wrong. It has nothing like a numerical addition. In fact, if you want to abbreviate the binary digit, it is called binit. Binit is the abbreviation. Bit has a specific meaning of information. That's why you cannot use that. And now it is also called Shannon. You see. So that is, please don't, of course, since everybody is using, you see in our village, Nehru is called Gandhi. So like that you can call this whatever, you see. So it doesn't matter. So the whole point here is, that is how this Alan Newell and Simon in the AI evolution, they thought this manipulation can't be interpreted like symbolic manipulation instead of a digital number manipulation. That is how symbol, once you manipulate symbols, it becomes a logic. You can draw inferences like logic books. I took a course in logic in 1950s, for my BA degree. So, and of course I forgot all of that. The logic means inference, that is a human effort, human ability. You only can do that. So they said, why can't I develop a machine to symbolic representation management? That is the real starting point of AI with a machine. You see, that it was in early 60s, you see. And then of course I don't want to go through all of that will take several hours. Then what happened is AI is, but sidewise, side business, something is happening. All of you have heard what is called Rosen. Everybody, human being is always a curious person. See, in what direction you are curious today? So everybody wants to understand this unknown thing called the brain. And I keep telling, God has designed this in such a way not to be understood. You see, If you understand that, you don't feel like living. That is the problem. You see? He has encapsulated. So everybody is like a white elephant, a blind man and wild. Everybody, oh, I understood human brain kind of a thing. This is this is how we started. In fact, although it must have been even earlier. If I keep track of it, 1940s is one Hebb's proposed Hebb's law. How the learning takes place in biological neural. That's anyway. All those stories are. So Rosenblatt, very important because it relates to somewhat Professor Priya's talk, what you have presented, and also related to what Ramakrishna has presented, you see. And link may not be perfect, but I think it triggered some thought in my mind, you see, with what Rosenblatt has said. Rosenblatt is the one who proposed a perceptron model for neuron. What is a perceptron model? Weighted sum, applied a threshold. Please note that. That is only to biological neuron is firing and not firing, nothing else. And of course, you can approach. So, understanding a single neuron itself, several Nobel Prizes have come. You see, understanding the brain of 100 billion neurons, I don't know how many Nobel Prizes will come. You see. The point here is we don't understand how they. And notice that whole thing, of course, I will come to the next topic what I am talking about, but in the learning part, but since I am on this topic. So, Rosenblatt had proposed a perceptron model and built a machine which can recognize certain symbols, let us say characters or something automatically. It learns, that means you display, show the symbols or characters, let us say, and the machine, next time you put another one of those 26 characters, it will recognize that. It has a hardware that was built and put it in an exhibition. Everybody was thrilled. This was in mid-60s, you see. And in fact, the perception at that time was, notice that there were digital computers, but still I was a student in early 60s, so I worked with analog computers only. Digital computers, we couldn't have that luxury of this. Lots of stories to tell about it, let me not do that. So this is Rosenblatt, when he proposed that, he has said something else which all of us ignore. And that relates to what Ramakrishna and I forget your Sunil, Santosh. You presented this talk. So sorry for my wrong. So Rosenblatt has proposed the input to the perceptron is not the sensory input, is not the samples of the speech signals. Input to the perceptron is the output of association units. And that association units means, imagine there are so many blocks, association blocks kind of a thing. It looks at the image and one unit collects data from or pixels from some 100 of them, let us say out of 1000, and another unit collects another 100, not in a sequential manner, in a random fashion. Random means it is not random. So that is the association. In fact, the beauty of that is the functioning of the association dynamically changes. For one image you see something, next image or next instant the same image, association units change. But we left that, we struck off that association unit from the our dictionary, you see. Although I put it in my book, I have to strike off sometime, otherwise people don't follow, you see. And so that is the problem. Right now your convolutional networks, you say, oh, say average this, and then of course whatever it is, I don't want to use our terminology, and so they are all fixed. So you can see, as long as you use that fixed, you can't get the kind of a result that you get from a biological system. That's the point I want to. I'm not evaluating and saying this is better, that is that. That's not my intention at all. My intention is to analyze and see what it is. So this is the evolution of this. So perceptron, and of course thanks to Minsky and Papert. If any of you have not read that book, you should read that. It was published in 1969 because there was a euphoria in that mid-60s that digital computer may never come. You see, they thought this whole thing, based on perceptron, you are able to solve problems. This is the model of computing. So they thought there was a euphoria, but suddenly these fellows, Minsky and Pepper, they don't keep quiet, they just work on this mathematically for 2 years and published a book called Perceptron. That's all. The whole excitement Rosenblatt has created died immediately. It was a step function. You see, once that book released, then they said dump Perceptron. That's all. That is what has happened in that. But it's an excellent book to read. It's a highly mathematical book too, but very beautiful. And anyway, so Perceptron. Let us leave that, because they came even in our here presentation, so I was referring to that. Otherwise, my intention was not that. So then what happened? In 70s we go. Symbolic manipulation, lot of everybody was engaged. I don't know whether you heard a name called Hans Berliner. He was a great chess, not only chess player, but chess programs he has written. In those days, I am talking about 50 years ago. He was at CMU. I met him also. So anyway, that's it. But 70 something has happened. Lot of things have happened. I will briefly. 70s what happened is the symbolic manipulation, they kept it aside. Computers are getting more powerful. So they wanted to know whether you can demonstrate the ability of human intelligence in a machine. So they are more focused on machine. So, and they said, okay, games like puzzles, chess and so on, they are board games with specific moves as operations. So that can be represented in a machine. So they put it, the intelligent part, we are suppose you are a great chess player, so you are more intelligent than me. That is the impression. So that is they are able to simulate by means of as a such a problem. So intelligence became a heuristic such problem. And that heuristic means is not a blind set, brute force set, but only at every time somebody plays, only many of them are pruned, many options, only a few of them are left. That pruning is called intelligence. And but that's what I used to teach in my AA course in early 80s when I taught, you see, pruning. That was the, but then people didn't keep quiet, you see, and that said, they applied it to image recognition. I am looking at all of you. I can count how many people are here, you see, and I can do many other things. So that means it is not that processing, image processing, but I am understanding the scene. I am understanding this image. So likewise speech, when I am talking, all of you can, if you want, you can take the dictation notes of what I am doing, you see. And so that is also, you don't really capture all my speech signal and so on. You are understanding the speech and then writing. So that's why the image understanding, you type in Google, you will get it. SUS and IUS, image understanding and speech understanding systems are developed, motivated by the heuristic search and so on. Very beautiful. In fact, it so happened that I was thick in that kind of environment, not knowing what is going on kind of a thing. But anyway, I just type a few commands on the system and get some numbers, and that's all. I didn't know beyond that. But there was a huge activity. And please understand, beautiful. So symbolic manipulation, yeah, heuristic search, yeah. But then what happened was, even at that time itself, I have to give another example to do that. You see, just again side digression. You have to put up with this kind of a thing. You see, we all talk about natural language processing. You see, when you are listening to me, you see, this is a speech processing kind of. So, and the speech we always link it up language. We don't have to. In fact, speech is a much higher level of speech is only for communication between two human beings. So that is at a much higher level of naturalness, and which you cannot put it in paper. When you put it on paper, you don't know who spoke that. And without emotion he spoke, without gestures he spoke, and all this also conveys the message in the communication. So that is the natural part of it, no question about it. You see, now what happened? Thanks to our Google level, and also we follow them. You see, we are always at the back. The point here is NLP. This NLP, I don't mind, all what is that? Some millions or billions, I don't know, whatever number you talk about. For me, all of them are same. So text you take and build a natural language processing. But what are you doing? That natural language is simply a text. And why do you get the text? Somebody speaks. Let us say if you want to do speech recognition, from speech You ask somebody to transcribe and keep the text and then process that, and they call it as natural language processing. But from speech, if you come to text, you have destroyed all the naturalness that is there. You understand my point? And you put a text, and now from text translation, text to text and so on, and now you want to create a speech again. So you have to, this is hard, you have to plug in the naturalness, put the naturalness back into the, how do you put it? Of course, we have all model, dialogue model, this model, that model, that is how we are all surviving. This NLP is a great thing, all the jobs, AI jobs are there, but you can just see, we destroyed the problem. You see, we destroyed the naturalness, and there is no, we don't even understand what is the natural process that you have destroyed. So you can't say that I have put it. Somebody said, no, this professor doesn't know. I listened to the speech. It is so beautiful. It is so natural and so on. Can you guess what it is? That because you are listening, that missing naturalness, you are substituting from the brain. You don't even know what you are substituting. That is the wrong message we are getting by saying, oh, something is happening and so on. So you can see, where is the intelligent part of it here? Intelligent part you have already done by transcribing the speech onto text. You have destroyed all the intelligence in the text, and now you are putting it back into it. You see what I am saying? Why I am putting in this fashion is, it is not that, I did say in the beginning of my talk, it's not that what we have done, but what we have to do. What we are not doing is what I want to highlight. You see? Not that all that I am saying is right, but it was just, so anyway, now let us continue our evolution of this one. Another beautiful thing that has happened, if you notice, apart from this, see, when you talk about speech or image understanding or something, or when you are listening to me, for example, there is I always distinguish even my signal processing courses. I teach normal, I'm a signal processing person, and I work in speech signal processing in particular. So when you are listening to me, you are not doing speech signal processing, you are doing speech processing. When I collect the speech signal from the microphone, put it in a machine and display it, that is speech signal processing. That is where you are busy writing all the papers. You know, you write algorithms, papers and all like this. Mine is better than others and so on. But in speech processing, when you are listening to me, the beauty of that is, you get the signal, this acoustic waveform into this, and you process it. While processing, without your knowledge, because maybe with your knowledge, you are using so much of acquired knowledge that you have about English, syntax, semantics, context, and also the whatever it is on the subject, all that you are using in understanding the speech. Suppose you put somebody else, somebody from the road, let us ask him to sit and listen to my boring lecture. Oh, it was really boring because he doesn't have that background. He cannot put that knowledge into that. You follow what I am saying? So that's exactly they caught at that time in 70s. That's why they didn't use the word knowledge based system, but they start injecting the knowledge into this for speech recognizers. And SVMU, MIT and so on, especially CMU, the knowledge you are collecting, I am talking in the context of speech, image is much more harder to get the knowledge, because speech at least there is a production and also some slightly better understanding of the process, you see. So anyway, let us focus on this. So that knowledge, syntax, semantics, prosody and so on, that's why you can see there is a book written, published at that time, Trends in Speech Recognition. Beautiful collection of about 15-20 articles, and published by Vian Lee and Jane Chu. Excellent. You see, what is the message that is there is, you have the speech signal, that is input, and you inject all this knowledge onto that to decode the message. And that is Roger Reddy's group in CMU produced at least a dozen PhDs, I think, using this. And of course, I didn't work like that. Whatever system they produced, I started doing some experiments with that without knowing what they were. But it was, you just see, it's very important to understand. That means speech signal itself is not enough. You have to inject the knowledge into that to decode this. Please, that is the message I want to convey. You see? So this knowledge has to be incorporated explicitly. And then somebody thought, instead of doing like that, can you build a knowledge, go to somebody like a medical expert or legal expert and so on, ask them to call out, to extract get the knowledge out of him, kind of a thing, so that you can dispense with him and use the knowledge based system and so on. Unfortunately, it didn't stand for more than 4 or 5 years, you see. So, because you can never pull out, when you are saying something, doctor also, how did you diagnose this, means he cannot tell all the ideas that he may, since you are forcing him to say something, he will say something, but you cannot pull out it. So, knowledge based systems, expert systems was thriving for 5 years, and I was also chairman of the department at that time at IIT Madras. So, not to lag behind, I immediately create half this room and so on. This is a knowledge based system, that is a lab. Otherwise, if you don't, and after 5 years I removed that label. Because in 1986 came the so called neural networks, PDP volume. In fact, those of you who talk about neural networks, if you have not done that, you please remember, at least the whole field came about because of those 2 volumes in 1986. They are called PDP volumes. Because in NIPS conference apparently a couple of years ago, there were at least 30,000 people there. In the plenary talk, the speaker asked, how many of you have heard PDP volumes? Not a single hand went up. But unfortunately, the whole neural network field started then, because of those 2 volumes. So, the neural network displays this expert system. What do you mean by this neural network? It is a model inspired by our limited understanding of the structure and functioning of the biological neural network to display some pattern processing task, which human beings do only pattern processing. You can never do data processing. I give 100 mobile numbers now. Tomorrow morning I will ask you, can you repeat all those numbers? What do you do? You can. The machine, what 100 million numbers you give, it will just produce it. You see? So, human being, on the other hand, even number also. If somebody, your friend says, just a short meeting, oh, note down my number, he'll say you 94493. Oh, you may, oh, don't worry, I will remember. Suddenly somebody says, let's go for tea. 944, what is the other number? We forget. That is short term memory of the biological process. And so, on the other hand, if the same number, instead of saying 94, if he had said, or if you have listened carefully, it's 944, 188, something, 355 and so on, already you captured the pattern in it. That sticks you. And on top of it, when he says a number, don't leave him immediately, you repeat that number to him and also say, also, you see, I also have a similar number there, or whatever number you have, even my friend also, his number is like that. You say a few words linking with that number, it gets registered. That is learning. That is learning of a human being. You capture the pattern and link that pattern to the pattern that we have here is learning. I am coming to that in the next step, because I am still in the evolution of AI business, you see. So, ANN. That ANN 86, 80, that transition was abrupt. I think matter of 6 months or to 1 year, that's all. Everybody dumped knowledge based, rule based system and jumped to ANN and so on. Everybody, every Tom, Dick and Harry, including me, was talking about ANN and so on and so forth. You see, without knowing anything that's happening. Hundreds of books, including economists, philosophers, civil engineers, mechanical engineers, everybody wrote a book. So I also wrote, why not? So that is what has happened, you see. That is ANN. Please note that ANN philosophy, pardon me to say what you are talking today, the DNN, they are not neural networks at all. They have not a single feature of a biological neural network. You see? Just because you have, you see, another very interesting thing I saw in the previous lecture also, you see the model, neuron model, you see, again, that is why I am provoking you to think. Please don't, otherwise that is correct. That is, all of us have to say that. The point I am trying to say is, the moment you take a perceptron model, neuron model, put it anything other than a hard limiting one, hard limiting function, firing, not firing, it's not a neuron anymore. It is not a neuron at all. That is only at the level itself, model itself. And what to talk of the connections and what to talk of learning, all of them have nothing to do with the learning neural network, the so-called DNN that we are talking about. And deep learning is of course a tragedy, because the point here is there is nothing deep in that. You see, it is a shallow learning of a deep network, and we do deep network of a deep learning of a shallow network. That's exactly what happened in ANN. ANN is a small network, but each network is designed to perform a particular pattern recognition task, which you have to unfortunately define, because you build a model. So it is inspired biological neural network machine. So the inspiration for this is ANN model. Don't get confused here. This is ANN. Of course, you can't do it. You don't understand it, so you do. But the whole idea here is as much as possible. That's why you should always keep that perspective. There are theorems which we all ignore, and students don't want to even look at them. You see, the theorem simply states that if you deviate from this hard limiting, its functionality is lost forever. But having said that, so what your DNNs and other things are nothing but a large nonlinear models. Nonlinear models is large number of parameters. That is the correct description of that. Why is it that people didn't do it earlier? Because to determine the parameters, I don't have a closed form solution. I have to go to iterative incremental solution, and for that I need of course huge machines to do that. That is the reason why it didn't thrive at that point. You see, but of course now, if I say this in another forum, fortunately you are all nice people, otherwise they will throw me out. You see, because the point here is that is what they think is a neural network. You see, and so anyway, now coming back to the neural network, please understand. So until then, notice this is in fact first time I am, although I give similar presentation, first time I am highlighting it because this is a learning conference. All I am trying to say is, until now there is no learning. Yeah, that means I am already in 87, say there is no learning. You see what by learning I mean, so it is when neural networks came, the idea was learning idea came. Learning idea came. Because in fact all of us have a tremendously wrong notions about these things. That is my problem. You see, neural network inspired by a biological network with a most important function of a neural network, biological neural network, hence artificial neural network is this step function. Anything else? No. What it does is you are not asking for a solution to a problem, the solution to a problem by optimizing something, objective function. You are asking for a solution which satisfies all the inequalities that this step function produces. That is why, in fact, when I give a neural network course and ask the students to do assignment, when I give a problem, if all of them get the same answer, they will all get 0. They all get the final, if you give input, all of them will give correct output. But no two neural network that they design will be same. That is the beauty of this. Why? You can see, I ask you to, I might have said this in many forums. So, what is the number between 5 and 10? How many? You have infinite number of solutions. Okay, you follow what? Give me a number which is both less than 5 and greater than 10. What's your answer? So you can't satisfy that inequality. You can only satisfy this inequality. That's what perceptron does. Perceptron has this artificial, very beautiful function. The books written by physicists in late 80s, really very thrilling to read them. But of course, we are engineers, so why should I read? That's a different matter. You see, excellent analysis. You see, so you understand my point here. So the learning, the correct idea. That's why I said human learning, I didn't elaborate on that. That itself takes 1 hour to do. Human now, so there is a. I am switching to the next one already, but I will continue the evolution part after this. So human learning, you learn only through patterns. You don't have a capacity to learn from data. And ANN learning, ANN is a computational model which performs pattern processing tasks, and ANN learning, which is nothing but finding a, underline the word, a solution to satisfy all the inequalities that is coming out of this hard limiting functions in this. And if a solution exists, there are infinite number of solutions. That is ANN. And your job is, given the data, to find a solution. Any one of them is okay. And that's exactly correct. You see, for example, I give a problem, reasonably some simultaneous equations or adding some numbers and multiplications and so on. Same problem I give. What happens? No two people will come up with the same sequence of steps. They may come up with the same answer. So the solution is the only answer. Solution is the sequence of steps. And learning is not by the answer, learning by the process. So there are so many ways of putting it. So that is, so the, now I am mixing up the ANN and this one. Let me go back to the evolution again. I am still in 80s. ANN, I am talking about evolution. It lasted for 10 years. You won't believe it, that period I was also very active. I started floating a course on this, 100+ students registered. I told them in the first class, is both of us, we have assembled here to share our ignorance on the subject, because I don't know what was going on. You see? And slowly for 10 years it went on, and then what happened? Notice in the 10 years from 86 or 87, 1 or 2 years strike off, doesn't matter, to 95, 96, what happened? What happened was, if you utter a word AI, you will be thrown out. It was such a bad word to use. But before that, if you don't utter a word AI, you are looked at as a tribal. So what I have done, of course, we are all a little clever. All that I have to do is change the label on my door. That's all. My lab is this, my lab is this, that's all. That's why now it is the ANN lab, that's all. And then what happened was, 96, 97 is a very crucial thing. It so happens I am a globetrotter, I keep on wandering around various places. So I saw the first mobile, my friend was using, my host was using in 95 or 96 mobile phones. And that gave a lot of flexibility to collect the data. And with cameras on that, so much of data was there. And so, AI, neural network also is forgotten. Data I can collect, so I can get, machines are getting more powerful, so I can extract use this data to find, please underline this word, lot of people don't answer this correctly. That is when the machine learning word has come. Machine learning means on lot of data find the distribution of these whatever pattern, data, feature, that is machine learning. If you are given only one sample, what distribution will have? Whereas for a human being, if I have to recognize your face, I can't ask 1,000 faces to look at first. I only need, in fact, I need only one face to look at. Can you see? But we are all such a great people, even that face recognition they converted to data-driven problem, with a large number of face, and I don't know. I get so much of, but all my papers are rejected these days because nobody likes that, you see. You have to have a DNN, you have to have a table, your number is bold, this one greater than the other. That is the way to publish papers. And I review also every year, even now, at least about 20 papers. I think even one is exception, but almost all the 20 papers are like this. And I told them I don't know, but they said speech word is there in the title, so you are expert, so you read. I said there is no speech in the paper. Only numbers. That's why in my review I write, can the author explain what is the relevance for speech here? See, that is, anyway, that is the trend. Again, please note that don't get me wrong here that that is bad. No, please, that is not at all the intention here. The intention is that has a complementary role is a different matter. You see, it has a, that means you are trying to find the distribution of the features, and for that you need data. And so even that ANN has vanished in 97, 96. There was a special issue on Elsevier publication, a journal called AI. I don't know how many of you have heard that journal. And there was a special issue or debate on this around 1999 and so on, about 15, 20 top AI scientists were debating. It's an excellent collection of debate, very nice both ways, you know. I think because everybody is confused how to, what to say now, see. But in the process, of course, I have the machine, I have the data and so on, collect. Machine learning thrived for 10, 12, 15 years, you see. That machine learning is, anyway, I will keep aside because it was in 2006, something else has happened. 2006. In fact, when Ramakrishna asked me, I thought I will talk about it because the so-called philosophy of Boltzmann machine, all of you know that, but I want to put it across in my own way, see. And so, but you know, I thought most of you may not be interested, so I changed the topic like this. And it was the Boltzmann machine, such a powerful, all of you should read that if you have not read. You try Hinton and Sejnowski, fantastic. I mean, I can't find a better scientific analysis than that, you see. They introduced Boltzmann machine neural network in 1980s, early mid-80s, when the ANN came, and it was never used. Such a fantastic thing, because you didn't have enough machine. Any amount of power. In fact, I remember my friends in Japan were using 3 to 4 supercomputers to run the data to before. Of course, fortunately, power doesn't go off, so they could run and get some result for just distinguishing 3 characters, Badaga, you see. So that is the kind of a thing. So Boltzmann machine was never successful in implementation, but concept. But in 2006, that guy Hinton, he doesn't keep quiet, you know, what can you do? He produced a fantastic approximation, which is so good, called restricted Boltzmann machine. I'm not interested in that. Boltzmann learning philosophy is introduced here, but that restricted Boltzmann machine is the one that forced him to use the word deep learning. That is the origin of deep learning. See? And that that is the correct. So that means for about 3-4 years, that was thriving like anything, deep learning. Suddenly 2012 or something, that or data, digit data, something, somebody, or image data, somebody get some percentage bigger and so on. Everybody moved to that. They dumped that deep learning and called this a deep learning, you see. But of course, in the meantime, Hinton got his Turing Award and so on. That's a different matter, no, for his work. The point I am trying to say here is that was deep learning. And I don't have time to explain, but what that does is you can exploit the characteristics of descriptive and discriminative learning in building a system, which was not the case earlier. A classification requires a discriminative learning. A recognition, face recognition, requires a descriptive learning, which Boltzmann machine, these two ideas could be combined in that restricted Boltzmann machine. That is a beautiful thing. That's why it's called deep learning, you see. And unfortunately, that they threw that idea and this one and so on, and then went to this DNN from 2012 onwards. That's where we are stuck, DNN and deep learning. So that is the evolution part. Let me, I don't know, time part. Can I take another 5 minutes? I think people also, those of you are getting bored, you can, oh, that's not a, so the point is whatever, so that is the ANN, AI from science. What was initially called as science, because I didn't, there was some engineering that took place in between, that is from 60s, 70s to 80s or 85, that is called engineering. I don't know whether how many of you have read Herbert Simon's book called The Sciences of Artificial. The Sciences of Artificial. You can type on Google, you will get that book free, you see. and it's only about short book, some 150 pages or something. The point here is you are able to inject this knowledge and so on, build systems and so on. That is all your idea, isn't it? But although it is engineering and you are building okay, this he says, what is the science behind this engineering? That is the book that he has written, very beautiful. So that means AI went from science to engineering, and now we are last 10 years in the technology. Technology means whatever I said, data, huge computing power, nothing else. So now I am coming to the next topic, human learning, ANN learning. I already mentioned that, but human learning, it always learns from pattern processing, never data processing. See? And human learning is a continuous process, and human learning is an online process. You don't collect all the things book together and learn. Suppose I give you 1,000 books today, what do? You will run away, let the books be there, that's all, because you can't read them. You see? You see the point I am saying, human learning, and also you don't collect all of this and learn. As and when I speak, you learn. As and when I read, you learn. So that is the human behavior. And the most important, this I need a lot of time to explain, but I would like to say this. There are two things. First of all, I think human, when I am talking or you are listening to me, the biological architecture is not a static one. It is a dynamic architecture. Every instant it is changing. Every instant it is changing. You see, it is a dynamically reconfigurable architecture. What it means is the weights that you are talking about, neuronal connection, those are also changing. If you only take this subset of neurons and not that subset, the weights, so the weight space itself is changing. In learning process, the weight space is changing. These are not well polished presentation, but I think these ideas I got in the last 2 days. So, and on the other hand, ANN, you need an architecture for each pattern recognition. You have to define the pattern recognition task. That itself is hard. But once you define either a classification or a mapping or whatever it is, you need a ANN model or a stability, plasticity, element, temporal processing, all of that you can take. For each one there is a separate architecture. I can reel out any number of avalanche architecture for temporal processing, neocognition for pattern variability and so on. So there are dozens and dozens of, once you say architecture, once you come up with the architecture, problem is solved. Programming is somebody else's problem. See, architecture involves not only structure, but the learning algorithm. That's why there are estimated 7,000 to 10,000 learning laws in those days. Because each architecture requires a learning by itself for you to complete the architecture. So that is the architecture that you have, and the learning is coming up with a solution to the problem, or there is nothing like a the solution there. You see? So that is the ANN part. And the learning of that, everything, you see, perceptron learning is the only beautiful learning where you can come up with a solution in spite of the fact that it is a set of inequalities and so on. You could not do it for a higher multi-layer one for the simple reason that perceptron learning directly does not work. Even today it is a challenging problem. If any of you are, we do not know whether a solution can be obtained or not. If we can come up with a solution for a multi-layer perceptron, please note that perceptron means hard limiting. You will get almost a Nobel Prize or equivalent of that. It will be a break. So somebody said, oh, don't do all of that, make this hardly, slightly adjust Baba, like this they will say, and that hard limiting one, they made it continuous. The moment you make it continuous, you can see half field capacity theorem, the performance drops down drastically. Performance of a pattern storage drops drastically. The capacity of neural network drastically. But you say, so that is what, because you need a differential function. That is where the back propagation came. Paul Webrose, he didn't think of all of this. His PhD thesis in 70, he wrote for something else this idea. What he said was, I have a mean squared error function, don't worry about it is a linear model or something, and don't worry about whether that is a smooth parabolic function or something, just take a derivative. What do you mean by taking a derivative for a rough curve like this? That's why almost everybody kept quiet and nothing, but he said forget about the error surface, just take a derivative. That is the breakthrough result. You see, if you do not explain and take something, and that is all. That is where the neural network field, they were so called back propagation. Even today that is what it is. So, that is artificial. So, coming to artificial neural network, the architecture is specific to a problem, and the solution learning is simply trying to adjust incrementally the so that you satisfy the inequalities if you can really satisfy them, and so on. And notice that it is the weight space for a given architecture is fixed. So, the weights, only weights change, but the weight space is fixed. I didn't actually, as I told you, last 2 days only, yesterday only, in fact mostly today, this morning in flight I was thinking about it. So, these are not well polished presentation, but weight space. Now, go to the third one. You must distinguish between human learning, ANN learning and machine learning. Machine learning does not have this characteristic of ANN. You see? So, machine learning simply means, you see, that is why ANN does not require that much of data. You see, because so machine learning, I simply have maybe, as some of you projected, some 3, 4, 5 or dozen architectures and so on. Keep pumping the data as much as you can, otherwise use the GAN to generate data. I mean, I am awestruck to understand, although it is working, success is a rare paint which masks all ugliness. That is exactly what is happening now. You see, otherwise you scratch your head and say, how can you generate new data from even GAN, which has the pattern variation of a natural system? I do not understand. But it is true. Please note that I am not passing any negative comment. I am trying to analyze these problems. You see, I may be wrong, but the point here is that is what it is. You see, so now machine learning. Machine learning simply means you need large amount of data, and for a given model, nonlinear model. Unfortunately, since I happen to know a little bit of neural network, I can't call that as a neural network. But otherwise, you know, it is a highly nonlinear model with dozens and millions, and now only last week or 10 days back I heard that somebody, Google I think, they do not have any other work to do. So, they used 1.7 trillion parameter neural network to train the model and so on. You see, all that is nice, you know, I think they can do it, but and they are getting great performance. So, as I told you, I am not disputing that at all. But I can't see why should that is the only, should we think that that is the only way? That is important, I am not disputing, but there could be other way as well. You see, so machine learning simply means that it is adjusting the parameters. I do not want to use the word learning. Perceptron learning is the right learning. Human learning I cannot articulate. So, perceptron learning, that learning has nothing to do with this. This learning is simply there is an objective function, you optimize or adjust the parameter, that is what you are doing. You see, that is the machine learning. Machine learning is simply adjusting the parameters to reach an objective function, to realize an objective function, that is all. That is the machine learning. And for that you need large amount of data, because you want to capture the distribution, unknown distribution. It does not fit into Gaussian model, Gaussian mixture model, any other distribution. So, that unknown distribution you want to capture it by the network, that is fine, you see. And also in this context there is a small catch here, you see. The catch here is everybody talks about this can solve all the problems and so on. You see, carefully observe that yes, it can solve the problem, but not the way you do. Not the way you do. So, there is what is called another field, lot of researchers are working. In fact, I was forced to sit in that evaluation of those research scholars and so on. That is explainable AI. That means what the DNN. First of all, what DNN is doing through machine learning, you call it as AI, I do not know. And second thing is explainable AI, you want to know what the various layers are. It is doing something, but you cannot explain. You want to explain in the form of the way human being does, sorry, because you just built a network and you are just something is coming out or popping out of the layer, and it is solving, that is fine, you see, there is no problem at all. But the point here is that you want to explain it in terms of a human understanding. Fortunately I am a retired person, so I am lucky not to worry about this, you see. But otherwise, if I am an active teacher, I have to worry about it. Either I follow them or I have to I don't know. Anyway, let us not worry about me. So this is the human learning, machine learning, neural network learning. You have to put that because that is closer to the biological network, at least intended to be closer to, whereas you may simulate it on a computer, that is a different matter. The model architecture is what I am talking about, and the machine learning. And machine learning is data driven, human learning is pattern driven, and of course this is neural network is in between. You see, that ANN is in between. So that is what. And lastly, I will take just 2 more minutes. Sorry for you see, the last part I wanted to say is missing science, this AI. So if you go through what we are doing through this ML, DL and so on and so, there nothing is wrong with that. We are doing great, we are working great. All I am saying, my 80-20 you apply, that is all. And so in doing this, what is missing? I had given a talk on this about a few months ago, the missing science in artificial intelligence. Artificial intelligence as we understand today. That means anything that we do with ML, we call it AI. So what is missing there? Number of things are missing. One such example, I don't have a list of that. I have it in my material, but I don't want to. One striking one I will tell you. There is what's called the selective attention mechanism, which a human being uses all the time. All the time. When you are listening to me, you are not listening to all the sounds that I am uttering. If we happen to do that, you don't understand a bit of what I am saying. You select a subset of these sounds, rest of it you plug it in from here. And since each person has a different knowledge of you select differently. That is a beautiful, intelligent activity of a human being. At least I can't see a foreseeable solution for that, at least not in my lifetime, you see, and even in future also. Because Fukushima in Japan, he worked on a similar thing but at a much lesser, lower level for about 20-30 years. Now I don't know whether he is still alive or not. You might have heard the name called neocognitron and derivatives of that. He was meant to something like this, you see, but selective attention. All the time, if you don't understand what I am saying, you can easily understand if you still happen to read some newspaper. I hope you read, some of you. You know what is the newspaper I am talking about, not the on your mobile. I am talking about a big morning newspaper. You see, just think how you are reading, little bit. Do you read THE, HI and U like this, each character, or do you read each word? The moment you do that, your friend comes, what is in news? I don't know. On the other hand, that whole 10,000 words in one page you finish in 1 minute and you get 80% of the message. Selective attention. It's a very important concept of intelligence, which I can't see in any foreseeable future to be implemented with the technology that we have. There are many other things like that, but I just want to, and another very important, there are many, but I think I will stop with this point, that you see, when I joined IIT Madras as a professor in 1980, since I am in Tamil Nadu, I am a Telugu speaking fellow, lived in Kannada area at Bangalore for 20 years. So Tamil people you don't know, they are very nice guys, they want to speak you only in Tamil. So I thought, so the point is, I thought immediately what I did was learn Tamil in 30 days. I bought that book. And you won't believe, I am a very sincere guy in all of this. See? So I spent every day 1 or 2 hours to practicing those characters. And at the end of it, I learned in 30 days those characters. But the problem is when I go to the road and see this banner, I can't read it. See the point I am saying? So that is not learning. You have not learned the Tamil characters. The Tamil, any characters or something, if you type it and put it, you have destroyed all the pattern information. To keep the pattern information, you should keep all those variations and observe several variations of that. Then you observe the pattern of that character, which may be different from the same character pattern that you observe. That is learning. That is pattern processing, which no machine does it. You understand my point? So that means these are some of the things which I say science. And what we are doing is technology. Both are needed. You see? So, but this science is missing in this technology. Okay? And I think I will stop at this point. Thank you very much for your attention. I think. Can you take it out, please?
Yes.
I don't know.
Thank you, sir, for a wonderful talk. Anybody has any questions?
Oh, yeah. You ask a question, each time I will come up with a different answer. This is not my phone. My phone is sorry. That is the human way of so please. Yes,
one question. I think
I have hard of hearing problem. So
yeah. So no problem. So when you do all this machine learning or deep learning and all, it looks very fancy and everything is nice. But when you really implement, it requires a lot of energy actually, even to collect data. Small amount of data also, it takes a lot of thing. And people are talking about the consciousness, right? Really, the human consciousness is like we have a lot of collected data is there. I think as soon as the newborn baby is born, they're able to learn quickly. You can, there's no comparison at all for the human, right? For a machine, right? That is working in a limited frame. What do you think? What sort of the higher end we can reach when you compare in terms of the human consciousness? The machine can go up to the maximum stage.
First of all, I don't understand the word consciousness, although I know the reason I am saying is I am very careful, at least in public, If we are talking to one, I can use a lot of loose statements, but the point here is when I am talking to, I don't know what is the consciousness, and I also know that those who talk about it in write papers on that also don't know what is consciousness. That is clear, you see. And so, because that is a human ability. And you can't, anything that is human and natural can never be understood. That is 100% sure. You may take only some part of it. You see, suddenly a robot doing something, you see, we are all very happy to, if a robot does Bharatanatyam and a human being does robotic dance. Like, I don't know what we are interested in, a human being doing good Bharatanatyam and robot doing this. But we are just the opposite, you see. So, that being the case, I think they're complementary. You want to make them as competitive. That is the wrong thing. You see, I think all the, even learning, machine intelligence and knowledge, it has a human attribute, but it so happened that it percolated into all this literature and technology. We can't help it, you see. But we have to learn to live with it. But otherwise, you should not have used those terms at all here. Same thing works for the consciousness. Because something that you see as a fancy, some model, no matter how sophisticated it is, you see, as long as it is coming from, from a machine, it is artificial. And that means you imagine that you have understood that. As at 20%, you see, then you see you didn't understand anything. That's the point. Please note, I think I have read a lot of articles on this. And see, people like Ray Kurzweil and so on, I heard his talk also. He wrote a lot of books and so on. I get so bored with that. You see, every time he said, we are solving all the problems in the world. You know, we are getting a robot doing like a human being in surpassing human intelligence, super intelligence. That intelligence word you are using there is different from the intelligence word of human being. That is the point. You have to understand that. You see, because if you don't, the point here is something surpassing. What do you mean by that? That means in future you only produce robots, not human beings? I don't understand this logic at all. You see, that's some complementary thing is what you have to reckon. Both are needed. You don't ask me to walk from here to home by a bullock cart or by walk. You know, it's 15 kilometers, so I have to. I need a transport. It's exactly like that here. You see, I think our inability. That is, as teachers, we are also wrong here. We are as teachers, not only me, all of us, and also the literature, the way it is spreading and so on. I mean, you are lost. You see, in this ocean of this, there are estimated 25,000 papers on machine learning in 2019 alone from US. What does it mean? See, that is what you see. You write, you say this is what it is and so on. But the 20% would have helped you to see what it is not. But of course, unfortunately, the scientific community don't accept those things. That's a different matter. We have to go through this passing phase, maybe another 5 years and 10 years. Afterwards, it will change. Something else will come. If I know what something else will come, that will come right away. You see? We have seen this change over the past, at least I have seen it. 50s means what? 7 decades. 7 decades I have, at least 6 decades. You see, I have seen this. So I never saw something is static. It is changing so much. That's why I had to, every decade I have to change my, this one. Oh, somebody gave me a label of professor of computer science. I keep on scratching my head, what do you know? You see, the point here is, but you have to, because that is one you can get students and everybody is professor of computer science and so on. You see, this is how the labels get changed, but our understanding is all. You see, but a good teaching or good research or good writing is one where you write on all sides and give the proper real perspective rather than highlighting this and not that kind of a thing. You see, all these percentages number. I mean, even now you must be feeling, I am sure, if it is one paper you will read. If there are 100 papers, all of them, do you ever read your own paper? You don't read. You see, your job is only to publish, not to read. You see. No, that is what it is. I have never read any of my papers. I think some 400, 500 papers. God only knows what it is. You see, that's why I keep saying that's all noise. You see, you have to extract signal out of it. You see. Sorry, I'm not sure whether I answered or not, but I know everything gets into a discussion like this only. You see, yeah. Sorry.
Thank you, sir. Any other questions or doubts? I thank sir for wonderful thought-provoking discussion. Very nice to see the other front of it and from your vast experience, sharing some of the very important aspects which are important to the researchers as well as for the growing persons in this field. Thank you very much, sir. Thank you. Thank you, sir, for coming and at the age of 80 with this enthusiasm, sharing all the experience with us. Thank you, sir.
I request Dr. RKG to give a memento to Dr. Yagin.
Thank you. All Lord's blessing. Keep it here. Oh, okay, good. Thank you.
So 6:30, right?
So, do you have some more lectures today? People get bored.
Yes, tea is, that's what I informed. I think around 6 is there.
Okay, so just two announcements. We will have a tea at the same place on first floor at around 6 o'clock, and then 6:30, from 6:30 onwards we have a cultural program in TC1, which is just next to the place where we were having tea. So we request all of you to join us there.